Okay, let me just see.
If you set it to
Okay, now can you just check? It's a different link, I think, now.
And also what you need to do is it connected to this, only connected to this one, isn't it?
Still the test bed.
But this is a different stream now altogether.
A different link?
Yeah.
Oh, okay.
Did you
How
make
to
a
share this
pilot?
link?
Oh, wait, let me edit this.
Because
It's not, wait, give me a sec. Okay, now it should be there.
But
There it is.
but the problem is that this is now a different link, isn't it?
How to share
Then we
the
just
link?
edit the post on.
we can share it around afterwards. Right. It's doing its thing.
Okay.
Yeah, this is fine. I think this should be streaming what I'm seeing here. This.
So are you sure we're muted?
Us on the Jitsi. Oh.
Yeah. Oh, great. Alright. Alright. And then if you just stream the Jitsi.
Yeah, that's fine.
Alright. And
And
turn
then-
on your webcam in the Jitsi as well.
Yeah.
Alright, there we go. Okay.
Okay, no, you have to go to this one. Okay, and then you have to go, then to these dots, because the camera is now used by another program. So you have to get the camera into Einstellung, and then to, yeah. So you have to log out the camera from the other stream.
Yeah, so just
There it is. Here we go.
cool. There we go.
Okay.
Back on. Just
Yeah. Okay.
Okay. Sorry. Thank you all for bearing with us through a few technical difficulties. So we can now get started with the next. Sorry. Okay, so we can now get going with our next speaker, which should be Tom Green.
Present.
Hi.
Okay.
So feel free
Let
to.
me share my screen here. 1 second.
Yeah.
Allow to share screen. Yeah, that'll do the job. Okie dokie. Alrighty.
Yeah, you can provide a brief introduction on yourself as well before you step into.
Oh, it's all coming. Don't worry. It's
All
all.
right.
I've prepackaged everything.
Okay,
It's,
great. Then yeah, you have the floor.
And this is all recorded, isn't it, too?
Yes.
Hello?
Yes. Oh.
This is all recorded, right? Because I should let you guys know, just a bit of a disclaimer. So I'm in Australia right now, and like all good Australians, I'm actually just finished work for the day, and I'm having a beer as I do this. And I actually haven't done a dress rehearsal on this one yet. I apologize. Robert did reach out to me to ask if I could present on this, and I'm very excited to, but I just didn't have a chance, unfortunately, with all the work and everything else that's on the boil to go through and properly do a dress rehearsal. So this is actually the first go, just for me and for you guys. So it's pretty exciting. We can do this together as in one hit and see how we go.
Yeah, great.
Yeah, exactly. That being said, however, of course, I've seen astronauts at the International Space Station, who've come down and during COVID, they were doing presentations, they were finicking around with Teams invites and Skype invites. So yeah, we'll see how we go. And if we get it wrong, that's okay, because people better than myself have definitely made mistakes as well. So that's all good. So when Rob asked me to do this presentation, I decided I might take a slightly different approach to doing straight science for Moon Day. I thought I might look more at some of the cultural phenomena I'm seeing coming through, just anecdotally as someone who's worked in the space industry. And I guess some of the issues I see emerging now and well into the 2030s that I think are of some concern. So I titled this The Risk of Moral Panics, New Space versus the 2030s. It's basically a story of us, the moon, and other space activities. and possibly some solutions will help us get through the next stage. So to kick things off, first and foremost, here in Australia, we like to do acknowledgement of country, where we sit and where we stand, where we live. I'm currently presenting this on the land of the Ngunnawal and Ngungari tribes here in and around the Australian Capital Territory. I believe Dr. Doris Gross is also from as well. So hello, Doris. Hope this applies to you as well, where you are. But fundamentally, it's an absolute privilege to be on the lands of these elders, past, present, emerging, who have done a tremendous job in preserving the land and for maintaining the waterways and the culture from then until now and into the future. And one of the things with our acknowledgement of countries we don't do often here in Australia, we like to talk about the land and the water, but I actually think it's also important to acknowledge the skyscape, or the starscape, I should say. The stars look different at every different latitude around the world, and to a certain extent also the longitude as well, I suppose. So every part of the Earth offers a slightly unique perspective on where we are around us. And the stars, of course, are the one thing that unifies people around the world. It's always been a central part of all folklore, all customs, all religions of every people around the planet. So I think it's important to acknowledge that as well. So a bit about me, and this is what I was getting into. This is pre-packaged. When Robert Marnie put this together, he was texting me the other day and saying, "Are you able to come?" I said, "Yep, no worries. What time zone you in?" "I'm in this time zone." I checked the emails, went to the wrong email, went to the right email, the invitation. I asked him if I could put together a slide deck. He said, "No worries." And I was going through the speaker list, and I saw that I was listed as independent. And I saw everyone else is from NASA, and they're from DLR, and they're from other. We've got ANU in space, of course. We've got other organizations, and I'm the token independent presenter for today. And that with great power comes great responsibility, or in this case, I suppose, irresponsibility. Most times you see an independent presenter, they usually have a pretty oddball presentation. They're not really affiliated with anything. I thought, well, I could reach out to Robert and say, "Rob, I founded my own space company, which is still doing reasonably okay," or, "Rob, I'm actually a project manager with New South Wales government. I'm doing experiments in a live environment." But I actually thought, I kind of like the idea that I'm an independent presenter. I actually thought, in some respects, it actually allows me to free up and talk about some concerns I'm seeing coming through, which I think might be of interest and might be of relevance to everyone here. And I guess here, to that point, there's a bit of a block text here from Marshall McLuhan talking about the idea of figure and ground relationships. We talk a lot about objects, but we don't talk about their relations to the ground around them. That is, say, the hidden networks that allow for certain things to come into existence and being. And with that in mind, I should probably talk a bit about where I came from. So about almost 10 years ago now, I founded a space company with a colleague of mine called Paddy Newman. He was doing some pretty remarkable work at the University of Sydney on some solar electric ion thrusters technology, which we thought was pretty darn good. He was doing it as a PhD student, and we thought this is probably good enough if we commercialized. This is back in a period when the idea of a startup was two guys eating ramen food in their bedroom and doing coding for a killer app. The idea of hardware startups didn't really exist, and they certainly exist for space. So we looked like slightly crazy people, but we thought, this technology we think is probably good enough that it actually has some merit in being turned to a company to look at propulsion systems for on-orbit maneuvers, for essentially anything to do with regards to zero gravity environments for maneuvers and for movements. But along with that, we started to realize we should probably engage on the academic front in terms of the humanities and educating, informing in terms of our technology. And the reason for that is because the technology runs on metal, and the idea was that we could potentially use space debris as a fuel source, as a way to simultaneously reduce the amount of debris and pollution we have in space, but also allow us a guaranteed supply chain of fuel as well, which we don't have to get from Earth. But of course, then ethical questions started to arise. If you're going to look at harnessing any sort of space debris, you then start to have to think about what do you want to keep, what are you okay getting rid of? Most people will be okay getting rid of a booster from a rocket, from an Ariane 5 that was launched, probably about 3-4 months ago. Probably very excited about the idea of the Hubble Space Telescope being turned into a bit of filament to be eaten up by a solar electric ion thruster. So we started to think about how to engage with the humanities and how to do some outreach with them, some of the ethical and practical issues we had. This is a mix of conferences we did. We did some of those stereotypical academic conferences where 4 people turn up and they all know each other and they put out a publication that has a circulation of 4 or 5 print issues for a journal, and that's about it. But we also went to IAC quite a few times as well to present our work. We actually have a paper coming up at IAC later this year looking at propellant issues in space around orbital maneuvers. But we also did a lot of outreach as well to the general public. So people who work in the space industry know, of course, that news articles, in some respects, it's a bit of labor to do them, because you don't really ever get a situation where Uncle Pennybags will dust off his monocle and go, oh wow, that looks pretty exciting, I might run over and invest money in them. You do most of these news articles really more than anything else as part of your social impact and to improve your awareness as to what it is you're after and what your objectives are. So we also engage pretty heavily with the media, and again, this is just one of those administrative burdens or administrative tasks which we took on. We maintained a database of journalists we could reach out to, newspapers, print, so when we did anything, we could keep the public informed, because obviously space, it's a commons area. What we do has an impact on everyone, and we thought it'd be the best interest to ensure that we could engage not just the academic community in terms of what we're doing, but also engage the public. So we did that as well, and we continue to do that to this day. That's still something which Neurospace does quite frequently. They just had a successful launch on Transporter 8 mission from SpaceX a couple of weeks back, and that again, a lot of news around that. But what we started to realize, I thought we were doing a really good job with this. We truly believed, at least here in Australia, we were doing an exceptional job on doing public outreach. We thought that we, not necessarily us personally, I'm not going to bump up our own tires, but we as an industry had informed the public as to what the issues were in space and how space could help the world. And it appears as though we may have actually overstated our own ability. We may have overestimated our own competence in terms of communicating ourselves to the bigger world. Just a few weeks ago, here in Australia, we lost $1 billion project. The National Space Mission for Earth Observation was a program of work to essentially allow us to put up the appropriate amount of space telemetry to monitor our own domestic environment here on Earth. Australia, of course, is responsible for about 10% of the Earth's surface, because obviously we have not just the continent of Australia and the oceans around Australia, but also the Antarctic region as well, which is part of our Antarctic territories. It's actually quite a large landmass which we have to monitor and ensure remains pristine, or at least relatively pristine, against ecological impacts from climate change. And this was one of those projects we had that was a bit of a crowning achievement ensuring this. Alongside this, we had some more sub-programs in terms of our Moon to Mars program, which of course is self-orbiting Artemis, and also spaceports generally across Australia to reduce logistics, because obviously logistics come with carbon emissions, but also to provide more resilience in terms of our launch capability and profile. These all got canned. And not only they got canned, it was a bit of a surprise, the Space Industry Association of Australia, as well as the media generally. And I think it just came as a bit of a shock to everyone as to what occurred. And it probably shouldn't have in hindsight. There were a few canaries in the coal mine, not just here in Australia, but throughout the new space sector. We do have a lot of people who are coming in with humanities backgrounds, who have a passion for providing, comfort and security to individuals around the world, as well as the planet itself. But they may have been misinformed as to the agendas around space and space activities. They may be aware of the fact that fundamentally, if you're doing off-Earth mining, you're going to have less of an impact on your environment if you dug material out of the ground. You're talking about literally tons of material has to be processed to get even a small amount of copper from a copper mine here in Australia. Our iron ore processes are exceptionally labor intensive and carbon intensive. One of the reasons why Australia remains as a large carbon emitter for our population is because we provide all the raw material that keeps the rest of the world going. Mining is exceptionally impactful in the environment. And for example, just that one alone, off-Earth mining would potentially allow for a significant reduction, not just in our own carbon emissions here in Australia, but also globally as well, potentially. But this seems to be lost in terms of a lot of people coming from humanities, in terms of understanding what the issues are, and the fact that really we're not monsters, we're not a bunch of, as some people have said, colonizers on an imperial project for Earth. This isn't a cult-like approach to changing the planet for the negative. So what has started out as a very nice approach of saying now more than ever we need the space philosophers, trying to call that call of arms to get the humanities involved in space and understand what the issues are around space, or more point, what the issues are here on Earth that could potentially be solved by space. What we may have ended up in doing unintentionally, and I'm not saying that this again was new in space, I think it's more just generally the feel that's arisen, is created a situation where some people are feeling a bit more reserved around the idea of space activities being done by the private sector. Keep in mind, obviously, the private sector you're still bound by the laws of the nation you operate in. For example, Neurospace GmbH, that is a company formed in Germany. They're still reliant on the rules in Germany and the provisions in Germany. The German government still has oversight over Neurospace. How do I know this? Because their suffix is GmbH. That's how I know this. So this idea that you'll see cavalier behaviors automatically from your emerging space companies is a bit disingenuous and a bit low resolution in terms of interpretation. Other thing too to keep in mind, I think this is important to do. This isn't simply a matter of some concerns of a few people who disagree with the objectives around space and space activities. This actually has some serious impacts. Community standards shape laws, and those laws create actions, and those actions subsequently change and shape community standards. There are a lot of legal theories that subscribe to see how law is formed and how it's created and how it's used and maintained. All of these theories, be they natural justice or more of a Rawlsian approach or positive or negative freedoms, these approaches to law, be it civil law nations such as Germany or common law nations such as Australia, they are fundamentally rooted in community standards of practice, which subsequently, through action from the community through elections or lobbying with their executive branch of government, are turned into laws, and those laws obviously have impact around them. Those laws can have positive impacts, they can also have negative impacts. And I think that it's important for us to do outreach and continue outreach to ensure that we see the right rules of the road being formed. Not necessarily to favour us, this isn't about lobbying or about getting ourselves a better deal, but more that we can actually educate, I guess, not just the public, but also our own industry in terms of what our responsibilities are and what our potential outcomes are. So with that in mind, I've got about 5 minutes left on this, which is actually pretty good because I wasn't sure if I'd go over time or not. But I suppose our options are to be cognizant of our stakeholders, engage their decision makers, attend forums and other means, but also to remind people we're not billionaires. And I think these are probably the four things we need to keep in mind going forward into the 2030s, because I don't actually think the future of the new space arena is actually potentially positive on the whole. We've seen a lot of liquidity leaving the investment market, particularly for innovation and startups. We've got a lot of people who move into retirement. I believe at the end of this last quarter, the majority of boomers are now in retirement, which means speculative investment will be dropping off. They'll be putting their money into more secure assets and bonds. So it's not a matter of reduced investment, but also public will needs to remain there as well. And I think for that to happen, we need to just be aware of the fact that our stakeholders may not be fully informed as to what's occurring. They may have a situation where they're conflating science fiction with reality. But I think it's also important for us to directly engage their decision makers as well, explain to them how space can be of use, how it can advantage them, what the outcomes are, not just at the moon, but also space activities in general, but also to attend forums that are hosted by our colleagues and friends in the humanities and from non-engineering and scientific backgrounds to reaffirm to them what our core objectives are and why we're trying to accomplish them. And just once again, reaffirm the fact that we're not billionaires. Yes, I understand that Jeff Bezos and Elon Musk are very prominent right now alongside Richard Branson, who's exited out of Virgin Galactic quite recently. But fundamentally, we probably are seeing a lot less heavy hitters financially in the space environment than we would have during the Apollo programs in the 1960s. Everyone forgets this, but Apollo was built by Motorola and DuPont alongside Raytheon. They usually were the primary contractors behind it, alongside Lockheed and others. We're actually seeing a lot more smaller companies come through, such as Neurospace, of course, and also Newman Space as well. And I think it's just important we just reaffirm the fact that really this is actually probably the first time we've seen space become democratized to a point where young people with very little capital can come together and create their own wonderful inventions to make the world better for everyone. So that basically closed it out. As you can see, I've dovetailed the first slide with the last slide. And the reason why is I spent a bit of time putting this one together. I had a bit of fun with this one, actually, I'll be honest. But I just wanted to just reaffirm the fact that I do see an issue coming forward. We've seen a lot of good science and a lot of good technology in the past being killed by moral panic. Stem cells comes to mind. Iridium, when they first went up, they wanted to put cameras on their satellites to do Earth monitoring. That was declined by the ESA. They had some concerns it might be used as a spy tool by the Americans. That prevented Iridium to do weather monitoring until the 2010s when LEO Labs came around. We do see these issues arise frequently with any new technology. And I just feel as an industry, we need to be cognizant of the fact that we need to take other people on the journey with us and provide them a forum as well, where they feel they can freely talk to us about their reservations, and we can address those reservations freely and frankly, so there is no confusion. It's not a solution, I think, that will be solved by any person in particular. Obviously, we have to do this as an organization, but it's something I've been toying with these last 2 weeks, I suppose, because here in Australia, we just lost $1 billion program, which a lot of people were relying on to advance our own space capabilities and competencies, and it was awful to see it go. And I hope for a better world for us and for everyone else. But I feel the way to get there is if we address this problem head on and acknowledge the fact that we're not actually very well liked outside of our own circles, and that's something we just need to accept and challenge as well. So that's my presentation. I believe, according to my timer, I have 1 minute and 50 seconds left. So if there are any questions, I'm happy to take them, or alternatively, we can go to the next presenter. I can take them at the end in a general forum. I should have put my email on the bottom here. I apologize, I didn't. But if you want to reach out to me, feel free to reach out to Robert Marnie in the first instance. He'll put you through to me. And thank you for your time.
All right, thank you so much. Unless we have any questions, I will then take a few moments to introduce our next speaker. So feel free to just jump in now if you have a question. Okay, well, in that case, I will just take a very, very quick break before introducing our next speaker. Okay, I think it's. Oh, should we change it?
It's starting.
Oh. Oh yeah, you're right. All right.
Okay. I believe Doris is in the call, so if you just want to invite her to start speaking. All right, cool.
All right, so thank you so much, Tom, for that wonderful presentation. Now we'll be moving on to our next guest speaker. So I'd like to welcome Doris Gross. Feel free to just chime in, and yeah, you can start sharing your screen and introduce yourself.
All right, thank you very much, everyone. I'm gonna start sharing this screen, and you tell me whether the full screen mode comes through. Is that okay?
Yes, that's good. We can see well. Thank you.
You see the full screen?
Yes.
Okay, cool. All right. Well, so yes, I'm also talking to you from Australia, and I agree with Tom. Beautiful Ngunnawal country and Ngambri people country to pay my respects of the elders past, future, and present. And I also totally agree with the culling of the funds. We are actually lucky at the Australian National University that we were funded a grant to build laser communication activities at the Australian National University that I want to talk about. And so as a bit of a motivation, I know this day is about the moon and exploration to the moon and rovers and stuff like that. And I'm basically proposing we are giving you the infrastructure to communicate to the moon at super high bandwidth and optical frequencies, also from the southern hemisphere to increase your coverage. But I'll come to that later. So if I now go on, do let me know if you don't, like if something happens with the presentation. So A and U, do you see the cursor on my screen? Oh, no.
Yes.
Okay, so this is ANU, which is situated in Canberra, and as you can see, lots of research schools that do all sorts of different things. And before I dive into what we do at the Research Group of Astronomy and Astrophysics at the Advanced Instrumentation and Technology Centre in Canberra, here is the headquarters of the ANU Institute for Space, which is a really awesome institute that connects all of us space researchers within ANU with each other, as well as it's also like a front door for all space capability at ANU. So if you are looking for a partner in Canberra at the ANU that does anything with space, the in-space people are the ones to be contacted, and then they can connect you with anybody at ANU who does that stuff. And at the same time, we can also reach out to them, and they help us connect us with people that they know of in the rest of the world and in Australia. And we are sitting here at the very back. So we're actually not on main campus. We're on a little mountain, which used to be a solar observatory called Mount Stromlo. And that's how it looks like. And we have a couple of very old telescopes that most of them are actually defunct because there was a big, huge fire in Australia in 2003 and they all got burned down. But we do have lots of other capability on the mountain that I'll talk about in a minute. First of all, I would like to kind of give a very brief overview of sort of the missions that ANU Institute for Space is supporting. So we have capability at ANU to do bushfire resilience. So we are building infrared detectors that can look down as Earth observation to the ground and detect how much, we call it fuel, that's why it's called OSFuel, how much fuel there is on the ground, meaning like dried up bushland or trees and stuff like that, that will potentially fuel a future fire. We also have precision measurements from space. So we have the capability to launch interferometric satellites into space that can do high precision gravity measurements that can then do or refer to or yield not only gravity changes, but also then basically defer how much the ice mass has melted and stuff like that, which is pretty awesome. We also have researchers working on space medicine and to see how, things change in space once we go into space with us humans and plants. And we also have space law capability and the Australian Centre for Space Governance at ANU. We also have, maybe more interested to the community that I'm speaking to, the National Space Qualification Network. So we have actually a national space testing facility with us here on the mountain at Mount Stromlo, and we can test CubeSats in vacuum chambers up to a cubic meter, and we have shaker tables and stuff like that, so we can fully test spacecraft or the satellites to make them spaceflight ready. And finally, we also have an advanced communications program that I'm going to talk to you about. And when I talk advanced communication, then I'm talking laser communication and optical communication, because for those of you who are not aware of this, on the little picture there depicted, you see all the radar frequencies or radio frequencies over the different frequencies from top to bottom. And the color coding are the types of satellites and the spectra that they are given certain spectral bandwidths. And it's pretty crowded, and particularly with mega constellations going up. The satellite world is having increasing issues with finding free slots for radio assignments. And so optical communication can help with that because it transmits at higher data rates, faster speeds. And it also has technically higher security because the beam width is smaller, and there is no spectrum licenses because it's a new technology globally. However, in Australia we do, but that's not really too much of importance as we don't have too many licenses yet. So at ANU, we're actually building an optical ground station. So it's a ground-based telescope here at Mount Stromlo in Canberra. And the site itself, so the ground station does not fully exist yet, but the site itself has a research school. So we have obviously established infrastructure. You can access the site super quickly. It's not very remote, and we have like obviously power, water, and data access. And as you can see in the picture, the telescope itself, I have that on a other slide, is fairly small compared to the design of the facility. 70 centimeters. Oh, down here we are going to have a Coude path that goes down here. For those of you who don't know what a Coude path is, so the light from the telescope can basically being put down here and into the clean room, and then we can have lots of research instruments here in the clean room, so we can have lots of space where we can actually do lots of, new instruments, lots of state-of-the-art research. And we have lots of adaptive optics capability in-house as well. And this telescope itself is LEO and GEO and Neurospace and lunar orbits capable to track. And we were lucky enough to just get into the recent funding round from the Australian Space Agency to get and support the NASA's Optical to Orion mission, which will be on Artemis 2, which I'll talk about later. So the facility under construction, I can show you. I'm very excited. And you can see here how very little it rains sometimes in Australia, and sometimes it doesn't. So also quite interesting for me, because I'm actually German originally, is to see the amount of engineering complexity that goes into such a ground station in Australia, because it's literally just a concrete slab with a simple shed built around it. But obviously we don't know yet whether it works, because we haven't quite finished it yet. And currently we're waiting for the dome that so at the moment the building is open at the top, and there is like a tarp over the top to protect it from the weather, and we're waiting for the dome that's going to arrive next month, and then the telescope can go in, which is this telescope here on this side. It's a plane wave RC700 70 centimeter aperture. And the design is maximized for its throughput, so it has a very small secondary mirror and quite a large primary mirror. Also, by the way, I'm keeping this sort of slightly top level because I don't know which audience there is. So if you have any questions, feel free to reach out to me. My email address is on the bottom of each page. And if you have also questions for the other things that I mentioned, I can refer you to the people that do this stuff. So you guys might all be aware that there is the Artemis 2 mission, which was the crewed mission next year, which we're all very excited about. And it will actually have an optical terminal installed on it, which is the Optical to Orion mission. And we now have the funds to be able to provide basically a southern hemisphere site for additional coverage, so we can make sure that we can continue to send optical signals up and down for a longer period of time. And we are obviously trying to kind of develop the technology and have this facility as broad set up as possible, so we can also accommodate maybe deep space optical communication missions such as the Psyche missions or other optical communications missions in LEO or GEO that are coming up now more and more over the next years. So just still a little render, because nothing of this exists yet. There's our telescope in there, and we can obviously have an optical link between the spacecraft and the telescope. And here you can actually see the telescope. On the right side, we see the transmitter here with the 4 little telescopes. They are the transmit telescopes, and they're sitting like a piggyback on the back of the telescope. And we have an uplink laser beacon and also acquisition cameras that we can mount on the telescope. And when the laser light comes down back from the satellite, it gets caught by the bigger aperture of the telescope, because the signal is going to be weaker and needs therefore a bigger aperture. And it then gets led through the secondary and a tertiary that's here, tertiary mirror that is, into the azimuth port of the telescope, where there is the receiver which has a superconducting nanowire single photon detector installed in it. We are now in the preliminary design phase, or we've finished the preliminary design phase, and we're bringing up the project to the critical design review, and we will be ready for the launch in, I think it is September, October next year, when Artemis 2 is going to launch. Fingers crossed they are staying on time. And not only that, we obviously, with optical communications, you do have the issue that you are restricted to, blue skies. And if there's cloud coverage, then it's harder to obviously send a signal or receive a signal because the clouds block it. So we also looked at, in our group, at what the cloud coverage is actually like in our site. So we are down here, and as you can see in Canberra, the site is not super perfect with 63%, compared to Germany, way better, but still not as good as, for example, a station that could be situated in Alice Springs, which at the moment there is none. The 3 optical ground stations that are most advanced are in South Australia and in Perth, or near Perth. And we are now basically talking to each other, and also New Zealand, by the way, as well. We don't want to forget that we can increase the coverage if we add to New Zealand to that network. And we are all in discussions to actually basically have the same or similar capability and compatible capability. So we can then basically, any of the stations can be available for up or downlink signals to, basically once like one station is clouded or it's raining or whatever, then the other station can take over. And that's, of course, a huge advantage given the big country of Australia, as it literally never happens that all sites are clouded over. There will always be one site that will be available as well. So what's also important is that, we have the site here. And I guess the message that I wanted to bring across as well is that with the optical comp system, if you are interested in having signals, going to your systems optically, that we are open for collaboration once we have the station up and running by the end of the year. Now, if you're more of a radar person, we also have lots of other communication programs that we always focus on the optical side of things. And we had a project going that's now finished, which is the Compact Hybrid Optical RF User Segment, quite complicated name, short CHORUS. And it combined this radio dish that you can see here in the picture with an actual optical mirror of just under 0.5 meter. And it was really quite interesting. So to actually mount those 2 systems together, and you have to kind of find a trade-off, because obviously the signals, both signals, the RF signal and the optical signal, are coming in, and they have to go into an optical sensor and also a radio sensor, which was down here through the horn. And you have to find the trade-offs between both technologies, because the design of, for example, this secondary mirror here had to be, well, it wasn't really a mirror optically, but it was one. It was reflective for RF, but it had to be transparent for optical. So we had to find a good balance for the performance of both. And the idea is that you basically then have only one piece of infrastructure on the ground that you can also, this is particularly small, a small RF dish that you can actually then take potentially also on the road, basically, with like a military idea behind it. And you can deploy it in the field or on sea or wherever. And the idea was actually that we wanted to achieve the tracking with RF, which is basically really broader beam and usually not very suitable for the optical signal to rely on the pointing of the RF. But we actually managed to do that So the optical design is sort of as good enough to stay within that, provided the satellite doesn't move. So we're not quite there yet. So once we moved, we had a pseudo satellite. Once we moved the pseudo satellite, we lost the signal, unfortunately. But it was a very promising technology to combine both for specific applications that you want to do. And yeah, as a university, we obviously love doing partnerships. As you can see, we had a lot of partners in this program that was funded through the SmartSat CRC in Australia. So I don't actually know how much time I've got left, but this is the last slide. So I guess the key takeaways, I hope I got my message across that optical capability has got some advantages over RF, particularly because it's also more secure and can have a higher bandwidth. And we are building up this optical ground station infrastructure in Australia, and potentially we'll also have a network up and running soon. And Australia is really well suited to get view coverage from the Southern Hemisphere. And I just want to stress, I'm like super excited about optical technologies, but of course it will never, basically, it will just augment the RF system and will never basically get rid of it for sure, because you do have the coverage problem or the accessibility problem with the clouds. But yeah, it's an exciting topic, and if you guys need some optical communication interfaces on the ground, get in touch, and I'll be happy to talk to you. Thank you.
All right, thank you so much for your presentation. So now I'm just going to take a really quick break again, and then we'll be introducing our next speaker. Okay, I think I'll just, maybe it's easier if you just present from here. Okay, that's fine. I'll just present from here.
Yeah, it's fine.
Yeah, others can wait. All right, so we now have our next guest speaker who, yeah, so you can go ahead and introduce yourself before you go
Yeah,
into your
I have
presentation.
updated those things in slides.
All right, so I'm just going to
Let's
start.
jump in.
Yeah, let's just jump on in then.
Yeah.
Um, okay, so you can just kind
Maybe you can present.
of,
Good.
yeah.
Okay. So, hello everyone. Good morning. Uh, I'm Abhishek Bera, uh, and I'm like a research associate in University of Luxembourg, and there we have like research center which is called SNT, and I am a part of research group called Space Robotic Research Group like in short, it's Space R. So my background is like I am like experienced with like multi robot systems. Specifically, my PhD was on multi UAV networks, their cooperation, mission planning, and communication. Now I'm currently focusing on like planetary exploration part with multi robot system for their cooperation, communication, and mission planning too. So yeah, in short, like space are we have quite like two pillars now mostly. That is, one part is like dealing with planetary robotics, and another part is like orbital robotics. and also we have a few projects running still with the aerial robotics, and I'm also like kind of in charge of that partially as well. And now we this space R group actually like created by Professor Miguel Olivares Mendes in like 2020, and now we are like grabbed like more than 4 million as a fund for the different project we have. So we have currently like 23 plus like researcher, including like postdocs, research scientists and PhDs, and also 3 master students. They're like working hard towards like making the robots boogie. So and also like we have, yeah, some quite of expertise in autonomous navigation, control, then of course multi-robot system, which I'm actually working. Also like robotic manipulation and like machine learning for robotics as well. So before going into the like few of the projects or the topic I want to discuss here, let's discuss about the facilities we have like under the supervision of Space Robotic Research Group. So one is the interesting like facility we have. It's called Lunar Analog Facility. In short, we say it Luna Lab. So this is the kind of like approximately 80 square meter of area, which having like 20 ton of basalt, and also like 20 like sorry 12 like motion capture system to provide the ground truth for the robots. So and also 3 IP cameras, so where we can like record any kind of like mission wherever whenever we want. So what we do here actually like while coming to this event place, like in the morning, I didn't ask me why we created this lab. So the idea was especially for my professor, and also we are working with him a lot. The idea was that so if we like generally develop any kind of algorithm or any kind of like system, so we cannot like restrict ourselves in only in the simulation world. Also we want to test it those like algorithm and system in like real robots. So that's why, and for the real robots, if it is coming to the like lunar exploration or planetary exploration, so we need some kind of like similar like environment. So that's why it began, and this lab was created. But the difference is that like here we use like basalt in instead of having like regolith, because we are not actually as a group not developing any like robots. Like we use different kind of off-the-shelf robots. Here you can see in the left top, it's like we are using like Leo rover. Right side we have like Robotnik. So different kind of robots. Also like other day when like Irene visited our lab, we also tested the Hive system from Neurospace as well. So so we actually work with the optical fidelity of from the robot's point of view, and also like create the like navigation control algorithm and test them over there. Also this lab we have the some like artificial light, so that we can like create different like time of the lunar day, like create different kind of lightning conditions, shadows, and also we can create like crater for different kind of experiment we want. So that's why like it helps like the researcher a lot. So yeah, this is one facility we have, and also like we have another facility is called Zero Z lab. It's typically it's a kind of like to simulate the orbital scenario. Here you can see like one floating platform is there. So it's developed from the scratch from in our lab, and it actually floats on the surface because it has like air like bearings, and with the high pressure it flows, but in the bare eye we cannot see, but it is actually floating. So on top of it you can like anybody wants to test their small experiment, they can like mount their like system, and they can actually emulate a kind of semi or gravity like like 0 G condition and test their like experiment over there. And also for the orbital like servicing, we have this kind of like rail like robots, robotic arms, so that we can like test different kind of experiments like autonomous docking or asteroid mining. So it depends on the like what kind of experiment we want to do. And then this is also we are collaborated with autonomous research group. It's a aero lab, aerial robotics lab. I am also partly working, I mean, in charge of the aerial robotics part from like space R. So we conduct this different kind of like aerial robots here. But let's move on to the project. So we have different kind of like orbital aerial robotics project and planetary robot like exploration projects running. So today, based on the topic, I'm actually going to talk about a few of the like planetary robotics related like project we are running. So currently we have one of our PhD research scholar who is actually working on the like multi-sensor SLAM mechanism. So he is actually trying to like investigate how to use different kind of like optical or visual sensor, or maybe some kind of lidar as well. So and fuse the all the information, create the map in real time, and give it a like better input to different kind of SLAM algorithm. So this is his PhD topic, and currently he is like visiting NASA Ames Center with our professor Miguel like this Monday. And he is like a kind of co-supervision with the from NASA Ames Center as well. So it's a joint collaboration for his PhD thesis. Another like we have one of our research associate who is working with like different kind of machine learning algorithms, so detecting rocks or the pebbles, so that we can like move the robots like remotely very efficiently. So this is kind of work we are doing over here. Also, this is one of the key highlighted like point I wanted to share here, because I was a part of this ESA Strict Space Resource Challenge last two like it's happened started in 2000 like 21 and ended December 22. So we were one of the finalists of this event. So it was like it's a kind of they have created a lunar like environment where they have craters, they have like minerals spray, and also like different kind of rocks. So the robots needs to deploy from a starting position, but we had to like the team has to sit in the like another room or second floor, and there from there you have to control your rover, navigate the area, explore the area, create the map, like find the science, what are the science material is available. But the key point was it was having a 5 seconds delay. So if you are sending any like goal, the robots are receiving like the information or instruction after 5 seconds. So it was like quite a bit of challenge and also lesson learning for us. So this is kind of one robot we can see. This is we are like collaborated with space I mean SAS, one company, Space Application Services from Belgium, also Tohoku University, and also SpaceR was the in charge of the scouting robot part. So they have the bigger like robots, which is like having different kind of science extraction like sensors. So it can like see the material, analyze it, and say like what are kind of materials are there. And we actually as a SpaceR we used like 3 Leo robots. So these robots are mostly like scouting robots. So they move very fast and then create the map as much as possible. And if it gets any kind of interesting information, it sends back to the like big robot so that it can go to the point of interest and like dig into that. And for this challenge, we actually I was in charge of this to like create a kind of mesh kind of network, so each and every robots can communicate with each other in real time, so that they can exchange their information. And also it was connected to the lander, so any kind of like information it can like send it to the like control station via the lander easily. So one like key videos, real time videos we have here. I don't know now it's working, right? Or no? So yeah, here you can see from like these are the three window for three robots we had. So in real time they took this video. So it's like 8 times or 10 times faster, I guess, the video. So yeah, this was one of the challenge we had. So another thing like also we have internal project, it's called like 5G Space Lab, where we are combining like 5G edge computing and also this real ground robots for planetary exploration. Mainly we investigated how this like high speed like technology, also like edge like 5G, also the edge computer, which actually enhance the like more resource in terms of like processing. So in real time they can like process the real images and also like predict, and we can run a different kind of machine learning algorithm to detect whether there is a rock or it is having like getting stuck into the soil. So yeah, one of the research associate actually she published one iros paper last year. It was accepted over there. So if you anybody is interested more, then they can check our website and the paper is there. So move on to the little bit learning part. One of the PhD student is working currently on the grasping especially. So he is you can see here it is a simulated world. It learns with a lot of like training data set. Then actually we applied in the real robots and they are able to like grasp in the grasp the like this kind of rocks efficiently. So this kind of work he is also doing over here. And then we have another project where I'm kind of in charge of this, like as a mentor and like working with a PhD. So this is like suppose you have future exploration is multi industry like scenario. So you have multiple agencies, they can share the data, they can share the knowledge, but it also involves the money. So how this blockchain can efficiently manage this monetary part when the multiple agencies are involved. We are actually investigating on that, and we are actually implemented already. Last week we did a test with the real robots creating a map. Another robot is asking for a map, and how this map is connected with the bit I mean the blockchain, and real time it downloads when it requested with a specific price when it exchanges. So this kind of work actually also we are doing. So I think I'm almost running out of time. So this is the last interesting thing I wanted to share here. So this is a kind of like another PhD, master student was working with a postdoc, and now he is going to join as a PhD. So it is like creating a virtual 3D reconstruction in unknown extreme environment. So it's better to see this video. So here we deploy our robot in a lunar lab, what we showed earlier. And in a VR glass actually you are when it is travel, it is creating reconstructing the 3D arena. You can see little bit of rocks we have over there, and real time in the 3D glass you are actually visualize this thing. And also the user from the control station, with this gadget, you can also send the goal to the robots, and they can move and you can see 360-degree what is going on around. So this is really helpful one where in terms of telerobotics. So in real time you get different kind of information about the path the robot is going, also how much energy left for the robots. So yeah, he is actually working on this, and now this work is in a good shape so that we can do further improvement for this. So yeah, these are the few works, interesting works we have been doing now. So last very interesting announcement, we have seen so far the years specifically space robotics related dedicated conference and journals are actually not present nowadays. So as a space R, we are actually conducting a first international conference on space robotics next year in Luxembourg. It's a beautiful place. You can see this is called Groen. It is a view from the Europe's best balcony, we say. and it will be happening here next year. Like, save your date, it's 24 to 26 June, and it will be published with IEEE Explore, all the papers. So all the researcher, most invited, just submit your paper, or if you need any information, just go to this web page and you will get all the further information. So yeah, in summary, that's all from my side. Like, as a space robotic research group, we are doing this kind of a sort of space exploration in terms of robotics. And if you need any, if you think you have any interest in this topic that I already shared, you can connect with our professor Miguel, and also you can connect with me. It's abhishek.bera@uni.lu. So yep. So let's work together, and let's go to the moon someday. Perfect. Thank you.
Thank you so much for that. It was such a pleasure to hear about all the work that you're doing. Yeah, so again, we will just be moving into a very quick break as I introduce the next speaker.
Okay.
All right, I will now be introducing our next speaker, who is Dr. Michael Schluter. Yeah, feel free to just chime in and start with your presentation. Thank you so much.
Sure. Thank you very much for the invitation. Just want to share now my screen. Just a moment. Okay. So I hope you can see the presentation.
Yes, we can clearly see you.
Can you confirm, please?
Yes, we can see.
Okay, great. So I'm Michael Schlüter. So I'm founder and owner of the Astronis GmbH, which is based in Munich, Germany. Actually, nearby Munich is in Gilching. We are already more than 10 years now working on this field. And originally, I have been working at Airbus in the electronics department for space. I mean, radiation testing, all the qualification and procedures for electronics to be applied for space. And since 2013, beginning of 2013, we start with astrionics. Former was the Spectrum ERC, but at that time we start with support from DLR, from ESA, and also we have been supported financially by the EU, so what we call the Horizon 2020 program. And the idea was to start a systematic study how to qualify commercial parts for space applications. It's a kind of low-cost solution because normally you use special electronics for space. But since really new space has been launched, let me say SpaceX introduced this type of let me say industry, space industry, there was a lack in these terms. So that means small companies were willing to join to this market, were not available because of the cost. You have huge costs if you buy electronics for space, qualified electronics for space. And also there are some restrictions like military applications, and this makes the economics really bad. I mean, in terms of cost and in terms of timeline, so you cannot really compete under such conditions. Therefore, we start with this idea and say what we can do in order to really qualify codes and use them for space, a kind of a low cost qualification process. And we introduce what we call space codes. Space codes is what we call is the just normal commercial of the shelf electronics you use in your laptops, in your mobile phones, in the automotive industry, and we test them based on already existing standards for electronic devices in order to fulfill at least the minimum levels to be used in these space environments, in what we call Neurospace. Okay, and here just a quick view how we do this. So what is the process behind that? Actually, we have kind of matrix of different codes from different suppliers, so you can access them directly from the manufacturer or from some distributors, but having all the what we call traceability. So you need this information if the codes are coming from a same production line, a same lot, so that you can really have this information in order to proceed with the evaluation and testing. And this is the second part here, what we call the serious test. So mostly we're talking about radiation tests, because most of the codes we are selecting or pre-selecting are already for automotive applications. That means they have a wide temperature range of applications. Even they have some pre-tests, some screening by manufacturer, so that we can really use this information and go ahead and just do what we call radiation tests. So what means radiation tests? You might know this is mostly gamma rays, protons, electrons, heavy ions, and everything. And for this, we just take a representative part, let me say an average 1% of the batch, and we test them. And we do some analysis based on also some experience we have, some heritage, some data we have, and then we can say, okay, the parts are good for the application case, and we can, let me say, consider different quality levels for this. So parts which are being used just for a LEO orbit should pass a minimum level, and if you are applying this for a higher application case, like even in a geo case, for a short time you can use this, but you have to be aware that there are costs, and the test we are doing is a minimum test. And now the idea is, with the same philosophy, we would like to apply this process and extend it to a moon mission. So we already know the radiation environments for travel to the moon, and also to land then there, and also to survive for some years at the moon surface. So all this is also considered in this analysis now, so that we will extend it for a moon mission. So as I mentioned you, we have the Astronics has already heritage, almost now 10 years knowledge, and we already are testing at different facilities. We have exclusive database of radiation reports, and also we are working together with the vast community, so that we have some sharing with information application cases. Therefore, we reduce the number of test steps based on this experience we have. And we, at the moment, we are offering services using this proprietary global sourcing. I mean, we have a network of suppliers of commercial parts. We help also projects with the part selection and design, so how to apply the parts according to the application case. We perform the testing and qualification, all the documentation you need. Also, we have the possibility to do some upgrades in case you would like to extend your lifetime in a mission. We can do an extra test for this, and we have also traceability, what we call the labeling. So, in the main document based on this methodology is a ESA or ESCC standard, which was introduced 2013 when we started with the company, which is dealing with these commercial parts. So this has been updated during the years, and we are working with this standard, and it has different quality levels, and this is actually our reference, and we are always in touch and working together with DLR, the German Aerospace Agency, with the ESA, and also with industries like Airbus and TESAT, which are also interested on these application cases. And we are mostly considering cuts from automotive levels because, as I mentioned you before, we have already these high qualification levels, pre-levels, let me say, and high performance under harsh environments, let me say, temperature, humidity. Okay, humidity you don't need, but already also the shock testing and everything, vibration, which is also the typical case in the automotive industry. You already have this done at least at a certain level for automotive parts. So just a quick overview, that's kind of summary what we are doing. So we have already a database of radiation data for COTS. We have we're working together with several distributors, not only in the, let me say, commercial sector, also in the classical one, because some distributors or some, let me say, electronic suppliers for space are also thinking about this field, and they are introducing new space products, and we have contact with them, and then we also can afford, to these parts and offer to the community for a specific application. And since we have to do several tests, we have a big network, let me say, of facilities where we are doing these radiation tests around the world, mostly in Europe, but we have also some partners in the US and also in Asia. And we have support also with big companies like United Systems, which are developing several tests of electronic parts, not only for space application. Actually, they are doing this for just manufacturing of electronics. For big companies who are just qualifying the parts for the normal commercial application, and they are doing this qualification test. So, and we are working together with them. So we have the access to this test equipments, and they are our partners in this field. So what we can offer you is just the radiation tests, so the total ionizing dose tests, the single event tests. We also can find for you alternative parts. If you need them, we can search for you suitable parts. We can also manage the topic obsolescence, because this is in this field a very common issue. New technologies are coming, and you have to really to update your database and find some alternatives and try to do minor tests in order to be sure that the new technologies are still suitable for the application case. And we also manage all the procurement chain. So we offer you also good prices for tested parts. We implement this into your production lines, so that you can really have access to tested parts whenever you need. So this is the services more or less we are offering to you. So we offer you mostly cost parts from known distributors or manufacturers, and all the documentation you need for this. Even if you need this for ESA project or for a NASA project, we can offer you also the traceability, all the tests you need, all the screening tests you need for this application case. So, and as I mentioned, this is our network, most in Europe now. So for radiation facilities, I can just give you this link if you prefer to take a look what is there and what they are able to do. So mostly we work with in Germany with the Helmholtz-Zentrum in Berlin, or general in Germany, with RADEF in Finland, also with PSI and CERN in Switzerland. So those are the main facilities, and we have collaborations with them so that we can do the tests there. And we have slots every quarter of the year so that we can really jump to any test, and you just join to our plan activities, and we just manage this together, and then you have a quick result within 3 or 4 months. So this is the idea behind that, to be very quick with the qualification process. And in addition to this, we offer also some thermal vacuum testing, as I mentioned you, for CubeSats. We have some collaboration also with the DLR. So, and as I mentioned you, for all electronic testing, so we do this in our house, but we have also support from United Systems, which has also dedicated equipment for testing electronics at parametric level. So this is the idea behind that. So just a little bit about the Unitas. This is a company from the Czech Republic, which is also based in this field, and I mean in the space industry since beginning of 2000. So they are really they have a lot of experience also doing this field, let me say, space electronics. But as I mentioned you, they are also, or they are mainly focused on just electronics for just commercial applications. So, and this was just a quick overview about the Astronics, what we are doing, where we are. So you can find us in Gilching. This is nearby DLR in Oberhofen. So in here you find also my contact data. So you can just drop me an email or just call me if you have some questions, or if you need some support. I will be happy to really offer it to you. Okay. If you have questions, just let me know. Thank you very much for your time.
So, hello everyone. Can you hear me?
I can hear you.
Oh, perfect. I was late, unfortunately, because I had other duties to do. But it's going to be my turn to start a presentation. I'm just trying to find out if now you should be able to see my screen, right?
Yes, we're able to see your screen. Thank you.
Great. Okay, so my name is Sabine Klinkner. I'm professor for satellite technology at the University of Stuttgart, and it's my pleasure to give you some insight on the things we do in the field of robotic systems for space exploration. And I would like to start with my background. I worked for 12 years at the small and medium-sized company von Hörner und Sulger GmbH nearby Heidelberg, and worked a lot in the field of space robotics. In that time, the company itself started already working in this area in 1989. And starting with the micro rover nanocod, which is based on a formerly Russian concept. Then the company took it on for different mission scenarios for Mars, and then finally under ESA contract for the Bepi Colombo mission, as long as it had a lander. Since it was one of the very few companies in Europe working on space robotics at that time, we were also chosen to do a precursor mission for ExoMars together with partners, of course, which is, so maybe I can show you a bit also the videos. So you get an idea of the system. So the micro rover is on the top left. It's a 3.2 kilogram rover system, and it is able to carry 1 kilogram of payload. For the Solero, it is 10 kilo system, and as I said, a precursor to ExoMars, and is also able to carry the 1 kilogram. So there you already see some difference in between the systems. For the Solero system, it was basically the idea to focus on a flexible chassis system which can adapt to the surface. And continuing that road, the company was also prime or rover lead when we started the ExoMars project, working in the phase A study. After that, we were lead for the rover chassis, preparing also the ExoMars breadboard, which is named Bridget, which we built for Astrium UK. And further on, we also developed a second. I can't start the videos anymore. Sorry. A second breadboard in the phase B1, and we're working on the flight hardware chassis electronics. So there was already a lot of involvement in robotic systems in these years. I wasn't involved since 1989, but started in 2002 throughout to 2015, and I was very excited to work in that field. So when I took over the professorship here in Stuttgart, I was happy to take on a topic in my chair, because I do think, a rover system isn't anything else but a satellite, despite it has wheels and is driving on a surface. So the attitude control system is slightly different, otherwise it needs the same systems. And so what we first of all did is that we continued working on that micro rover system, also together with the company von Hörner und Sulger, but focusing on a lunar mission. So as I said, it has a high payload to system mass ratio that is resulting from that it is a tethered solution, so it is able to use synergies towards a lander or a cooperating rover system. Of course, this is limiting the reach of the system, but I consider the nanocod itself rather a robotic arm with a reach of 50 to 100 meters. So it has a system mass of 3 kilograms that is comparable to a robotic arm, but the reach is up to 100 meters, so it can really move away from contaminated area around a lander. So it is very interesting. Furthermore, by using the synergies with lander, it is also able to remove critical system or put it on the lander, such as batteries. So it is a very robust system. Communication and energy supply is from the lander, so we have no thermal extremes which we need to take care of within the rover, so that we can have a system which is suited for extreme conditions which are of specific scientific relevance, such as craters and sky holes. And furthermore, with such a small system, it also enables easily a swarm application, because you can think of having multiple systems exploring a, a region, and maybe also using different sensor systems, applying them in the field. So that is very exciting. We're working here on different aspects, like how to make it robust, how to make it as small as possible, but also how to have a recoil mechanism which allows you to enhance the reach even further. But another big issue is also dust mitigation. If you have such small systems, but any system on the lunar surface, dust mitigation will be a big issue. And so we're working a lot in this field currently. But we also do have larger systems and work on robotic components for larger systems. We built a modular rover chassis platform where we try to find out the best parameter for a chassis concept. Since we were working on the ExoMars chassis for a long time, I know that there is a lot of effects you get from the different suspension parameters, and it is also very difficult to get these from simulations only, and thus we build up this very flexible, reconfigurable chassis, which allows you to measure parameters and then compare it also to simulation. Furthermore, it is a perfect testing platform for other robotic items, such as robotic arms and deployable masks, which we are working on, and also for different sensor packages we are developing here. So these are all different aspects where we work on from research side, but what I think is also very, very important is to always combine it with education. So we have a strong cross-link between our research projects and education. So what you see here is all the mission patches which have been designed from our students in several studies, but also some of the hardware development, which you have seen on the slide beforehand. So this would be my very short overview on the activities which we do here at the University of Stuttgart. And if there are any questions, I'm very happy to answer.
All right, thank you so much for that presentation. Sorry, I think I might have been muted before, but I just want to thank, regardless of the last two speakers, for those really insightful presentations. And yeah, so if there's any questions from anyone who's currently watching, feel free to just chime in now. If not, then we'll be taking a short break until our next speaker that is scheduled in around 10 minutes, who will be Dr. Stefan Bartholmes. So until then, short break.
All right, thank you.
Thank you.
Hi, can you hear me?
Hi, yeah.
Perfect.
Yeah, so we can, so sorry, I think I was again muted before, but yeah, we can go ahead and yeah, get started with you if you want to.
Can you hear me?
Yes.
Hi, yeah. Perfect. Yeah, so we can, so sorry, I think I was again muted before, but yeah, we can go ahead and yeah, get started.
Sorry, just some, sorry, it was a playback on
Some
our
noise in the
end.
background.
Apologies. Anyways,
No,
yeah,
no worries.
go ahead,
I
give a brief introduction on yourself, and then yeah, you can just go ahead and get started with the presentation. Thank you so much.
Sure. I'm not sure if you can see my camera. It looks black.
We are not able to see you, no, just a blank screen. Oh, yeah, perfect. Now we can see you clearly.
But we can't hear you.
Yeah.
There is a setting with the microphone where you have an arrow, and there you can switch on the right microphone. But you were here already, so we could hear you. Yes.
Does it work now?
Yes.
Yeah, perfect. Thank you.
Okay. Camera picture was not so important, but I thought maybe quicker.
Okay.
Sorry.
You have the floor. You can go ahead and get started.
Okay, perfect. Yeah, so I'm gonna quickly introduce myself. My name is Stefan. I'm working for the German Aerospace Center, more specifically the Institute for System Dynamics and Control. And I've been working there for the last almost 10 years by now, and mainly in the fields of rover simulation, dynamic simulation, and rover controls, which was also my PhD topic. Yeah, so thanks first of all for inviting me to this International Moon Day celebration today. I'm glad to give you some insights into roving in milligravity. Now, I guess some of you will probably know already by the title what this will be about. It's about the Martian moon exploration. That is a Japanese space mission, which is scheduled to launch next year. And the mission goes to, as the name suggests, to the Martian moons, Phobos and Deimos. The bigger one of the two is Phobos. And I brought some quick facts just to give an impression of what we're talking about. Phobos has a diameter of about 20 kilometers. Can you still hear me well? Because my computer is kind of lagging today.
No problem. We are here.
Okay, perfect. And the gravity of Phobos is very low. It is about the factor 1 by 2,000 of the Earth's gravity. So that's, of course, always hard to imagine. Our rover is about the size of a drink keg, and it weighs 25 kilograms. But on Phobos, it's gonna weigh as much as a little grape. And some other facts, basically, when you start driving about 30 or 40 kilometers an hour, you would reach the escape velocity of Phobos and fly back into open space. So, of course, orders of magnitude below that velocity, the rover would already start to be jumping around like on a bumpy racetrack. So that is quite challenging and also quite counterintuitive, because the inertia of the rover doesn't scale in the same way. We also have quite challenging temperature range of about minus 150 C up to plus 70 C on the surface within this day-night cycle of seven hours. And last but not least, we do not know a lot about the surface properties. Now you might say, well, there are nice pictures of missions, different missions that passed by Phobos, and of course there are, but the scale or the resolution is not what we would need for rover driving. So basically, the best images have a resolution where 1 pixel is about is larger than the whole rover. So basically, there can be quite some challenging stuff hidden in the resolution of the current images that we have. So talking about the rover itself, it's recently been named Idefix, and it will be dropped from 50 meters height. It has several functions. I will show you that in the video. That's a bit easier. And we also have different scientific instruments like a thermal camera and a Raman spectrometer. We also have wheel cameras, which will film the movement of the wheel and the interaction with the soil, as well as stereo cameras and for the navigation. And one very important aspect for JAXA is also the acceleration during impact, because JAXA wants to land on the surface of Phobos with their large and expensive lander, and they want to take a soil sample to bring it back to Earth. And of course, they are very interested to know more about the surface geometry, but also the regolith behavior that we find and they will find on Phobos. So now I hope that you get the sound of the video as well.
Sorry, we can't hear it.
No sound of the video?
No, unfortunately not.
Okay, no issue. Then I will mute it on my side as well and explain you a little bit. It's basically a... No, it hangs again. Sorry, it's my laptop is terribly slow today. Okay. One second. Here we go. So that's a little trailer of our Idefix rover, and what you see here are scenes of the flight model and also prototype driving here in our test bed, and some impressions of how the mission will be looking like. This here is in an AIT facility at DLR in Bremen at another institute, where basically the outer part of the rover was integrated. That was the interface, and here you see the clean room at CNES in Toulouse at the Centre National d'Études Spatiales. And there the final integration was done and electrical testing. You also see now movements of the locomotion subsystem and basically some final tests. Here's a simulation video that I will show you in more detail in a second. That's a deployment of the solar array. Here's some testing in the EMC facility at our partner in France. And here's some testing in our test bed, where we drive a prototype rover up a sandy slope in a special locomotion mode called inching locomotion. That was some recent test that we did. Okay, to give you a bit more insight into what the movements of the rover on Phobos will look like, I want to show you this simulation video here. So basically, as I said, the rover will drop onto the surface from a height of about 50 meters. Of course, just like a dice, it will land or settle on any of its faces. And then after that, the locomotion subsystem consisting of these legs and wheels, it will start uprighting the rover. That's how we call that process here. And basically, there is a special sequence that was developed by our French partners to upright the rover from any of its faces. Then it will stand up like this and finally deploy its solar arrays. And then it can, well, kind of breathe, in that case, meaning recharge its batteries. It will open its shutter windows that protect the cameras from the dust of the impact. Now there's some shutter on the belly, which opens, that is barely seeable here. And now to maximize the recharging after that very exhausting uprighting maneuver, the rover can align itself towards the sun to get a better angle of the sun on its solar arrays. Then it will wait a bit to recharge its batteries, and once that is done, it will stand up, go to driving position, and perform its very first drives on Phobos. These will be the first driving maneuvers of wheeled systems in milligravity. So basically, yeah, since it's a world first, we don't know much about how exactly the soil will behave. Of course, you see here in our simulation that we perform in our group here, there is some soil deformation, and you can imagine that we not only performed the simulation with these properties, soil properties, but also with all kinds of different other soil properties to kind of get a range, because remember, as I said, it's very uncertain how it will look like in the end. Here you see the field of view of the thermal camera, the mini-RAD instrument. It measures a day-night cycle to get some,
this video is presented to
some soil and material properties. There will be, after that, some drives. At this point, we will have performed already short drive periods and what we call the checkout, and we will have parameterized our locomotion software for the soil and the environment that we will then have found during these first checkouts. Once that checkout is done, we can also drive a little bit faster. Little fast in that case means up to a maximum of 1 millimeter per second velocity. So all these videos that you see here are accelerated to make it a little less boring. Here now, the Raman spectrometer is going to be measuring, here you see the green laser of the instrument, into the soil. For that, the rover moved down because it needs to bring the instrument into the focal area. This measurement is going to be done at night, and on the next day, the rover can again stand up and perform further things. Okay, so you've seen the nice video of the simulation, but what's behind all that? Basically, with the simulation, we started to get in the project quite early. And as I mentioned in the introduction, that we've been developing for almost 10 years now rover simulation, and MMX rover mission is the first mission where we employ the simulation throughout all mission phases. And what are we doing throughout the different mission phases with the simulation? That's what I want to show you here on that slide. So one of the very first questions was, can a rover drive at all in milligravity? And of course, that's a quite important question if you want to start a rover mission in milligravity. So you see here a video which is still labeled for internal use only, because in the beginning we didn't want this not so nice box rover to be published. But this was one of the first simulations that we did to basically assess the question of, can a rover drive in milligravity, and then in the next step, how fast can we go? Going further in the mission phases, there were other questions for the design, like how much motor torque do we need, or also for other subsystems like the solar arrays, what are the dynamic limits for opening? You can imagine with a very low gravity, if we flip open the solar arrays too fast, then the whole rover might jump or even flip over. There were other questions like the stiffness of the shutters. That's a similar story. If that is too stiff, the rover could jump meters high into the, well, I wanted to say air, but of course there's no atmosphere. So from the soil, from the ground. And also we assessed if we would need an additional uprighting mechanism or if the locomotion itself is sufficient. By now, the simulator is also used for verification purposes, and it is even integrated at CNES in a hardware in the loop test bench where the main software of the rover is tested and verified. And last but certainly not least, there's going to be the exciting part of the operations of the rover on Phobos. And we're already in the midst of preparing our simulator to also be used in this period, basically by the mobility group of the mission. And questions there will, of course, be, once the rover is there and we have images, which path would be safe to drive? Which path is efficient? How can we go to this particular rock, which the scientists are interested in? Questions like that will be answered with the help of our simulation. Now I want to make a little jump to the locomotion subsystem, which is developed jointly at my institute and the sister Institute of Robotics and Mechatronics here in the same campus of DLR. The locomotion subsystem is basically the system that provides all the uprighting, alignment, and driving capabilities of the rover. Most prominently here, you see the wheels. These are optimized for loose soil. You can see the large pedals here. So basically, we want to be sure that even in very loose sand, very fluffy material, we want to be able to drive. But there is, of course, a lot more to it. Basically, we have tiny legs with even tinier drive shafts inside the legs. This is because all the electronics and all the motors are located inside the rover chassis. And then through a little drive shaft in the leg, the wheel is actually turned. And then there's other things that are even less visible. Inside the rover, inside the inner compartment of the rover, we have an electronic box. There we have all the power electronics, but also an FPGA with the firmware. And of course, we also have software for the kinematic controls, but also failure detection, isolation, recovery functions, monitoring functions, and so on. That's the local partition, which is written in C and running on the main OBC of the rover. Well, what do we need to do before we can actually be launched to Phobos? There was an extensive qualification and acceptance campaign. I won't go into the details here, but I want to give you a few numbers. We had 4 overlapping test tracks over the course of about 6 months in 9 different test facilities. And we were about 150 days in labs, and everybody who has done testing before knows that there's a lot more days in preparation and post-processing. About 20 engineers were involved in that qualification campaign, and it was successfully finished in summer last year. And the system basically was accepted to be integrated onto the rover. Here's a short video of the thermal cycling test campaign. I'm just going to jump a bit here because it seems to be lagging a lot anyway. So here you see the wheels and legs and integrated in the thermal chamber with over 3 kilometers of test cables. So that's what you see here. And yep, and here is one final test. Some images of that. We threw a big metal ball onto the poor wheel here. Good news, it survived. It was not the only impact test that we did, of course. There were other impact situations. We threw a lot of dust onto the wheel and tested if the hold down and release mechanism would still release and if the wheel and leg would still turn after the impact and after this dust. Okay, that's it from my side, from roving in milligravity. I hope that I could give you some interesting insights, although the videos I think didn't run through very smoothly. I hope that you still saw some nice still images maybe. Thanks for the attention, and I'm happy to answer your questions.
Thank you so much for that presentation. Yeah, once again, if anyone has any questions, you can just chime in now. If not, we'll move on to our next discussion series. So, All right. In that case, I'm assuming that there's no questions. So
Maybe currently.
yes.
So I will just go on now because we also decided to have a short discussion as long as we have you as a participant here, and maybe you would like to discuss some further things. And so I will start with some of these things we were facing. So as a new space company, we of course have to focus on business of rovers and business of the whole moon market. And it was very hard to face all these things because moon technology is extremely expensive, as we have figured out. So, especially, for example, Stefan Barthelmes, your rover, of course, is not comparable to what we do. Of course, it starts from technology, software, and so on, due to the time you had, the money, and so on. So, what is your opinion about these new space technology also now getting into the moon market?
Very, very good question. I find it very exciting because for a long time, the space in general was so agency driven. So of course, it's always hard to get started because things are expensive. But on the other hand, there are quite some developments, especially also in the electronics area, where cheaper components off the shelves are used for space, and actually even for our rover, there are components off the shelf. Hardly, it's not all radiation hardened and space components. So I think there are developments that kind of play well with the needs of new space startups. And I mean, there are very prominent examples that it seems to be working well. And I think it's gonna be exciting times to work together and to kind of merge the capabilities of agencies together with like the dynamics and agility of startups.
So, okay, I have a question from Sabine Klinker. So, Professor Klinker.
Yeah, I was just going to join from that. I mean, this is exactly what we're working on here at the university as well, that how to use the components of the shelf reliably. So there are different methods how to apply them securely by software methods, by shielding and so on. So I think it's going to be a strong driver. And as I mentioned beforehand, I was working for a long time in a space company and working on scientific instrumentation. And there we often used components off the shelf because just for going to the moon, there are no qualified components. It is really tough to find things which are really qualified for the whole range which is required on a lunar surface. So I think it's always been there, and since working not on the system but on a payload, it was also easier to go towards components off the shelf. But yeah, I think technology is developing, so it's going to be easier to go for these components, and of course more affordable.
I think here's also Dr. Michael Schlüter from Astronautics, because I hope you are listening. So this is your field, qualifying components. And what is the bigger challenge of qualifying components for the moon here then? Do you think it's reasonable also our approach, taking COTS component and qualify the final system?
Sure. This is actually, as I said in my presentation, the next step, let me say, it's a question of, for electronics, it's a question of radiation, right? And the most issue there is actually, okay, to see how we can, I mean, we have to calculate the radiation levels for the given mission and try to find out the safety margins. I mean, just to know how long should work the system under such conditions. This can be also done in the lab. I mean, just for example, for total ionizing dose. We know the levels also for a moon stay during the different periods. Let me say also the sun activity should be also considered for this, because it's the travel there without any protection. I mean, you are leaving the Earth magnetic field, and then you have also heavy ions. All this issue should be taken into account. Our experience now is more in a LEO application for Neurospace, for small satellites, for, let me say, up to 7 years application. So we know already this, we have a lot of heritage. We don't go for really deep tests like ESA or NASA are doing. I mean, because this is a question of cost, you know, and also not all costs will survive the test. So you have really to deal with these effects, what we call radiation effects. And there is, as already said, Sabine already said this, you have possibilities to really handle those effects, mitigate those effects by software, by hardware. I mean, you have some filtering, you have already some ledge-up protection systems, and all this can be done by using also COTS. This is possible because from our library, we know there are some parts which are actually COTS parts, which are suitable for space environments. They are not really the high REL or red hat parts. Let me say, you cannot compare it to those parts. But you know, under such derating levels, so you don't really power, for example, a MOSFET to the maximum values according to the spec. You go below this, and you know, by driving the pass in that way, you will be in a safety and operation area, what we call this. So this is the way how we will do this also for moon applications and even beyond, because you have this radiation everywhere. And radiation, I mean, if you know the models, or you know the environment, you can really simulate this perfectly in a tool first, and then do the corresponding testing in a lab. So this is feasible, and even before really these moon missions, actually NASA starts already with COTS parts in the 60s. I mean, because hydrogen parts came after this. So therefore, this is a common case, and also COTS are used. I mean. The benefit of using COTS is the technology you have. The COTS technologies is very forward. I mean, you have improvements every 2 years. You have very efficient devices, very integrated systems. So you can also work with these advantages and say, okay, I can also do many of them, like backups. Like you have many systems running in parallel, and if one of them fails, you have another system which can take over this. This is the idea also, to make redundancies. And in terms of cost, if you use COTS, you can reduce the cost, you reduce the test, so you can, in overall, you can really have a good product by using COTS. This is the idea.
So I'm just taking the opportunity as long as people are here. So I also see that Manish Verma, you are also here. So maybe what is your experience here with your rover development and in these fields? I hope you are hearing us too, or you're listening. But as we have figured out, it's always something challenging to find the right components, and as you said, the impact of radiation. So I would like to hear some other opinions in case. So if someone else would like to say something, I would be open. So in case if not, I would just like to say from our experience was that we now go the approach by testing system-wise, as it's been done for CubeSat as well. So of course we select some of the parts which are critical, and we already did some radiation testing with Dr. Schlüter. And so these parts we pick out, and the rest will remain as COTS part, and at the end we will test it as a whole system. Because of course we need to have these differences of saving times. Our system is being used in a different way, of course, and it's not like we want to have this long-term vision of, and even though this is one of the goals we are going to, but up to now, like reaching the moon, surviving the day, I think for these things, it's not necessary to go through these huge cycle testing and components which have to be that reliable. So I think it is okay to select components which are critical with this approach, but also it's important to select components and all these things based on the mission. So this is something which is also used for the Neurospace technology, and that's why for us it's always interesting to discuss these things with others. So one other question is, of course, what is now upcoming, for example, also what we do with our rovers is swarm technology. So what we always say is, instead of using these big rovers and with so many different tools and settings which are very critical then, and you can only perform one one measurement, one experiment at one time at one place. It's better to have a swarm technology which can spread out and do missions at the same time on different places. And I think that this is also something where the future of space exploration is going on, and as we have now experience with the development of AI, that swarm technology is now getting more popular, and it will definitely be capable of performing these things. But what is your opinion about this here? Because up to now, this was not done. Yes.
Yeah. So I can maybe. Sorry. Should I start? Sabine, you wanted to? You raised your hand.
Go ahead. Yeah, no, go ahead.
Okay. Yeah, that also goes in the direction of the question that I also brought up to your colleague Irene. That basically, what's going to happen with rovers in the future, and in the future where we have maybe permanent bases or even the moon village with astronauts, because so far rovers were there to basically extend the range for scientific instruments. And once astronauts are there, they could carry the instrument to the rock where it needs to be. So, what's the future for rovers looking like? That is a question that we are currently also concerned with. And in terms of the swarm aspect that you mentioned, I think can certainly be one aspect to that. What I also think is basically the velocity might be a point, because current rovers driving in the range of, I mean, not necessarily the 1 millimeter per second as on Phobos, but that has different reasons. But if we're talking moon, we're also going just in the range of centimeters per second usually. So and basically, if the astronaut is faster than the rover, and the astronaut has a working day cycle and so on. So basically, the rover can't just drive for hours if it wants to be of help, and if it should like work together with the astronaut, for example. So I think that the dynamics, and specifically the speed of the vehicles, might also be one aspect that we will encounter in the future.
Okay.
Maybe are there opinions on that?
Yes, this is a very interesting aspect, because that's true. We also that why now speed up our rovers. They are quite capable of we are running quite fast. But yeah, I would also like to hear, Professor Klinker.
Yeah, thank you. Well, as I mentioned in my talk, we're working on that topic, swarm application, because I think it is very important. I mean, we see that in the satellite technology as well, that it's rather going towards smaller satellites, having a dedicated focus. And I think this is done because it reduces the complexity of the single system and allows to have a faster development and apply newer technologies. So I think this is, of course, also very interesting for rover systems. And as I mentioned before, and it's also very interesting, this is referring also to that speed topic, that if you have a rover system which is basically following one track and doing measurement on that one track, it will just give you little data on very specific field. And if you're able to implement swarms, you can really analyze a whole region and get much more information. And there you can focus on specific sensor system added to these rover swarms. For the speed topic, we're having that discussion always with our students because they always like them to be much faster than they are. But yeah, I do think it's still a control issue. But you're the expert. I mean, it is always a lot of the speed issue is to analyze the data, do data fusion of all the sensors before you then drive. And I think that needs to speed up first, and cannot be made by just motor and torque adding that
Yeah.
or increasing that, but definitely it's an issue. However, if you're driving much faster, you will have to deal with dust issues a lot and have to take care of that. But yeah, it's an interesting research topic we're working on, so it's definitely worth thinking about that more.
Yeah. So it's absolutely the same we experience. So driving faster is not the problem, especially on Earth. So people knows all these remote controlling cars here on Earth, where things just react different than on Moon, and then you have this latency and all these problems, and that's the reason why things are running slower. That's true. What I can also consider is for the astronauts that they are there live on that moon surface, and they can control the rover more directly, so they don't have to face this latency. Then things might look different then from that aspect, just as
And still, of course, from the perspective of the dynamics, that's more our topic than.
Yeah.
I mean, the current rovers just have passive suspension and kind of rigid wheels mostly. I mean, some flexibility, but not made for fast driving and suspension. So this is definitely something that we would need to look into. Apart from, well, it's basically two different control topics or levels of control, right? One is more be it autonomy or teleoperation, and then below that you wanna compute what do the actuators need to do in order to realize to allow for that movement that is commanded by astronaut or autonomy, and this layer below is basically our main focus here. And there, basically, I think there's going to be some interesting stuff where we also can learn from our automotive department at the institute and bring in their experience with active or semi-active suspension systems or passive suspension systems, which still use springs and dampers. And of course, there are a lot of challenges, as you mentioned, Professor Klinkner, with the dust once you have moving components. So yeah, but I think that's going to be interesting topic for all areas. So yeah, that's why I brought it up. and wanted to know your opinion on this issue or potential future topic for roving.
Yes. So currently, so maybe we can play this in. We have another stream running, which costed us some interfering. That's why we had to change the YouTube channel and reset it. But currently, we have this Moon Day running today, and there we have students from all over the world. This is arranged by the Moon Village Association, who are currently running our rovers. We have two of them here at the Lunar Yard test field. This is called #the Moon. It's in Rostock Lager and done by the spaceport Rostock. So yeah, and here students from all over the world have the chance now to drive our rovers at this test field. I think here you can see them. This is live currently. So we have two rovers, and they are both controlled. So there are students group from Australia, India, Indonesia, from America, and so on. And they get a login. There are some QR codes set in here, so I'm not sure whether you can see it. I'll try to make it bigger. No. So never mind. So there are these rovers, number one and number two. We have placed some QR codes. We gave them some kinds of challenge. And this is the Lunar Yard, which is really comes very close to the moon dust, which is very great. Our first time we tried it here was very tricky. Our rover were very slow, but meanwhile they can manage everything. They don't have these stacking problems, and they are steering very well, I think. So we did not have any issue up to now. And they are running the whole since the whole morning now, both of them. And so yes, you can see. We actually, I don't know who is controlling it currently. Maybe we can look up. But so this was also one of the things which was interesting for us, that people with this experiment now get more insight how a lunar mission might look like and how critical it is, and making decisions based on what you get as an image. And the camera is set directly at the rover, at the top of the rover, so they have to make their decisions by all these information they get back from the rover, and then try to steer it. So this should bring back or like show the students how these missions are, and that they understand why rovers are running slowly, the impact of this dust, and that it's not that easy. So I think these things are very interesting, and I think also it would be great if we have more of these experiments running in Germany, also for the understanding of these lunar missions, and that's why we are taking part. Maybe you like to comment on this. What does it? Yeah, I would be very curious. So if anyone would like to comment something, just go ahead. Straight. So yeah, this is a live stream, by the way.
I would be curious if you have already some feedback from students driving.
Actually, yes, but I was even called down because actually, I think it's going really well. And the feedback up to now, we didn't have any complaints, so everything runs good, I would say. And so I think it's a huge experience. So we also had some kids running around here, so they were also allowed to drive it, and they all loved it so far.
But that's what I mean.
Yeah.
What's their, how come they want to drive it? What's their motivation? And do they, is it, scientific interest on the lunar surface, or is it driving a car?
So actually, they are very amazed and enthusiastic about space, and for them, driving a rover is very exciting, of course, and they all want to do. And after this, when we ask them, "How do you feel?" So you can see some of these kids there, and they just love it. they all said it was just amazing, and one just said it made my day. And it was just a huge experience. And I think it's even more fun if you just participate here and yes, just performing some of these tasks which we have set up for the students. I think it has this real moon mission feeling then.
Great.
So I think.
What was the? Yeah.
Please go ahead.
I was wondering what the main challenges might have been. I mean, you said it's not. They saw that it's not so easy to drive a rover and that it needs to go slow. What do you find as the main challenge when people that maybe do it for the first time operate these rovers and even through remote control from somewhere?
So we had also done a lot of how to say on several universities presentations. We took the rovers there and they were able to drive it through our highway system. So it is especially the latency. We have also some virtual latency programmed inside our highway system so that they can experience this as well, and to understand that they were now pushing something. The rover was already doing it, but the feedback they get back is even later. So to understand it and then to realize how to steer it the best way, this took a while sometimes. But then after they figured out, it just was fun. And more fun was when we gave them some tasks. Like, okay, you have to find an object. It should be somewhere far west or something, and then they should try to find their way to that object. And or here we have the QR codes, and here they have to even solve some challenges, like they have to scan the QR code. There is sometimes a video behind it. They have to say and solve some questions and so on. So this is like a challenge then, and then only if they do it, they can go to the next task and so on.
Okay, thanks. Cool.
Yeah, so we already reached our lunch time meanwhile, so I would very much thank you for participating for this and presenting. This was amazing that you had time. We have arranged it in a short amount of time because we had the possibility to do it here at Spaceport in Rostock. And we are very grateful to be here and thank you for your time. So we will have a short break and we'll go on in an hour at 1 p.m. CET. I have to mention it because there are people from all over the world. Unfortunately, yes, we have the new link. But the next presenter, it's very interesting. It is Dr. Markus Schladebach. He is doing space law. And this is, I think, also extremely challenging. Listening to him is just really entertaining because he has so much information to present and things we as an engineer hardly would think of. And the law behind it's so necessary to somehow follow up here. And during the break, we will play our new latest video from our rover. We did a little movie with our first rover where it got somehow lost in a subway station in Berlin and it finds its way back to our office. So it's really lovely and I would appreciate if you would watch it. So we would just play it. And once more, thank you very much.
Thanks to you. Bye-bye.
Thanks for having us. Bye.
Thank you.
Bye bye.
Bye.
Should I put
Yeah,
it just on the stream?
On Jitsi through the screen.
Okay, yeah. Fine.
This video is presented to you by Neurospace, a company which is building the next generation of moon rovers and wants to take the opportunity. This video is presented to you by Neurospace, a company which is building the next generation of moon rovers and wants to take the opportunity to look back into the history of previous Moon and Mars rovers. It is a story full of pioneering spirit, exploration and engineering miracles. Welcome to the video series, The History of Extraterrestrial Rovers. In the last episode we talked about the first two unmanned rovers, the moon rovers Lunokhod 1 in 1970 and Lunokhod 2 in 1973. Actually, there were 3 more moon rovers between July 1971 and December 1972, the Lunar Roving Vehicles by NASA, but they were manned and driven by astronauts during the Apollo missions 15, 16 and 17, as they are very special. The only manned rovers so far. We will cover them in an own special episode. So how did the history of unmanned rovers continue? The logical thought would be that the space agencies continued exploring the moon, as it is the closest celestial body and thus perfect for testing and improving the performances of extraterrestrial rovers in general. But this is far from the truth. In fact, no space agency was interested in the exploration of the moon's surface with rovers until China landed its Yutu-1 rover on the moon in 2013. The focus was on Mars, although it is a lot harder to get and land there.
You have to keep in mind that the moon and the Mars are actually a little different from each other. But that has a significant impact on the rover design. For example, there is a different length of days and nights, which results in a different temperature range. And the rover weighs twice as much on the Mars as on the moon. Or, for example, the moon completely lacks an atmosphere.
Especially the Soviet Union had many failures in trying to land on Mars. Only one probe made a soft touchdown on the surface, the first ever on Mars, but it only survived for 110 seconds.
Please change here for BER Airport. Ausstieg links. Nach Westkreuz.
sky will look upon the morning fall, and the mountains you crumble to the sea. I won't cry, I won't cry, no, I won't shed a tear, just as long as you stand by me.
Ah, da bist du ja. Wo warst du denn? Oh, hallo. Oh, du schaust so aus. Oh nein. Ein bisschen Staub abputzen. Ja.
Please change here for BER Airport.
Ausstieg links. Nach Westkreuz. S5. Zurückbleiben bitte. Nach Westkreuz.
Wo warst du denn? Hallo. Oh, du schaust so aus. Oh nein. Ein bisschen Staub abputzen. Ja.
stand by me. Stand by me. Whenever you're in trouble, stand by me. Oh, stand. In the sky, we look upon the mother and the mountains. You rumble to the sea. I won't cry, I won't cry, 'cause I won't shed a tear. Just as long as you stand by me.
Da bist du ja. Wo warst du denn? Hallo. Oh, wie schaust du aus? Oh nein. Ein bisschen Staub abputzen. Ja.
Please change here for BER Airport.
Ausstieg links. Nach Westkreuz. S5. Zurückbleiben bitte. Nach Westkreuz. Just as long as you stand by me.
Da bist du ja. Wo warst du denn? Hallo. Oh, du schaust so aus. Oh nein. Ein bisschen Staub abputzen. Ja. so aus. Oh nein. Ein bisschen Staub abputzen. Ja.
Please change here for BER Airport.
Ausstieg links. Nach Westkreuz. S5. Zurückbleiben bitte. Nach Westkreuz.
All right, hello. Okay, so we can get started with your presentation. So yeah, feel free to just start sharing your screen and you can introduce yourself.
Mhm.
Great,
You
thanks.
can hear me and
Yeah.
see me?
Yes.
Yes?
Yeah.
Okay. Yeah, hi everybody. My name is Markus Schladebach. I'm a professor of air and space law in the University of Potsdam. And thank you for the possibility to speak about a topic which is one of the hottest issues in space law in recent times, the legality of moon mining. In times of shrinking resources on the Earth, with a more recent view, in times of international conflicts concerning natural resources, mankind has to care about the fundamental question how the increasing need of natural resources can be managed. As we probably all know, one way is the special technique of deep sea mining. Since a couple of years, a number of states, also Germany, has put their claims of exploration fields in a Pacific area between Hawaii and Mexico, the Clarion-Clipperton Zone. That the mining on the ground of the ocean, the deep sea, is not very comfortable for the ecosystem of the deep sea is more than obvious. A second way for the state community is the idea of moon mining. There are a lot of serious initiatives to bring technical equipment to the moon and explore and exploit natural resources on the surface of the moon. Especially for the United States of America, is the new moon program not only a simple return to the moon to remember the moon landing between 1969 and 1972. No, there are hard commercial interests of the so-called Artemis program of 2020. From my profession, the legal perspective, it is essential to analyze whether moon mining is a legal measure in public international law or it is not. Maybe we find as a substantial answer in the Moon Treaty of 1979. It is an international convention as a reaction to the moon landings, which have clearly shown that exploring and using the moon became possible. So the United Nations has drafted this treaty, the Moon Treaty, and tried to find a difficult but necessary balance, stating that the moon belongs to every state and that's why common heritage of mankind on one side, and provide some incentives for the mining state to invest lots of money, capacities, infrastructure, and human resources on the other side. In legal wording, the difficult balance in Article 11 Moon Treaty sounds like this. Section 1. The moon and its natural resources are the common heritage of mankind, which finds its expression in the provision of this agreement. State parties to this agreement hereby undertake to establish an international regime, including appropriate procedures to govern the exploration of the natural resources of the moon as such exploitation is about to become feasible. And now the hottest section, Section 7. The main purposes of the international regime on the moon to be established shall include an equitable sharing by all state parties in the benefits derived from those resources, whereby the interests and needs of the developing countries, as well as the efforts of those countries which have contributed either directly or indirectly to the exploration of the moon, shall be given special consideration. Although the spacefaring nations have supported the drafting of the Moon Treaty in general, they strictly rejected the concrete result. They said, "We are planning to invent high-end technique and know-how for moon mining. But should we be obliged to share all the benefits with all other states which stay inactive and do nothing? No way. This is communism in space. One is working and all the others participate from our inventions." With this reasoning, all spacefaring nations have not ratified the Moon Treaty. Only 18 states operate the national ratification procedure, but all states without a larger space industry. So my first message to you: the Moon Treaty cannot be the legal basis for moon mining, because this treaty is without any practical relevance for the states. Turning to the more general treaty, the Outer Space Treaty of 1967. It is ratified by 110 states and determine the outer space, the moon and other celestial bodies as a common heritage of mankind. Because of this legal status, the common heritage status, it is forbidden by Article 2 of the Outer Space Treaty that a state appropriate parts of outer space. The very important non-appropriation principle of Article 2 Outer Space Treaty reads like this: outer space, including the moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. The legal question concerning this article is whether the exploitation of natural resources on the moon is an forbidden appropriation or it is not. This question has been discussed very controversial. There is one legal opinion that exploitation of moon resources is only a use of the moon, not an appropriation. Another opinion argues for an appropriation. The term appropriation should be interpreted in a broader sense. Especially Article 2 of the Outer Space Treaty includes also any other means and is with it very large created. In my eyes, the second opinion is preferable because mining is an intervention in the substance of moon surface. My second message for you: moon mining would be a violation of the non-appropriation principle of the Outer Space Treaty. The third step represents the new Artemis Accords of the United States of 2020. It is the program of the USA for the next moon landing, probably in 2025. The document looks like a convention and it structures into 13 sections. Most of the rules are in accordance with Outer Space Treaty and Moon Treaty. But in section 10, there is a dramatic game changer. If an American citizen flies to the moon and exploit resources on the moon, then this should be no appropriation with regard to Article 2 Outer Space Treaty. This section 10 reads and provides. This section 10 changes the fundamentals of space law, but it delivers incentives to operate moon mining. Of course, the Artemis Accords are not a new treaty in the terms of public international law, but it could be interpreted as an political invitation to negotiate a new moon treaty in near future. Against this background, it is very interesting to see which states have signed the Artemis Accords. With Australia, Bahrain, Brazil, Canada, Colombia, Czech Republic, Ecuador, France, India, Israel, Italy, Japan, Luxembourg, Mexico, New Zealand, Nigeria, Poland, South Korea, Romania, Rwanda, Saudi Arabia, Singapore, Spain, Ukraine, United Arab Emirates, United Kingdom, and United States of America, there are 27 states which have confessed to this new American document. From a European perspective, it is remarkable that a number of important ESA, European Space Agency states, are part of this initiative. France, Italy, Spain are European states with a big impact on the European space policy. Our German friends are still reserved. As a space lawyer, I have to add one critical point and put some water in the wine. Such dramatic changes of the foundations of space law should be better negotiated in the regular international institutions, concrete in the Committee on the Peaceful Uses of Outer Space in Vienna. This would be strengthen the legitimation of the new rules of space law. Therefore, finally, my third message to you. The Artemis Accords of the United States have the potential to become the new Moon Treaty. This document tries to determine important incentives for space industry. We will see whether the glass is half full or half empty. Moon mining is only legal in international law if the international state community renounce the common principle in outer space, which was for the last 60 years the most important rule in space law. Are we ready for this change? Thank you for your attention.
Wow, thank you very much for all those very relevant insights on kind of the legal aspects. So yeah, thank you very much.
Yeah, you're welcome.
Yeah, it was a pleasure to have you speak today. Thank you.
Yeah, thank you, and a good luck for your presentations of
Thank
this
you.
afternoon.
Thank you. Have a lovely day.
You too. Bye-bye.
Bye. Okay, guys, listen. Take it.
Sorry.
That's okay.
Trying to actually go and do that.
Okay, yeah, that's fine. Well, you.
3 minutes.
Yeah, no need to.
No need to rush.
No.
need to rush. No.
Also, there's one or two people are going to be doing the present. So other people are doing the presentations for them in the slots, and one final person has added into the day at 1600 at 4 p.m.
Okay.
20 minutes space there. So yeah, just I'll after I do my thing, I'll get you the names. Actually, while you're doing that, I'll get you those changes. But just be careful. There might be some ad lib on who's actually doing the presentation.
Okay.
It's still the same organizations, but
Okay.
yeah, cool.
Yeah, so we do next.
15 minutes? How long is the plan? 20 minutes?
It's 20 minutes, but you take as long or
And just-
as little as you want.
Your presentation is still on that. Should still be on that USB.
I have the presentation still.
I put my presentation on there as well.
Okay.
You still have mine?
Yes, I do. I pull it up. I need to get it. Yours is it this? It's this one? Yes.
That looks good.
Perfect.
Yep.
Okay, great.
Start from the beginning.
Yes, it is there. Okay.
And there's something where I can see how long I'm talking.
Yeah, at the bottom here, there's the time
so
set
there,
up.
right?
Yeah, I know you have a few more minutes. And yeah, you had your practice before.
This is the last slide.
Oh, what do you mean this is the last slide?
The last slide of the presentation.
Oh, so you don't want this to be the first one? Oh, yeah, okay, you're right.
Yeah, I would love to start.
Yeah, it would be great to start from the beginning.
You can do it backwards, and I talk backwards, and
Okay,
then you can make
perfect.
a challenge and say,
yeah, now this is,
and
now, yeah, now hopefully this is correct, right?
Yeah.
Yes. Okay, perfect. Well, we can start in 1 minute. Input, or,
Are you driving?
sorry? Let me add. Okay. I can. Sorry, in a minute.
It doesn't get better.
Okay, we get started. All right, so now I will be introducing Frank Koch, who will be giving us a short presentation now. So you can provide maybe a little bit of a background on yourself or a little explanation, or we can just move straight in.
I can do a short intro,
Yeah,
right?
okay.
So, welcome back after lunch, at least our lunch break. Depending where you are in the world, you might just breakfast or already enjoy dinner. My name is Frank Koch. I'm the Chief Moon Operator here at the Moon, at the Spaceport Rostock.
means I am responsible for that lunar test facility where we are hosting the International Moon Day today with Neurospace, our partner. It's a quite nice environment, which I will just present here in my next in the next minutes.
Great. We can get straight onto that. Okay. Yeah, so you can go
Everything's
ahead and
fine?
yes.
Perfect. So, once more, welcome to the moon. The perfect location actually where we can host the International Moon Day, right? Ideally, of course, the only location which would be even better would be the moon itself. But to reach the moon, we need to travel quite far, like these 348,000 kilometers, 84,000 kilometers. It would take 3 to 7 days, so the International Moon Day would actually be over before we even reach the moon. And we also would need a very powerful rocket and a huge budget to go there. And yeah, actually, is it worth to visit the real moon? Well, I just Googled it and I only found 12 reviews at TripAdvisor. Not all actually favorable. It seems to be a pretty gray place. Nevertheless, if you just want to reach the moon, our location here, all you need is a short trip to Rostock-Lage, right? Rostock-Lage actually is in North Germany, conveniently located at the Baltic Sea. It's a quite nice trip, not long if you go from Hamburg or Berlin, but actually you don't even have to fly to Hamburg or Berlin because our moon location is located at a public airport. Spaceport Rostock is actually at the airport Rostock-Lage, which allows you to either drive to us or fly to us, or if you want to have your very large experiment hosted in our environment, you could even ship it to us. The Baltic Harbor of Rostock is actually Germany's largest Baltic harbor. And from that point of view, it's very easy for you to actually come to us and run your experiments here at our location. Because that's what it's all about at Spaceport Rostock. It's a facility to host your lunar experiments, to host your lunar rovers, your vehicles, or whatever you have in mind. And before you travel these 884,000 kilometers to the real moon and spend a fortune to go there, you probably want to test everything from Europe very, very carefully. And that's what you can do here at the moon. I mentioned it already, it's located in an airport, and that's actually how it looks like. So it's an aerial view from our lovely small airport. And with the blue rectangle, that's the public airport terminal. So this facility is actually not somewhere hidden in the cargo halls or in the backyards. It's really installed in the public terminal from the airport. So when you fly to your vacation, if you do your check-in, you can actually see our environment. And you will see it in a few minutes when I show you the photos from that location. Or you might have seen it already when you follow our live stream from our rovers here. The location itself is really, really quite nice. It's a nice public terminal. And there we installed Europe's largest fully privately financed test facility for the moon. This is actually how it looks like. And it comes pretty close to these TripAdvisor reports. It's pretty gray. And that's unfortunately how the moon actually looks like. The moon consists more or less out of moon dust on its surface. Scientists love to call it a regolith. It's broken stone. So you take stones and break them in very small particles in a very small size, and then you have a very, very dusty environment. Actually, and that's what we simulate here in Rostock at our spaceport. The facility itself actually offers you an area of 17 by 5 meters. So actually, when you're working on a rover, you have a quite long distance where you actually can test that your rover survives this severe dust environment. You can test different wheel profiles. So if you want to climb up hills, or if you want to go faster, you might have different profiles you want to test, different materials, and see if they are moon ready or not. In the back of the right picture, you actually see our orange crane. It's a gantry which can be moved across the whole area, and that allows us to simulate the reduced gravity of the moon, right? On the moon, we only have 1/6 of the Earth gravity, so if you're 60 kilogram on Earth, you're actually 10 kilogram on the moon, so just by going there, you lose weight. Well, you don't really, but if you put yourself on your scale, it looks much better. So ideally, you go there right after Christmas or any other holidays, and you already have your bikini body for summer. Okay, back to serious. This gantry allows you to really test your profiles of your wheels, mainly for rovers, but also you can simulate seismic experiments which needs to connect with the surface. So if they weigh less, the connection will be different. And this is something we can offer here at the Spaceport Rostock. In addition, we also have the capabilities to darken the whole environment. So we could put curtains all around the 4 areas or 4 sites, and then it's completely dark. At least it's dark enough to use our very powerful light source to simulate the light conditions on the moon. There we only have the sun, and that would bring a very, very straight light to the surface. And this gives completely different shadows than you're normally used to. So the shadows are only either black or it's bright, but there's no gray zone in between. And this is complicated when you write software to find the best way for your rover. Even a tiny stone at a very low sunlight on the moon can make very large black shadows. And to identify if this is a shadow from a small stone or a large hole where your rover could fall into, that's complex, and that can be simulated here with our environment. And we could generate quite a lot of data to train these artificial intelligence software to allow real rovers later on to drive safely on the moon. Nevertheless, most often people start with this dust environment, and this dust environment can actually be seen here on this picture. So Neurospace, with its a great rover, already used our facility to see how it looks like when you drive on the moon. And even this regular speed of a normal rover on the moon creates quite a huge dust cloud. And this is more or less true. So if you look up old videos from the Apollo missions, you see the astronauts slowly walking on the moon, and they all generate quite a lot of dust there. So these white, shiny astronaut suits became gray and ugly. And this happens to these nice rovers as well. So when you drive around in the evening, you have to clean up quite a lot. And these sticky stuff of the dust is also some of the research we're doing here at the Spaceport Rostock, how to prevent that this dust actually enters a future moon station. Normally, I'm not the most brilliant person in cleaning up my stuff, but here over the past year, I learned quite a lot how to prevent dust. And I would call myself now a cleaning expert. So we have here around that environment plexiglass walls, so these shiny walls. And unfortunately, I have to clean them up every time a new customer is coming. And you learn a lot how to remove this dust from this material. And this is something which is true for the astronauts later on as well. So there might be a certain room where they enter the station, where they undress, where they move into, and all this dust will be there, which is a huge research topic. So if you consider yourself interested in the moon, but you're not smart enough or not interested enough in developing own rovers, maybe dust prevention is a topic for you, and you're more than welcome to do this with us here at Spaceport Rostock. The capabilities for this are really brilliant. As I said, we have 17 by 5 meters of this regolith, of this artificial moon dust. More or less the stones coming with the Apollo missions, with the Chinese and with the Soviets back to Earth were analyzed, and they identified all the different materials which made up these moon samples. And then smart scientists looked up which kind of stones are actually used to generate these probes. And that's what we actually did, but not on small scale. We actually created 50 tons of this artificial moon dust in our environment. And it's really, really large, which is more or less a unique environment for all scientists interested in regolith, in dust, and in similar topics. With the spotlight and our shadow capabilities, we can actually train AI and software developers or help them to identify the right algorithms to drive these rovers. So if this is your topic, feel free to reach out to us and see if we can generate data for you, or if you want to collect this data yourself. With these different lunar lighting conditions, either pole region or equator region, wherever you want to go, we more or less can come to a pretty close simulation of what you might find there at the moon. And last but not least, with our gantry, with our crane, we can simulate the reduced gravity. And this is, as I said, also interesting for seismic experiments, for ground experiments, not only for rover. So even there, we can help you a lot. And if you sign a certain document, you might put yourself under the gantry and figure out yourself how it is in walking about the moon with reduced gravity, which is actually quite fun, though probably not legal. Everything is recorded with our cameras. You can more or less follow them in the parallel stream where the rovers are driving to. So after the sessions, you might want to switch over in the breaks, but not between the sessions. And more or less, when you do your experiments here, you get a USB key with all your recording for analyzing it later in your laboratories. If the 17 by 5 meters is not enough, in theory, you can also use our outdoor area, maybe for long distance drives to find out how long your battery lasts. It's not then in regolith because the weather conditions here, rain and so on, and especially wind, would more or less blow it away. But we have classical sand environments, stone environments, concrete environments for these kind of tests. And a smaller dedicated area if you are in solar sintering and melting of regolith, this could be done here as well. With all this, I would love just to mention that we are completely open to anybody who would love to utilize our environment. If it's research institutes, startups, industry customers, but also private people are more than welcome. We have daily rates from a single day to a week or even longer. And if you think you want to celebrate your party here in Moondust, you're more than welcome. We don't ask any question. If it's legal, you're allowed to use it. And no paperwork or justification is needed. This is also very interesting, mainly for the research people. If you think this research is valuable, you're more than welcome to conduct it here, right? We don't question it. You don't have to justify it. You're really, really welcome here. It's up to you how you spend your days here. It's not us to judge you. Means all you need is just send us an email or go to our webpage. You will find our contact details later and just sign up. That's it. Which means we can also give you very fast replies if the environment is free or not utilized, and then you can just come over and use it for your own tests. Might be driving, might be ground experiments, might be sintering, whatever you find relevant, you can do it here with us under these dusty conditions. And this is the only one where I still want to remind you. You might have experience with sand, you might have experience in stone, but only very few people of you will have experience with moon dust, with a regolith. And this is dusty. I will repeat it. It's really, really dusty. You might have to seal all your mechanics. You might have to make sure that your electronics won't collect this dust. It's a little bit electrostatic here. Not as much as on the moon, but still. It will stick to your instruments, it will stick to your vehicles. Worst case, even at the evening when you go home, you have to clean up everything and it will take a while. And that's the reality on the moon, and this is what you have to prepare for. I mentioned it already, our contact details are pretty simple to find. You can either send me an email, frank.koch@pts.space, or go to our webpage, testing4.space. It's a little bit like Airbnb, but more spacey. You can just book the environment from a date and you just let us know how long, if you need certain things like special environmental surface stuff. We can help you to create the environment you're looking for, and then you're more than welcome to conduct your tests here at the Spaceport Rostock, the moon. And with this, I would say probably it's enough for you to listen to me.
Great, thank you so much. This was such an insightful presentation, and it's such a pleasure that we were able to share this with everyone. So thank you.
It's my pleasure on my side.
Thank you.
Thanks so much, and then enjoy the rest of the day, and there are more fantastic sessions to come.
Yeah,
And in the breaks, don't forget the cute rover from Neurospace driving around.
Yes.
Good.
All right.
Perfect. I think that's it, right? From your side. Yes. And from Lasse as well, right?
Yeah.
Yeah. No, not for you. You will continue. Danke für die herrlichen ungesunden Satz. Und sind die Kids noch irgendwie Spaß oder?
Is this?
Yep, that's the one.
Wir entdecken jetzt das Stock.
Ah! Ja, irgendwann reicht's auch.
Well, we can wait.
Yeah. Just want to also make sure that that's shared in the.
Verfolgt ihr die Social Media? Ich habe schon irgendjemanden, der
There's
gesagt
no
hat,
one to
gefällt die Menschen.
Just in
Also
case.
ich gucke immer mal, ich habe zwar vorhin was gepostet, aber ich weiß nicht, wenn irgendjemand kommentiert hat.
Go, give it a couple minutes and
Das
then.
ist halt ein bisschen ärgerlich, in dem ersten Livestream war 80. Und das war natürlich, das haben wir danach.
I'm good, I'm a little tired.
Yeah, long day.
Ach so, wenn sie rausgefahren sind, sind sie nicht wieder eingeloggt.
Nee, wenn dann sich die URL verändert und dann je nachdem, LinkedIn ist ja so toll wie Facebook, ne? Da kriegst du einige Posts erst Tage später.
Genau, also und das steht erstmal so von den Kommentaren und so. Also es hat sich auch niemand negativ geäußert, aber es hat sich eben auch niemand positiv geäußert.
Ach, wird schon. Ich finde es ganz gut. Ich glaube, das trifft.
Irgendjemand ist jetzt hier vorhin vorbeigegangen und hat gesagt, er hat sich vorgestellt, hier ist mehr zu seinen Kindern. Das war jetzt natürlich ein bisschen, ja, aber für Kinder ist es ja auch schwierig.
Aber ich finde, man kann schon mal schön gucken da hinten.
Ja, aber ich glaube, die verstehen ja jetzt vielleicht dann auch nicht so ganz, warum sie jetzt nicht zum Rover rennen dürfen oder so. Das ist einfach ja nochmal so ein bisschen.
Ist so.
Ja. Kann man immer, ich glaube, das kann man schlecht erklären. Einfach. Ich glaube, das ist so ein, ja.
Man kann auch nie allen es recht machen.
Eben, ach, das ist ja einfach.
Gut.
Das ist schön.
Sonst, wenn irgendwas ist,
Ja.
man findet sich eh.
Super, danke.
You just have to, when you do the presentation, you can't like actually present it. You have to just do it with the keys. Because I don't know why it doesn't show up otherwise. So. Okay, so for our next presentation, we have one of our own, Rob. So yeah, you can give a bit of a brief introduction, and then we can get into the PowerPoint. Yeah, wait, let me just change it. Sorry. Yeah. So. Okay, you can go ahead and get started.
All right, cool. Well, hi everyone. I'm Robert Marnie, the mission manager here at Neurospace, and today I'll be giving an overview on why lunar exploration is a bit more important, a bit of the history of it, some of the requirements, and how our new approach can help enable exploring the moon a bit further. So, Neurospace was founded in 2020 with the goal of opening up the lunar surface to further explorations. We are a very diverse team with people from around the world working with us and with a diverse range of experiences as well. I, for example, worked in everything from the rail industry to structural analysis to drone manufacturing, while dabbling in designing Mars colonies in my spare time, as you do. So why specifically do we want to go to the moon? There's a number of reasons to do it. Like, of course, why do anything? As JFK said, because it's there. But more specifically, it is a very good stepping stone on the road to Mars. Water ice there can be used for fuel. Practicing for the surfaces can make things a lot more achievable, and not just to Mars. It can help get out into a larger array of locations throughout the solar system. So, as I said, you can use this as a stepping stone onto Mars. There are, however, a lot of things that make the moon a lot more achievable than Mars. For example, launch windows come around every 3 days as opposed to every 2 years. The travel time is far less. It's not 9 months. There's no atmosphere, so it's a lot easier to land. The exposure to solar energy is a lot higher, so you have access to far more sources of energy for you to actually do things with. That having been said, exploring the moon does come with its array of challenges. As you've heard a lot today, the regolith can be incredibly destructive. While the lack of an atmosphere makes it easier to land on, it makes it just as dangerous as deep space. It has a 14-day cycle with temperatures that can range from 390 Kelvin down to almost 95 Kelvin. There is no magnetic field to protect from radiation, and the nature of the surface makes it very static and electrically destructive as well. So that having been said, there have been rovers sent to the moon before. This isn't, so we're not necessarily starting from scratch here. The first one was Lunokhod, held by the Soviets in the 1970s. This managed to survive for almost a year. It weighed close to 750 kilograms, and it used a combination of solar panels and radioisotope heating in order to survive through the night. It would basically have a lump of radioactive material that would keep it warm and heated through those dark and cold lunar nights. Now, not a moon rover, but a Mars rover. This is a lot similar to what we're building. The Sojourner, it was about 11.5 kilograms, but it managed to travel a full 10.5 kilometers on the surface of the moon. Sorry, on the surface of Mars. It's powered with a solar power generator with a peak power of about 15 watts, showing that these small-sized rovers can be built and can operate in these harsh environments for very long periods of time, even using technology that is several decades old at this point. More recently, the Chinese space program has been able to land several rovers on the moon. These are slightly larger, but again, it shows that there is still growing interest and growing endeavors to explore the moon. So we're not starting from scratch here when it comes to designing rovers, but their success and their range of applications has been fairly varied over all of the years. So how do we make this work as a business? Well, one way we can do that is to potentially look at other space businesses that have occurred in the past, specifically looking at CubeSats. Now, for those who don't know, CubeSats are a standardized satellite design based around a 1U or cube bus. These are 10 by 10 by 10 centimeters, hence the name. They were developed in the late 90s and early 2000s and were initially considered to be nothing more than toys or learning tools that university students could play with before they got to work on proper satellites. Now, however, they are the cornerstone of billions of dollars of industry. As you can see, their use has spiked over the years. They've been used for everything from testing solar sails to simulating orbits for space stations around the moon to providing communication relays to Mars and back. They are incredibly diverse technology that it can be used in a number of different applications. Additionally, the support technology for these communications, deployment, transportation is an incredibly large and robust industry. Now, while private industry has taken over as the primary user of CubeSats in today's environment, universities still make use of the second most number of them. So how does this compare to the current state of rovers and exploration systems today? Well, primarily, the CubeSats have a standardized approach, COTS off-the-shelf parts, and a very easy open standard that can be used by anyone. Rovers, on the other hand, are almost all done by the government. They are all customized, large, heavily made things that are designed for very, very specific missions. There isn't even an open standard, let alone commercial standardized parts. And while this is changing, there are a number of initiatives to develop commercial and flexible rovers. These all suffer from a very similar drawback in that they are all very specifically designed for very specific roles. They don't allow flexibility, they don't allow the use of existing off-the-shelf technologies, and as a result, they face limited applications as it currently stands. So what is our idea and our approach for taking this is to basically take an existing standard, the CubeSat, which why reinvent the wheel, build a chassis around it, and then make it moonproof. Whoop. There we go. All right. What this allows us to do is to tap into the years and years of technological development for CubeSats. While the environment in low Earth orbit and deep space is different to that on the moon, the deep space usage of CubeSats has shown that they can operate in the more higher radiation environment that exists on the surface of the moon. This allows us to use, as I've said before, components that already exist and anyone can go out and buy. Essentially, all we will need to do in order to make these function on the moon is provide the ability to survive the temperature ranges and through the lunar night as best as possible. By doing this, we'll allow more organizations and research groups to be able to focus on their mission rather than having to develop the rover from scratch or be constrained by a number of onerous design requirements. So this has potentially endless applications and everything from basic exploration and discovery of things on the moon, pharmaceutical and biological experiments, all the way up to potentially mining and research utilization plants, although those latter ones are probably a bit much for something of this scale. So in doing this, we realized we can actually offer our technology here in a range of applications. By networking them together, they are able to have specialized uses in their different areas. We call it Hyper because we intend to have them work through a Wi-Fi based mesh network. This will allow them to be far more flexible and far more specialized in when deployed in swarms. For example, you could have a queen that is based around communication back to a base station or back to Earth, drones that can have better optics and analysis equipment, and potentially even workers that could be equipped with arms and certain kinds of manipulators. Additionally, we're looking to offer these in a tiered system with raising levels of qualification and thus expense. This will allow people to either experiment with simpler parts that have a similar form factor before having to go out and do a very expensive and destructive testing. And it also allows for a range of applications here on Earth that, while might need a similar degree of qualification to operating in space or on the moon, won't necessarily need the full gambit of thermal protections, power systems, or protections against a vacuum. So here's our current lineup of rovers that we've been working on, and if you tune into the rover live stream, you'll be able to see some of our development rovers currently being driven all over the tested ground here. So, thank you all very much for your time, and if you have any questions, don't hesitate to ask.
All right, thank you so much for that. It was so nice to get a little bit more insight into our own mission here at Neurospace. And yeah, we'll just be taking a very quick break while we set up the next speaker. Thank you. Next is, I think.
Okay. Well, I think Manish did say that we're traveling.
Okay.
Can we just make sure we're muted?
Yeah, we are.
All right, good. Oh, there, Manish.
Okay. Are we able to share? I don't think so.
Oh, I think I may have been muted while I was presenting.
No. This is like a different question.
Yeah, I know, but if you go and
Oh. Yeah, well, it's okay.
throughout the entire thing?
No, on the live stream it was fine.
the live stream was fine, but it was the
On the
Jitsi. But there was only, I don't think there was anyone else in the Jitsi.
Yeah, so it's okay. Okay, I'll just.
Alright, cool. I'll just pop off. Thanks very much.
Great.
Doing great.
Hello. So our next speaker is Manish Verma. Just to clarify, unfortunately, I think the sound from the presentation is not heard on the live stream or on the actual presentation. So yeah, just to clarify.
Okay. Can you hear me?
Yes, I can hear you.
Okay. Clear enough?
Sorry?
Hello? Is it clear enough?
Yes.
Okay, perfect. Yeah, okay, I will take what is in hand. That's fine, not a problem.
You have a few more minutes anyways until your slot, so feel free to take your time or start now if you would prefer.
We can take it. We'll take our time.
I can wait till the 2 p.m. slot if that's okay with you.
Yeah.
All right, perfect. Great. I think fine. Like now the next few ones and like the next two are I think are on the thing. So there's really actually like
Then that's it, right?
no, then there's more. Then there's Leonard. Then there's 3 more people.
And you got the message about the last two? It's in the Mattermost.
Okay.
There's one at 1540 is a different person but from the same organisation.
Okay.
And then at 1600 we have one Weinhold person should be joining.
Okay.
And then at 1700 Rob Mill should be joining in. But
Okay.
I think Irene wants to host that one.
Yeah.
Are you okay?
Yeah, tired.
Can I help you in any way?
I mean, it's okay. Like the next few, anyways, they'll just be speaking, so I'll just be sitting here anyway, so I don't really have to do anything.
Okay.
Yeah.
Okay. And how many people are on now?
Now it's just us, and then the person who's going to present is Manish.
And are they seeing him on the live stream?
Right now, no. But like once he presents, I put on live stream. Right now they're seeing this on the live stream.
Okay. And how many people are on live stream?
Right now there's no like just him and us. But before, like in the morning, there was many people. Like all the people that were presenting were on there of the morning. So yeah.
Yeah, okay, I was checking in to see if I can help.
Yeah, it's okay. I mean, I don't really think there's much. Yeah. Um, yeah, anyways, the next two, they're just on here, so I can just sit and do whatever.
And your flight is ready for tomorrow?
Yeah, it's at 6:40 p.m., so yeah.
Evening?
Yeah.
Oh, okay. So you still have all day too?
Yeah, I packed most of my clothes already, so I have to just pack up the rest of the stuff, but yeah.
And are you looking forward? Where are you going to?
Back home to Geneva.
To Geneva
Yeah.
first?
Yeah. So yeah, it'll be nice, because I haven't I only spent 10 days at home when I came back from uni, so I really haven't spent a lot of time at home recently. So yeah, I'm excited. Also, a lot of my friends will be back, so I'll get to see them too, which is nice.
You went to school in Geneva, right?
Yes. I lived there since I was 3.
So you're it's really home.
Yeah, really. And my family's still there, so yeah. So I'm excited. A bit sad to leave Berlin, honestly. I really enjoyed being in Berlin, so in the summer.
And then you go back to the US?
Yeah, in September.
For the next semester?
Yeah, exactly.
How many do you have left?
I'm halfway through my experience at Brown, so I did already 4 semesters and I have 4 more. Yeah, which is crazy. Can't believe it's already halfway. So yeah.
Yeah, crazy.
Did your sons come or?
Yes, they were downstairs.
Oh, I didn't see them.
Oh, they had such a nice time. Oh my God, they're so happy.
Oh,
All the t-shirts.
Oh,
so
that's
sweet.
so cute. Did you come with them yesterday or they came today?
We came super early. We left at 5 a.m.
Okay, yeah.
Yeah. And now they are somewhere in Rostock.
Yeah, having a day trip.
Nice. Are these used?
I don't know. I don't think so.
What's there? The last live streamers begin.
The last live stream, I think it begins at 5. But that one Irene was doing, so I'm not doing this one.
With NASA.
Yeah, it's with the Rob Mueller. So she's gonna be in charge of that one. And yeah.
I could walk through the yard. It was really.
Oh, really? Wearing the boots?
Yeah, it was so fun.
How does it feel?
It's so weird because it drops. You sink real fast.
Really?
But then it gets really hard.
Oh, that's not what I expected. When I imagined the moon, I didn't imagine that there was so much dust. I thought it was just a stone or something. I don't know.
Yeah. So and then sometimes it gets so you sink so deeply. So weird.
Yeah.
Yeah, it was fun.
I think we can now. Good. Okay, so are you ready to present now?
Yeah, I am.
Okay, perfect. Well, then you feel free to just share your screen and get started. And you can also provide kind of a brief introduction on yourself.
Yeah, thank you. So can you see my screen already?
I cannot see your screen at the moment, no.
Now?
Yes, a bit blurry, but I can just see all the Jitsi part of your screen. Okay, now I can see. Perfect.
Can you see the Luna Zero?
Yes, yes.
Okay,
Also,
first of all, thank you for.
We can hear you only a little faintly. I don't know if there's a way to maybe.
Okay.
Oh,
Is
great.
it okay now?
That's much better. Yeah, thank you.
Perfect. Yeah, no problem. First of all, thanks for inviting me, and yeah, happy National Women's Day to everyone. I have heard quite a few interesting presentations before earlier in the day, and I'm really, really happy to know that there is so much work happening on the moon rover side, especially on the micro, also one of our teams actually. So yeah, let's just get started. So I will present today a project from TU Delft, which is called the Luna Zero, and I am the head of operations and team leader for Luna Zero since 2017. My name is Manish Verma. My background is aerospace engineering, and for the past almost a decade, I've been working with off-world robotics and one of the projects that was started in my student time and has continued since 2017 as a full-fledged flagship project to go to the moon. So to get started, what is our vision with the Luna Zero? Well, as it is part of the university, the first thing is education, of course. And I think a lot of university teams in Europe and in US across the world have this vision where you are trying to train the next generation of engineers for space applications, especially given that a lot of space studies are done theoretically and very few get to do hands-on experience. And we as a project and lab also bring that to the students. The second is technology. A few years back, one of the research pillars in the various faculties of engineering and electrical engineering was miniaturization. And miniaturization led to swarming. I will not dig deep into it. I think a lot of people before me have already explained why miniaturization leads to swarming. One of the key important things is that we're trying to miniaturize almost everything that is concerning a like rover, and this means including the sensor systems which might be found off the shelf. So we kind of coordinate and collaborate with researchers within TU Delft and work with companies and see we can miniaturize even those sensors to be compatible with our other micro rovers. So one unique thing of our rover compared to others is its unique locomotion, which I will talk a bit later about. And the last thing is to provide a versatile platform in itself, where as everybody knows that a rover mostly serves around a particular payload. Bigger rovers serve about multiple payloads. Micro rovers usually depend on one payload or science mission in mind, and almost like everyone else, we are supposed to provide a versatile platform to support space exploration, either it's moon, Mars. So how does the timeline look like for our project? So we originally, as Zebra project, it was not space back then. It was just a Christian Zebra started in 2013. We started with the mindset of having miniaturized rovers to begin with, more for terrestrial applications, and swarming came a bit later down the line, 2015. But it was still only for terrestrial use to do more sensor deployment, collecting images and mapping using swarms. Then in 2017, around the same era when Artemis program took off more officially, and we had like more push from the industry to see that yes, this is something happening. So the whole pipeline of the of the of the of the industry has to be in line. So this means that when the industry was ready or even the governments were ready to support such a mission, we could also start within the universities so that this zebra will turn into a zebra rover. In 1820, it's almost 2 years to build the engineering model from ground up. And then we went on to do development design and testing, which we are currently in phase of it. We will also, at the end of the year, we will finish most of our development testing. Some things like vibration, shock, TVAC, and also some AMC inhalation testing on our payloads. So this will, for say, qualify, build into a qualification model, which will take several years, and then probably 2026 will be able to qualify for the model itself. And if we do our first mission quite right, the plan is to move forward and do multiple missions from there forward, which could lead to swarming. And one of our key projects, goals at a national growth, is to implement LUFAR, which is basically doing radio astronomy, using multiple rovers as the companion to create a big dish interferometry technology on the spot of the world and go into zero frequency processing. And we think that zero fits this large scale and we want to reach that goal. So how projects set up? So I think very few projects, and I think this is very unique to the rover and the drone teams, basically at the university level, where they can have their own rover team and also go out to do analog missions. So first, I would like to talk about topic like where does the name zebra come from to begin with. And actually, zebra is itself a Dutch abbreviation for Z-bear robot, which actually translates to six-legged robot. This concept of a legged robot was first introduced by the Rex project from the University of Pennsylvania as a very robust form of locomotion. It can walk through sand, rocks, mud, vegetations, airways without any complex locomotion mechanism. But more there's behind the concept is just there's more to the concept of zebra, just the locomotion capability itself. And that is the swarming and miniaturization that also comes into play. The idea behind is to develop a small, relatively simple robots to perform complex and as a swarm of zebras. Because this means that kind of like an army of ants, collectively finding the shortest and easiest path to the best force and coordinating forging efforts. This means that we are actually going the other way most of the rovers actually go, where they're trying to implement more and more sensors and complex algorithms to finish a certain task. We are going actually trying to make it with less sensors and trying to use more geometry algorithms to check to see if we can do the same complex stuff using and being inspired by nature. So I remember earlier in the day we were having a conversation about time, how fast the rover should be. And I think in most of these space missions where rovers play a crucial role is the exploration part and even deployment of these sensors. The one aspect that missions usually have where robots are installed surgeons on the surface and not humans alongside with them is time actually. You do want your rovers to spend as much time as possible doing certain activities. On Earth, 5 hours might be long, but on Moon, 5 days is not enough. So you can actually let your rovers do a lot of things randomly and find the most optimized way of doing accomplish some tasks. So moving forward is that the Lunar Zebra project is also divided into several departments like structure, software, and ground station from the rover side. And also we also go out to test in the field a lot of analog missions. We started doing analog missions in a very large scale in 2017 when we went to Hawaii for high seas mission. And since then we have every year pretty much gone to either 1 or 2 analog missions in Iceland, Czech, Spain, UK, and even Sicily. So these missions actually allow us to test experimental subsystems. We have been testing different shapes and sizes of legs, stiffness of legs, also different sizes of the rover itself, because the size of the rover plays a crucial role in the algorithm optimization of speed, turning, move forward and back, and also especially the center of gravity of the rover, so it can do more high high angle of banking or even inline terrain. Um, and then, of course, the analog missions bring more regular and more uh, soon hands-on experience into the field. Otherwise, a lot of these missions, students have to wait very long time for a mission to be successful, to launch into the moon and getting some real-life experience, work with ground systems or setting up tests. Not only that, in academia also we play a very crucial role, just like any other teams. And so, so we also have a test bed of 4x4 meter regular with accurate lighting on the, mimicking the south pole of the moon. And in the future, we're planning to have tracking cameras to see what, so that we can uh, uh, see where the roads are doing it in a GPS denied environment. So how does the rover look like? What is its unique property? So the rover is about 2.5 kilograms in weight. It's fully built of aluminum. So all the sun parts are built of carbon composite. The unique thing that you can see is the locomotion shape, which is the legs. So they are called the C-shaped legs. And one of the key things is that at a given speed, it can actually just overcome obstacles with just brute force. Although the rover is designed to have obstacle avoidance system and path planning, it is at a very rudimentary level, so that it just avoids hitting samples and just goes around it. It has a stereo camera. One of the other defining aspects of this rover is that the rover has a deployment, that the rover has a solar panel deployment system. This means that the rover can actually go to different latitudes on the moon and still have the optimum solar light hitting on the array for charging. So for our first mission that is tentatively planned for 2026 is that we want to survive the moon for 14 Earth days, which is one moon day, demonstrate the unique C-shaped legs. And we also have built our own camera in-house, which is about the size of €1, I think, coin, and about 20 grams. Actually, it's two grams each camera. And we also have our own in-house obstacle avoidance system. One of the unique things that we're trying to do is communicate directly with the rover between the Earth and the moon at a very low power. And we have our own radiation measurement device on board as a science payload. So just to wrap it up, because I cannot share the sound of the video, I will just show you the video once to actually give you how the mission will actually look like in terms of this animation.
So unfortunately, we can't hear anything, but we can hear your comments in case you might. Okay. So unfortunately, we can't hear any noise, but maybe you can comment this.
Yeah, that's maybe not good. So yeah, so this is one of the future applications where I was just talking previously that we can have smaller antennas on the rover for multiple times, and create a virtual big dish. The last part of this animation is that we're also looking into human machine interaction applications of these micro rovers. The past two analog missions have been with analog astronauts to understand how micro rovers can also assist uh, the astronauts in doing their task more efficiently, not only at their technical or scientific tasks, but also psychologically and them help.
Great.
So yeah, from my side and from Zero, if you have any questions, feel free to ask.
Thank you very much. So, are there any questions? So from my side, hi, here's Irene. I would like to ask you what was the challenging part for you from the whole design to now where you are, and what do you expect to come up? What might be challenging as well?
Uh, I think when we started back in 2017 with this idea, the challenging part was having the experience and the knowledge to ask someone else what they have experienced, and given that no one in Europe had actually been to the moon before, it was quite challenging to see what was correct. So we can of course do all the engineering calculations the way it's supposed to be done. We can extrapolate information from previous deep space missions, but because nobody has actually worked on an actual moon mission, it was really hard to verify and validate all the things that we had actually calculated. So we were in a limbo for a lot of months, how to progress with it, because in aerospace most of it actually relies a lot on past missions, and this was something which was quite new to us. That was the first challenge, but I think over time, while doing subsystem testing, and that we have seen other teams also come up with the same problem and have faced and solved those problems. Uh, we have a lot of preference now to do certain things. I would not say that we are still there yet, but the approach that we have now taken, which the team here have taken, affects qualified for yourself. In the future, I see basically, at least at a university, it might not be for a company, is maintaining such a high level of knowledge and experience, given that students come and leave quite frequently. So maintaining that level of experience within a team which will actually launch, which is 4 years down the line, is very difficult as a as a project manager basically uh, to maintain, because you can have all the experience in the world, but if uh, uh, your bottom line engineers, the actual engineers who actually work day to day, daily with all the experience, it becomes quite difficult to maintain such a team. Uh, that would be my biggest fear and biggest challenge on how to keep this going for the next upcoming 4 years. Yeah.
Yeah, I can totally understand. And how do you think to launch it? Do you have something already in mind, launcher opportunities and so on?
Yeah. So it's uh, it's actually, but it's basically we are talking to at least four launch companies, mostly lander companies, because launch companies don't matter here. It's actually a lander company. And the thing is, it's a chicken and egg problem, that do you finish the rover first or do you have the lander first? And that's a decision that lies not with me, but with the university itself. Uh, so we have been in advanced talks with a couple of them, where if we have the qualification model ready, then we can make a flight model with the specifications of the lander kept in mind. But for now, there is no guaranteed lander we are also waiting for someone to be successful the first time.
So, because talking of Blender, we have our next speaker, who will be Natalie. So maybe you should listen to her as well. Maybe this might be an interesting
Yeah,
opportunity.
yeah,
I would like to
absolutely.
welcome you to listen. So,
Yeah,
yeah.
thank you.
So,
Hello.
thank you very much.
Yes, thank you.
No
Thank you
problem.
very
Good
much,
to be here.
for the wonderful presentation. Hello to Natalie Bergman.
Hello, nice to meet
Hi, welcome. How are you?
you. I'm very good. Wait, let me just start my camera. Okay.
Hi. Wonderful background. Fits to our days motto perfectly.
Exactly.
Okay, please. I'm handing over the mic to you. Feel free to present yourself and
Mhm.
tell us a bit about who you are, and looking forward to listen to your presentation.
Okay, perfect. Yes, let me just share my screen. Okay, I think I have to make sure some permissions are there. I might have to quit Google Chrome and join in 1 second again.
Okay, no worries. So she'll be back. It's like the typical permission stuff. We know it. So let's wait. Hopefully she will get in once more. So there she is. Hi, Natalie.
Okay, I'm very sorry about this.
Don't worry.
It did not let me share the screen, so hopefully now it lets me do it.
Okay.
Yes. Okay. So, can you see my screen now?
Yes.
Perfect. Then let me introduce myself. I am Natalie. I'm a mission manager at the exploration company. So basically what I'm doing is that I'm the primary contact person for all our customers, and I am in charge of the interfaces with the payload. So I ensure the successful integration and operation of our payloads. But today I want to tell you about the exploration company, and we have the goal to democratize space exploration, which is of course a very big goal. So why do we want to do that? Well, we believe that space can make Earth a better place. We think that space can improve life on Earth, it can inspire old and new generations, and it can also open up possibilities for exploration in general in space. So how do we want to play a role in that as the exploration company? Well, we are building a transport vehicle, which is called Nyx. It is modular, so we have many different configurations for it. So we have a free-flying configuration where it can be used as a platform for microgravity experiments. We have a configuration that will be able to dock to space stations, and we will have a configuration called Nyx Moon, which will be able to transport goods to the lunar gateway or to the lunar surface. So what are characteristics of this vehicle? Well, for us, it was very important to be launcher agnostic. So we want to be able to launch with all the launchers that are currently available that can launch this big of a capsule, so around 4 meters in diameter. But we also want to have the opportunity to launch with launchers that are bigger, that are going to be developed in the coming years. We want to do that at a price that is very competitive so that we can offer this to as many people as possible. And we want to be sustainable while doing so, because as I said, we want to use space in order to improve life on Earth. So therefore, we want to have as the minimum impact on Earth as possible. And that's why we plan to be completely reusable and refuelable. Additionally, we want to be very open and transparent in what we're doing. So as we want to democratize the space, we aim to be open source and also use open interfaces. But maybe more about the exploration company itself. We were founded in July 2021, so pretty much exactly 2 years old now. We have the headquarters in Munich, and we have another office in Bordeaux. So Bordeaux is actually mainly focused on propulsion systems for the moon lander. So there's a lot going on there, and I'll show you some more later on in the presentation. We're roughly a bit more than 80 employees now, which is pretty much half-half in France and in Germany. And it's a nice mixture between young professionals and very experienced people who have many different viewpoints. We were very fortunate to have a great funding round at the beginning of this year, so we're set to build everything that we have on our agenda, and we're very much looking forward to what the future holds for us. So why do we believe that a transport vehicle in space is needed? Well, if you look at space right now, you see, okay, there's the ISS in low Earth orbit, there's a Chinese space station. I mean, there's some things happening, but it's not that much yet. It's a one-digit market, but if we fast forward a few years, we can see, okay, 2030, there will be the ISS that is retired, but a lot more space stations coming up from the US, mainly commercial entities. There will be the Lunar Gateway around the moon and another station, which is a cooperation between China and Russia. So a lot more happening there. You can see, okay, the market increases to about a 2-digit billion market. So a lot more opportunities there. And then if we fast forward a few years more, we see, okay, there's an Indian space station, low Earth orbit. There might be some more stations around the moon and possibly even around the Mars. So there's roughly a triple-digit billion market. So there's a lot of possibilities for us to leverage on. And all of these space stations need to be supplied with cargo. And that's where we want to come in. So we want to be able to have this up mass to the space stations, but also down mass back to Earth, or down mass to the lunar surface from the Lunar Gateway, for example. So of course, we don't plan to just go to the moon directly or to dock to the stations immediately. So we have a roadmap for, so our plan to go there is, okay, this year we have Mission Bikini, which is basically just a very small re-entry demonstrator. And there we're gonna get some data on the re-entry, on how the heat shield is behaving and all these type of things that we can then move on to Mission Possible, which we're also currently building at the moment, which is our first functional prototype, flying also with customers. It's a bit smaller than our final capsule, but as I said, already fully functional. And then we have in 2026 Mission Odyssey, which will be the maiden flight of Nix Earth. So our fully functional capsule with the service module and everything. It will be in orbit for up to 6 months and then return back to Earth. And then in 2027 also we have the first docking concept demonstration, because as I said, we have different configurations, one for free flying, which will be Mission Odyssey, but also the ones that will be able to dock to the space stations. And Mission Home will then be the first demonstration for that. And then finally, we also have Mission Moon in 2028, so our first flight to the lunar surface. So if we look at the things that have been going on a little bit more in detail, we have here Mission Bikini in the background. As I said, a re-entry demonstrator. So we were awarded this launch by ESA in January 2022. And then things had to go quite fast. So within 9 months, we went from design until flight readiness, which is, of course, very, very fast for things in space. There was a lot of effort and work put into this, but it was a great success for us to see that we can do this and that we have the right capacities in the team and that we're capable of doing the things that we set our mind to. I mean, we know, unfortunately, okay, Ariane 6 has not launched yet. So we did not actually, we weren't able to fly this demonstrator yet, but we currently plan to fly from India this year. So in 2023, there will be a launch of this mission, and then we gather all the data that we get from the sensors on board of this demonstrator to then implement that in our new capsule for Mission Possible. So this one, as I said, is a fully functional prototype. We have customers on board. We actually have about 300 kilograms of payload on board, so we're fully booked. Very nice for us to see also to have a lot of people who are interested in our technology. And we also have a very broad set of customers on board. So we have very established players like ESA or CNES, but we also have an 11-year-old boy who partnered with a 20-year-old student from Australia, and he wanted to test his algorithm in space. So that's very nice for us to see that we have a very broad range of customers on board, and that we can also have educational payload on board. So for this mission, we will have a duration of roughly 3 hours. And during that mission, we will have about 30 minutes of microgravity. And then we're going to return to Earth, splash down in the ocean, and have recovery of the capsule, and then basically hand over the payload back to our customers. As I said, this is already in full design. So last year was focused on designing, procuring, and forging everything. And now this year, actually, the assembly is starting. So you can see on the right side the heat shield that is currently getting manufactured. And then in August, actually, we're going to start the assembly of the capsule. So very nice for us also to see how things are coming together. And then the next step will be our fully functional capsule with the service module. As I said, this one will be the free-flying configuration first. So it will have microgravity experiments on board. The first flight will probably be only about 2 months. But as I said, it can stay in orbit up to 6 months. For the first mission, then, we have payload capacity of around 4 tons. And it will be fully automated. So all the experiments on board will be able to perform fully automated, and nobody will be on board of our capsule at that point. In the future, there will also then be the possibility to go to the space stations and supply cargo to them. And then possibly in the future also supply, or not supply, but to bring humans up to the stations. So maybe interesting to know that, I mean, I said we want to be as affordable as possible. So that's why we also want to be transparent. So the price actually for Nix Earth for the first main flight will be 20,000 euros per kilogram in the unpressurized department and 25,000 euros per kilogram in the pressurized department. As I said, completely automated, and then it's just going to be in orbit for around 2 months until it comes back to Earth. And maybe also interesting to note that price contains everything. So it's launch, service, power, communication, and the return back to Earth. So really it's one price and then it's set. And then, the next step will be Nix Moon, as I said. So this vehicle we plan to have as a transport vehicle, basically looping between the moon, the gateway, and back to Earth, being able to bring mass in between and also do last mile delivery to the lunar surface and do hopping there. The main flight, as I said, is 2028. And depending on the configuration, so if you want to bring payload to the lunar surface, it will be about 2 tons of payload that it can carry for delivery to the lunar gateway. We have a capacity of roughly 5.5 tons. And if you want to perform hopping on the moon, we have a capacity of around 5 tons. Again, here, a very competitive price of 150,000 euros. So we hope to offer this to as many people as possible and to also as many industries as possible, because we want to be open not only to the traditional space industries or industries that make use of space, but also to a lot of industries that maybe don't know yet that space can hold a lot of possibilities for them. So that's why we also do a lot of educational talks where we try to show people of what space is capable of and how they can benefit from this. And then here you can see what we're currently doing for Nix Moon, because we're already starting to work on the engines there. And here you can see the engine pump and injector have actually been tested in 2022. And this year, actually, right now, we're testing the chamber and the injector head. So we have a cooperation with the DLR, and we're hot firing the first chamber and effector head, actually probably right at this moment. So it's very nice to see that things are coming together. And we're already performing these tests so that we can make sure that we stay on time, on quality, and on cost, because that is really our goal for everything. And that's something that is really, really important for us. So yeah, that's everything about us right now, and I'm happy to answer any questions that you might have.
Great, thank you so much for that. Yeah, so I guess we'll leave it open if anyone has a question to ask. Yeah, I think, oh yeah, Leonard
Hi.
over here.
Actually, I do have a question. I was wondering, like in the last slide you showed, I found it really interesting to see that you had this 3D printed chamber. I believe it's 3D printed. I was wondering if, like, are you going to use any novel manufacturing techniques, or are you trying to get something that is reliable and built up on heritage technology?
Well, to be honest, I'm not in the loop for the whole manufacturing process. I know that we have looked into novel technologies to see how we can implement them, but this chamber, as far as I know, is not with any novel technologies. But it's definitely a topic that we are looking into to see how we can make use of it.
And then, if you allow us a follow-up question, you said this is going to be tested and built, I believe, as well at DLR. So how is your relationship between DLR and the exploration company?
Oh, we have a partnership.
Okay, so only for manufacturing or constructing?
That's a very good question. I don't know the exact details of the partnership, I'll be honest. That is nothing where I'm involved in. But I know that we have a very strong partnership and that we are able to leverage on the testing facilities with them.
Nice. Thank you anyway. Very good presentation.
Thank you.
Thank you. So we're just going to take a few moments to get ready for our next speaker.
Perfect.
Okay. All right, so now we are presenting our next speaker, also one of our own coworkers at Neurospace, Leonard. So yeah, you can introduce yourself briefly, and then we can get into the directly into the presentation.
Thank you, Talina. Yes. Hi, I'm Leonard. I am a development engineer for Neurospace now for 1 year. And I studied aerospace engineering in TU Braunschweig and TU Delft. And I'm now responsible for all the mechanical stuff at Neurospace.
Okay, great. So we can just go ahead and get started with the presentation. Okay.
Thank you. It's not this one?
Oh, wait. Okay.
That's it, yeah.
Great. Okay. Yeah, you just.
This is live already?
Yes.
So I would like to talk a little bit about moon rovers, and especially in the...
Sorry, just you have to only present from this. Like, you can't do the presentation.
Okay.
Okay. Yeah.
Oh, all right. Sorry.
That's okay.
Yeah, I would like to talk about moon rovers and especially about the lunar environment that the moon rovers are exposed to. I will start with one slide of history lesson to update everybody on what happened so far on the moon. So here we have a quick overview about all the vehicles that have driven on the lunar surface so far. And we can see it's not many. So, and especially what we can see is most of them, the Russian and the US ones, they've driven on the lunar surface in the 70s. And this is quite some time ago. And now, in 2013 and 19, we had 2 Chinese attempts that were successful. But in total, this is still quite a low number. And now I would like to introduce you to Hyper, which is our proposal for a rover for the lunar surface, so the next generation. And if we look at these rovers from before, these are all machines that are as big as a small vehicle, like a car or something like that. Hyper is only a couple, at the size of a shoebox maybe. So it's quite a different approach, and you will learn in this talk as well how we approach this. But first, I would like to show you this quick animated video where you can see one of our versions in a test drive in Italy. It is equipped with a LiDAR and a stereo camera scanning the surrounding environment. And yeah, I just wanted to give you a feeling for the size of the rover. That's why I put this in here. Here another comparison. You can see on the right hand side Lunokhod. This was the first Russian rover, 840 kilograms, so about the size from a small car. And you can see in this diagram where the LRV, the vehicles from the US and U2 are positioned in the mass and distance traveled. And on the picture on the bottom left, I put Hyper in as a comparison. So you can see these are really small rovers. That's why we refer to them as nano rovers. This has nothing to do with nanometers. This is just because compared to the traditional rovers, they are so small. Before I go on, I want to introduce you as well to our staggered system. So we have 4 variants of our rover because as we started developing the space rover, partners from other industries such as universities, chemistry industries, and even hospitals approached us, and they wanted to know if they could use their rovers for their reasons as well. But of course, if you have a rover that's only working in your plant or your industry facility, you don't need a space-grade rover. That's why we came up with this tiered solution. But of course, the ultimate goal is the 4th tier on the right-hand side, which is the space. So now you've got a bit of the background of lunar rovers, and I would like to go on and talk a little bit about the lunar environment. So what is the challenge of the environment that expects us there? And they can be summarized in these 5 categories. So the first category of challenges in the lunar environment is, of course, the radiation. The moon has no magnetic field, it has no atmosphere, and therefore the radiation from the sun and from outer space impedes the surface of the moon without any barrier. It just hits the surface, and this is a very big challenge to all systems that you might have installed on the lunar surface, because there's no protection. The second environmental challenge is thermal. I will talk a bit about this a bit more in detail soon, but one thing I can tell you already, the difference in temperatures between the sunlit areas and the shaded areas are multiple 100 degrees of Celsius. So this is a huge differential. And if you imagine you have a small rover on the lunar surface, and one side is heated up to 150 degrees or so, and the other side is minus 130 degrees, there's an immense thermal, tension in the material. The third, of course, is gravity. We all know that the moon is smaller and less dense than the Earth, and therefore gravity on the moon is also lower. The fourth one is the dust. This is especially challenging because the dust is so abrasive and so fine. And the last one is vacuum. There is no atmosphere on the moon, I said this already, and this is of course also a challenge. I will tell you why in a second. So let's start with the first one, radiation. The radiation effects on our technology can be categorized in two fields. The first one are single event effects, so high ionized particles that hit your electronic circuits and then may result in a flip of a bit and therefore change your entire software. And we attack this by having redundant systems. So you have 2, 3, or 4 systems that work identically, and when one or two of them drop out, the others can overtake, and we always know that something went wrong. The other effect is total ionizing dose. Total ionizing dose is basically, over a long time, you get this radiation from the sun and from the space background into your electronics, and over time materials degrade from this, or there is an electrostatic effect where you get different levels of electrostatic energy, or your glasses and your optics might get less opaque, and all these effects come from this long duration of radiation. And we can test this by putting our electronics into a test chamber. So what you see here in the bottom 2 pictures is a test chamber in Potsdam near Berlin, where we actually tested some of our electronics already for total ionizing dose. And in the chart here you can see the comparison between the radiation on Earth, on ISS, and on the lunar surface. And you can immediately see that on the lunar surface it's like more than 200 times the radiation that you experience on Earth, and more than twice the radiation on ISS. So that's also the reason why we use robots on the lunar surface as often as we can, because we don't want to put anybody into danger. And a realistic scenario would look like having astronauts working underground on the moon and only occasionally going outside to avoid these long radiation effects. The second lunar environment factor that I already mentioned is thermal. I already said minus 230 to plus 120 degrees. These are of course the extremes, but even on average you get easy 200 degrees of delta T. On the left hand side you can see a picture from Apollo by NASA. You can see the lunar roving vehicle in the front, and in the back you can see a shaded area of a crater. And this is interesting because there are some craters on the lunar surface which are permanently in shade. They are always in the shadow, no matter where the sun comes from. And this means that these areas are always super cold. And then in the same moment, you have these areas which are in the bright sun, and they here have these super high temperatures. Exactly. And the issue a little bit is we can't really test this here on Earth. We have some thermal vacuum chambers, as you can see here by ESA on the bottom right hand side. These can build temperature delta T's of 280 degrees or so, but you can't really emulate for the same environment. So that's why we have to do some analog testing. And one more fact I would like to introduce you to, some might know this already. One lunar day is about 14.75 Earth days. This means that twice a month the entire side of the moon that you are located at the moment is night, and then becomes sun again. This is of course because the Earth rotates within 1 month period. And this means that we can, if we are in one position, we can only have 14 days of sunlight. This is, for example, interesting for having solar cells that generate power. And then you have 14 days of night with deep temperatures down to minus 230 degrees. And it's quite harsh for batteries, for example, to survive this lunar night. So this is a challenge. One idea to overcome this is by going towards some specific points on the South Pole where there's always sun, for example. Moving on to gravity, I already said the moon's gravity is about 1/6 of Earth's gravity. This is actually not that big of an issue because less gravity means, of course, also less stress to our mechanical systems. So for a rover like ours, it's actually nice to design for a lower gravity system because then we can design everything lighter. But the issue that appears is that it's harder to test. And also, if we want to design for 1/6 of Earth gravity, this wouldn't work anymore here because it's designed for less. So what we need to do is to compensate for that. What we do here in Rostock, for example, is that we have a crane system where we lift and we counteract the forces of the gravity, and we call this gravity unload. But what we also could do is to simulate the moon's gravity on board of a parabolic flight or in a drop tower, as you can see in the first two pictures, or of course on the ISS or on a space mission like we just saw from the exploration company. And then to the fourth environmental factor, this is dust. I already spoiled a bit. This is a very challenging factor because on the lunar surface we have no erosion. There is no weather, there is no atmosphere. So all the particles that were crushed down from micrometeoroids and bigger meteoroids over millions of years, they stayed like this. There was no mechanism that rounded them down like through the rivers or wind or anything like that. And that's why these particles are so sharp-edged and abrasive that they really are a nightmare for mechanical systems. You can see, for example, on the left-hand side from Apollo 17 astronaut that the material sticks to his suit, to his shoes. It gets into every single bit of the equipment, and we can only test by analog missions. That's why we test, for example, here in Rostock or in volcanic areas where there's a similar rock composition as you see here on the right-hand side in these pictures. And of course, this material has their own challenges. As you see in the bottom right-hand side, it's quite sticky. So if you compare it to sand from a beach, it behaves more like flour or so. It's like super sticky material that clumps up and behaves completely different. And that's why we test for it. And now to the last environmental factor, this is vacuum. The moon actually has an atmosphere, but it's so thin that it's actually not called an atmosphere. It's actually called a super high vacuum. And we can only test for this by using vacuum chambers where we suck out all of the air. And to generate a vacuum that is as high as on the moon, we actually need to have 2 pumps running for multiple days to get every single atom of air out of that. And one fun fact is when the Apollo landings were, they observed actually they thought they observed an atmosphere, but what they observed during sunset was that there were like particles of lunar dust floating above the surface due to some electrostatic effects. And you can see this here. The sketch was done by some Apollo 17 astronauts from their capsule. So now that you know a little bit about the lunar environment, here's one more short video of our rover tackling the volcanic environment. We did this to test for several environmental factors. I would like to give you a quick slideshow, just 3 slides, of images to give you an overview of where we from Neurospace are at. You heard about Neurospace this morning twice already, so I'm keeping it short, just showing you we are testing already for dust. especially like our locomotion system and traction. We have tested for radiation. You can see this on the left-hand side. We did some school children education. You can see this with the robotic arm where children actually developed a shovel for it. And we did lots of teleoperation development in the recent time. Okay, this concludes my presentation. If you have any questions, I'm here to answer them. And if you find anything later, feel free to contact me through email.
Thank you so much for that really cool presentation. Definitely super interesting and complements the presentations that we had earlier. So yeah, that was great. Thank you.
You're welcome.
I have a question
Yes, please,
actually.
please.
So, I mean, one of the challenges you have is getting the rover dust proof. And at the same time, you have to test for the rover in a kind of a gravity-free space. Is making the rover waterproof and testing it in water an option?
Testing in water, I haven't thought about this, but making it waterproof is actually, it's the same dust resistivity you would need, but of course there's like, for example, the pressure, you wouldn't have any pressure on pushing stuff into your seal, so it's a bit different mechanism. But yeah, it's a similar kind of sealing you would use, yes. But testing it underwater, I have not heard of anything like that yet. But it's a good idea.
Okay, great. Super interesting question. Thank you, Georgia. Okay, we're just going to move into a very quick break before we introduce our next speaker. Thank you.
Hello.
Good afternoon, Giuseppe. Welcome to our live stream.
Thank you. I'm trying to share the screen. Let me see.
Okay.
Can I do now? Because before it did not work. It tells me that the screen sharing failed.
Oh, that's strange. It should be enabled for you. Maybe try again now.
Okay. Sorry.
No problem. Take your time.
This is because it said Chrome, Windows, and entire screens. I do Windows, of course, Microsoft PowerPoint. That's what I have, and it's not working.
Okay. Like, are you pressing the icon like next to the kind of video camera?
No, the video camera it was off. Here.
Oh, there you are. Yeah, next to the video camera, there should be another icon which allows you to screen share.
Yeah, that's what I've done.
And did you do it in window? Like, are you trying to share from a PowerPoint presentation or from a?
No, I have a PowerPoint behind this on the screen. So maybe I should do entire screen.
Yeah, so you can just share I think there's an option to share the window. It should be the middle option, and then you can just share the window of the PowerPoint.
It's failing.
Oh.
Still failing.
Oh, it's the security setting, and maybe he has logged out and logged in again.
Okay, do you know what to suggest then? So we do not have a presentation, then others we could do it. But, okay, so it is there is this lock at there.
I can try to send me my presentation.
Yes, that would be great.
Let me see, because I should have done before, but just in case I didn't do it. Just a second. Okay, I think this is the one. No. Okay, so I'm sending to Rob.
Okay. Just tell
I'll just wait for it to come through.
Okay, great.
Use mail drop. He said to use mail drop, yes. So.
Then Rob, if you have access to it, maybe you can just share your screen and then we can do it that way.
Oh, once it comes through.
Yes, of course.
Yeah, of course. So it is gone now. I'm sorry about this, but there's nothing I can do.
No problem at all.
Okay, so hopefully you should receive. So I cancel the screening, the share. Is that okay? The video you can see?
Yes.
As soon as you
So
get.
I've received it and it's just downloading.
Okay, fine, thank you. I think it's probably better.
Fine.
To do that.
Oh, it's taking its time.
No
All right,
problem.
there we go.
All right, then Rob, maybe you can just share your screen if possible.
Yep, and then I will mute myself so I don't have any sound coming through.
Yeah.
Just tell me when to move to the next slide. All right.
Thank you, Rob.
Yes. You may want to go to full screen. Yes.
Great.
All right. Okay.
Yes.
Shall I start? You want to introduce, or is that okay?
Yes, go ahead. You can start and also just provide a brief introduction about yourself.
All right. Okay. So, well, first of all, good afternoon to everyone. And my name is Giuseppe Rebaldi. I'm the president of the Moon Village Association. So first of all, I'd like to thank Neurospace for having organized this double event, if I might say, because it's what's so-called global events, and also they are participating in this telerobotics experience around the world. So twice as thank. And what I'm going to do, I'm going to explain basically what is going to constitute the Moon Village and what is the organization called Moon Village Association is doing, and how this is connected to the event of today. So if I may have the next slide, please. So, well, let's first find out what's going on and around the moon right now. So you can see here a list and the relevant pictures of all, let's say, the lunar mission which are operational right now. So this is not an historical piece of information. These are actual spacecraft which are operating on around the moon. So as you can see, most of the spacecraft are around the moon, which are orbiters, like the Lunar Reconnaissance Orbiter, very old, 2008, still going strongly. Chandrayaan-2 from India, the relay satellite from China, which has allowed to land on the dark side of the moon, or the hidden side of the moon, as well as basically the Korea Pathfinder Lunar Orbiter, which is the latest arrival in the lunar orbit. And then there are two more spacecraft, which is actually operational on the moon, which is Chang'e 4 with a rover U2 on the dark side of the moon, and the Chang'e 5, which has been basically collecting samples and bring it back to the Earth. So what this shows you is that there is a huge number of spacecraft already operational around, let's say, the moon. And what I'm going to show you is even more impressive. So if we can have the next one, is basically the number of spacecraft that they were launched in 2002. Basically, They were launched 4 missions. Everyone knows about Artemis, the US mission, which in an automatic way went around the moon. Then we had the Capstone, which is also a US microsatellite. And then we had the launch of iSpace Akuto R, which is the first commercial spacecraft from Japan. And then the Korean Lunar Pathfinder orbiter. And then we can see what happened this year. So with the next chart, please. So this year, in 2023, is the year of the landing, or at least attempt to land. Now, let me start with the first one, because I think most of you probably knows about the Apollo mission. And of course, those have been carried out by the United States with a very large budget, more than 50 years ago. In view of the, let's say, exponential technology, which are now available to many industry at the technology level, private organization like Neurospace, but like iSpace and a number of organizations in the United States, like Astrobotics and as well as others, there are basically building spacecraft which are landing on the moon. The fact is that the success rate of landing spacecraft on the moon is 50%. And so this has been seen in the latest, basically, landers, which have attempted to land on the moon in the last few years. We had a sequence, unfortunately, of crashes. We had an attempt from the Israeli private company, which crashed. Then we had the Indian with Chandrayaan-2, which crashed. And unfortunately, the latest one was in April, iSpace Akuto R, unfortunately, had a hard landing. So going to the moon is not easy, but is hard. So the next one in the line of attempting to land is Chandrayaan-3 from India. No, can you stay on? Yes. Which is going to be basically launched, it's been launched on 14th of July, and is going to attempt the landing in August. Then we are going to go to Russia next month, and then we're going to go to Japan, and you can see there other missions. So what all this brings about, the point I want to make, is that the moon is the place to be, is where all countries, or most of the countries in the world, developed and underdeveloped, wants to go. And so let's go to the next one, which explains you a little bit the concept of the Moon Village. So the Moon Village is actually not a village, as the name suggests. It's not a science facility. It is not an international space station. It is basically putting together all this effort from different countries around the world, exploring and use the moon in a cooperative way. So basically, it's a lunar community. And so that is the reason, if I can have the next chart, is what the organization, Moon Village Association, which I'm the president, has been created to bring together basically all these different stakeholders, which involves space agency, government, industry, international organization, NGO, and of course, the public, which is very important. So our organization is a member of International Astronautical Federation, and we are participating as a permanent observer in the United Nations, where we bring our concern and issues coming also from industry and from all other participants in our organization. It is also helped to stimulate virtual civil investment, bringing together also institutional members, and Neurospace, for instance, is one of our institutional members. So if I connect to the next one. So what I'm going to do in the next few minutes, I'm not going to go through all this because it's all different type of activity which the organization is dealing. You can see detail basically on the moonvillageassociation.org. I just going to flash some of them in my next chart. And in particular, I'd like to bring your attention to the International Moon Day. So the International Moon Day that we are celebrating today, and also for the rest of the week and next week, it is, as we can see, a project of the Moon Village Association. But you can see there is a palette of activity which we are carrying out together with the people which are joining us, and it is basically a voluntary organization, and it goes from technical to cultural to economical topics. So let me go to the next chart where I'm going to show you one of the activities that we have. It is a so-called Moon Village 2045 reference concept. So this is a group chaired by John Menkins, which is Vice President from the United States, former technology chief of NASA. And they have defined basically what is going to look like a multi-stakeholder settlement on the moon. We do not use the word moon base, but we use the moon village terminology to the south pole of the moon. When this work started, NASA had not yet selected the location on the south pole. And I can pleased to tell you when NASA did select 12 locations, those are one of them. So detail of these, you can see them on the website where there is also a report. So if I connect the next chart, please. So another topics which we are dealing with, next chart, please, is related to the economics aspect. Sorry, the lunar governance. So basically, it's important to understand that because of all these many missions going to the moon, there is a need to basically define what is called the rule of the game. So like when you drive a car, you have a code of conduct. So you need a code of conduct on the moon, because right now there is no coordination mechanisms. And so there is a need to create confidence building and way to act on around the moon, which are shared by all countries. And so for that reason, the MVA had created a global expert group on sustainable lunar activity, which in 2023 published a document, which is recommended framework and key elements, which is available on our website. And we have distributed this report and engaged in discussion at the level of United Nations in order to push for reaching an agreement on mechanism to coordinate a future mission in order to avoid that missions which are coming very close to each other, they will be creating problems and therefore creating harmful interference. So the lunar governance is one of the key elements that we are working on. If I can have the next chart, please. So it is a topic which we are also very much involved, and that is basically stimulating the participation of space emerging country to the lunar activity. And so we had made a call to the world, actually, and so we had received a number of applications. You can see the country which we are working with. What is the goal of this project is to help them to develop what is called a roadmap. So if I can have the next chart, please. You can see there, we do not go in detail, but you can see that each of those countries have identified a certain number of projects which they would like to work in. And what MBA is doing is providing expertise, is providing coaching in order to help to get basically developing country involved, even particularly if there are specific space agencies which are already existing. So we work also together with space agency. And as we can see later on when we talk about International Moon Day, there is a lot of interest in moon programs, not only in big countries, but also in small countries. You can see from Nepal to Thailand to Jordan. So if I can have the next chart, please. The next chart shows that we are also involved in the cultural activity. And so there is just some of the different, let's say, webinar that we have organized, and there are many available on our website. And so I think one of the, let's say, activities that we have been working recently is also basically the, let's say, the overview effect. Many of you are knowledgeable is how the effect that the astronaut going to the moon have by looking to the Earth. And then there is the deep space effect, which is being generated by landing on the dark side of the moon. Basically, not seeing the Earth, but just watching the open space. This gives a completely different perspective to humanity. You can watch all of these on our website. If I can have the next chart, please. So then basically the other important aspect of the organization is to be present in the different countries around the world. So you can see there we have about 50 national coordinators as well as 6 regional coordinators. We have, of course, also in Germany, we have a national coordinator, and there are a number of events related also to the IMD, which are taking place in Germany, beside, of course, this excellent event organized by Neurospace. So if I can have the next chart, please. So we have also very strong, let's say, importance to the young generation. So besides being present in the country to speak the language of the country, we have also now a website, a student corner. So if you're aware of, students which have some question, curiosity about the moon, you can certainly point to our website, where there is in particular a place where you can ask questions which experts from all over the world will reply. If I can have the next one, please. So then basically we come to where we are today, which is the International Moon Day. The International Moon Day was declared as such by the United Nations General Assembly, following, I must admit, and I'm pleased to see, this as a recommendation from the Moon Village Association, which was made in August. And I have to say, in a very special fast track, we managed to get the approval of the United Nations General Assembly only in 3 to 4 months, which is right now, it is something completely impossible because of the political situation. So we managed to get the approval at the end of 2021. Last year, it was the first event. What is basically celebrating is an achievement for humanity. It's on the 20th of July, but not necessarily only because of NASA. There's a lot of countries which in the past 60, 70 years, they've been having mission to the moon, and these include not only the United States, but all the countries. So the goal is to engage with the public, like we do today, in order to explain why there are a project, lunar project, what is the benefit for humanity. So I just want to say a couple of numbers. So last year, 2022 was the first. We had about 28 events in 23 countries. This year, as far as I'm aware, we have about 50 events in 42 countries. And so, as you can see, from one year to another, the number is growing. So we do hope soon to go towards 100, which is the number of countries which are presently available at the United Nations at the COPOS. And so if I can get the next one, but so that is nearly my last one. We have annual event, so I invite everyone that has not been to Japan to come to Japan, because we have a wonderful Global Moon Village workshop from 6 to 10 in 2 very picturesque and nice location in Japan. So you're mostly welcome. And I think this is, if I mean the next one, I think this is the last one. So I thank you for your attention. And of course, if there is any question, I'm ready to reply. Thank you again to Neurospace who have organized this event.
Thank you so much for that.
So is there any question?
Yes, actually, I have a question.
Please.
The last map you showed was really interesting, and you, if I got it right, like where the Moon Village is actually having activities is which were other parts on the map which were yellow, right?
Yes. Yes.
What's the reason for the other side of the globe being so inactive?
Well, some of them are political, to be quite honest. There is a big area, Russia. There is a big area, China. So there are some big areas around the world. So I think what, of course, the other is because they don't know. So it's up to us. I think this is an event which it is just a year and a half old. So it's not 20 years old. And so we need to let this propagate and let the people know. As soon as people knows, they are very enthusiastic, because you can have all sorts of events. You can have a big event. We just concluded just a few minutes ago the main event of this year, which was in South Korea. And so there we had quite a strong participation from Asia countries, of course, together with NASA. So there are 2 kinds of events. There is the main event and the global event. The global event is what you are doing right now. And so, but it can be even a smaller event. It can be also a meeting, a university, where there is a discussion between maybe students and the teacher, and you can webcast these around the world. So there are all kinds of deals. So the answer to your question is political on one side, but I will, let's say on the optimistic side is the lack of communication. So United Nations is not very active in this area. You might know that there has been a change of management in the United Nations. Finally, we have now a new director, which is taking place in the next week or so. And of course, we do what we can as an organization. Of course, we rely on you guys to propagate the words.
Okay.
Okay.
Thank you.
Great,
And
thank you.
last question, the symposium in Japan,
Yes.
what is it actually specifically about?
Well, we have every year since 2017 an annual workshop where we invite all major stakeholders, so big space agency as well as a small country, to tell us what are the challenges of cooperation and on the technological side. But it's also a moment of time to report the findings on the different activity that we are making. So basically, all the different work, which I just showed very briefly, they will be reporting where they are. And so this is a place also for an intake of information from the other stakeholders. So it's a moment of time where we bring together, let's say, the other stakeholders as well as the people working in the MBA to try to basically explain to each other and hopefully to try to mix information and create more cooperation, which is, of course, the goal of the organization.
Thank you.
Okay.
It was really great.
Great, thank you so much. So without getting too off track, so our next speaker is going to be Johannes Schumacher. So yeah. So you are welcome to introduce yourself and then also share your screen if you have any accompanying material.
Yes, hello everyone. Good afternoon. This is Johannes Schumacher from Celestial Space Technologies, and also from my side, thank you to Neurospace for the invitation to speak here today. It's definitely a very interesting, a very hype topic at the moment, the lunar economy, and we're just happy also to contribute to this event and to this industry. I have some slides prepared. So give me a second to start sharing.
Yeah, exactly. You're just sharing your screen. Great.
Okay. So is my screen visible?
Yes. Oh. Yes, but we can currently see just the Jitsi.
Yeah. I need to switch to the presentation.
Yes, we're able to see.
Perfect.
Great.
Okay, if anything comes up, just interrupt me, then I try to adjust this. Yeah, but in any case, let me just start with giving a brief introduction of myself and the company. So myself, I'm one of the founders, along with my colleague Mayank, of Celestial Space Technologies, which is a rather early stage startup located in Germany. We started a project in Berlin about 5 years ago when we were still studying at TU Berlin. So this is the heritage of this project. And by now the company is located in Nuremberg in Bavaria in the south of Germany. And our focus is satellite antennas, or rather telecommunication RF engineering, especially for the space industry, for satellites, but also for other potential spacecrafts. And basically, our capabilities are in designing any antenna for any size, any frequency, operational range, and also any mission range for the satellite. We've done quite a bit of work on patch antennas. And also at the moment we are designing as part of an ESA, part of a consortium which is under ESA Artis, a larger antenna which is a 1 square meter deployable reflect area antenna in Ka band, also for CubeSat missions. So and since our our expertise is on the RF and telecommunication side. I would like to discuss the lunar topic also from this angle, and especially of how we with our antenna technology want to also aid enabling the lunar exploration, but also the growth of an economy and data-driven missions. So this could be interesting. But yeah, let's start with something rather general about the moon. I'm sure we've heard about this already multiple times. But there's, of course, as we all know, a bigger vision for the moon, and this goes into having a permanent settlement, permanent human settlement on the moon. And there's some estimations that this could start in 2030 already with 40 people, but then grow to 200 in 2035 and already 1,000 people living on the moon by 2040. So there's definitely these big ambitions, and we also know there's many missions scheduled for the moon. From a private side, of course, we have the US returning back to the moon as part of their Artemis program, and but also China in the last years launched a rover to the moon. India as well, I think also United Arab Emirates also planning to do this, and there's also many private missions as well. But of course, if we want to sustain a real human settlement on the moon with hundreds or maybe thousands of people, there's some requirements. And so what I see is that there's various terrestrial industries which basically need to adapt and transform, or rather transfer the industry also to the lunar economy. And this is of course mining. We need resources from the moon. We need energy there. We need communication, navigation, very very important for everything. I think also this will be a big research hub, moon and moon orbit. Of course, if there are people, medicine will cannot be missed out, and all of this. All of these topics are also logistics topics, of course. But to realize all of these different industries and then use cases, the satellite technology, we see this still as crucial. So satellites in lunar orbit, and of course they are often communication satellites, especially important for the moon because it has the dark side where relays are constantly required. And of course, then telecommunication is just as important for on the lunar surface to coordinate everything that's happening there. But there's also a big potential of commercializing lunar data. I will talk a bit more about this in detail with maybe also a few unforeseen applications, but they're certainly there. So, and we can talk about telecommunication in all aspects of the lunar economy and of lunar transportation. So that is certainly relevant, and this is where we come into play. So I mentioned before we have especially worked on patch antennas. Patch antennas, maybe briefly for those that don't know, those antennas which are basically in the form of a patch, so very flat. Typically, for example, we have an S-band patch antenna, which is roughly 9 by 9 centimeter and 3 millimeter thick. We also have S-band and X-band and C-band and various others that we are working on. So we have quite a bit of expertise in this type of antennas. And traditionally, they're based on PCB technology, also as when it comes to the material and the manufacturing. And one system that we are working on right now is first of all to make these patch antennas transparent, so that in the second step we can integrate, for example, solar cells into this transparent antenna. So it would be a transparent solar panel integrated antenna. And now this is interesting, of course, for satellites, which they have limited space available, limited available power. But if we talk about, especially big constellations across multiple orbits, they have an interest to extend their communication capabilities into all directions, which means ideally for them, they have antennas and solar cells on every side of the satellite, and they can do so. So that's also a topic for inter-satellite communication links. And then in the next step, we don't want to have this technology only as a surface-mounted subsystem, but also as a deployable subsystem. So what we are envisioning is to have deployable solar panels, which have multiple antennas with different frequency bands also on them. And this is something fairly interesting, especially for deep space missions. If there's communication requirements over with different types of data, over different frequency bands, as we will certainly also see on the moon. About this technology, so there are similar concepts, of course, but mostly in research. We've not come across anything similar which is commercially available. We did some a more detailed analysis on this. There is maybe other transparent antennas that integrate some solar cells, and there's also multi-layer systems, and there's mesh surface antennas on top of solar panels, mostly described, as I said, in research, but all of them they have disadvantages. Typically, it is rather high cost, and it is complex and takes therefore a lot of time to develop, and maybe also it's a delicate system. So with our concept, we try to eliminate all of these disadvantages, and most importantly, bring this from research into the industry, into missions, so that satellites, especially small satellites, in terms of their power availability and communication capabilities, they can also go to deep space missions. And so currently where we are with this, we have the first two prototypes of these systems. On the right side, you see our first prototype of this, which was still semi-transparent. The second prototype for the transparent antenna that we have by now is actually more than 80% transparent, including the radiating patch, which is very important if you want to integrate a solar cell behind this, because of course it should be as transparent as possible. But we have more than 80%, so this is already very good. And we have the first integrated prototype, which was tested in a lab environment in terms of its RF properties. So the antenna worked quite well, and also the transmission to the solar cells was verified in lab as well. So the solar cell also worked. So we had the first proof of concept with this, and now we are looking to develop this further, and ideally also bring this to missions directly. But getting back to the moon, so how does it play into the moon, and where do we see our spot in the moon? Well, if we look at the transportation value chain, starting at Earth, of course, anything that needs to get to the moon, needs to be manufactured and tested. Then there's companies that focus on the launch, and of course, then you have the transportation between orbits. Eventually, many missions will also land, of course. But then you have also these topics which are fairly downstream, such as operation and transmission, and the data signals and processing. And where we see our spot is the operation of payloads in lunar orbit, because based on the highly integrated antennas and other subsystems, we plan to develop a proprietary satellite, which is then able to offer in-orbit demonstration missions around or in lunar orbits. And there's definitely a requirement for orbital payloads also on the moon, because as I mentioned, many satellites, they are communication satellites, they are relay satellites, especially for the dark side. There might also be, for sure, there will be a requirement for experiments such as on ISS, and of course prospecting. So surface data from the moon for mining operations, just to name a few. So there will definitely be a need and a requirement to put various payloads into the lunar orbit, and this is where Celestial sees its position to enable this and offer this this service. Moving on to the data part that I mentioned before, because when we look at pretty much all terrestrial industries, we see an increasing relevance of software and data. traditional products which have been hardware defined are becoming more and more software defined. And I think this will be very similar also with the lunar economy and about the moon. Moon data will be very relevant, and there's three different categories. First, there's telemetry data, which can focus on two forms: on exploration data, and also with terrestrial applications. So the use cases here are very clearly, of course, lunar exploration technology development, but of course also the commercial sector, the development or the advancement of technologies in non-space industries. So, for example, the telemetry data from mining and boring on the lunar surface. This could be also interesting and relevant for mining and boring operations on Earth's surface, right? The second part, of course, is environmental data, and this is your classic space resource utilization topic. Of course, there will be exploration missions, and those will be prospecting exploration missions, especially for mining, because we are going there as the moon, primarily also for resources, which is water from ice, for propellant, right, to go further into deep space, but maybe also helium-3, which maybe in the future is, which on Moon is a lot, on Earth not so much, but we have an interest in this for nuclear fusion to solve also our energy demand for Earth. And then there's a third category, which is entertainment data. Interestingly, because which could be images, videos, recordings, etc., etc. But what is meant here actually is entertainment for Earth, because when you go to the moon increasingly and you have images and videos, that's interesting for the entertainment industry here. This can be used in videos, in documentaries, in movies, maybe also in video games. So there's a big potential also for lunar data as entertainment data on terrestrial applications. Well, of course, if we have people on the moon, they won't work all the time. So at some point, they also need some entertainments. So there's big potential also in this regard. And as you see here, all of these data-driven missions, so this data needs to be transmitted somehow, where again the telecommunication aspect comes into play. So I have a couple of more slides about the company and what we plan to do. We envision to develop our technology, our company, or various phases. What I mentioned before, the integrated antennas. This is also interesting for low Earth orbits, in Earth orbit. As I mentioned earlier, we talk about mega constellations across multiple orbits. They definitely want to extend their communication into all directions and also communicate inter-satellite and not only between ground station. It's actually relevant to make these mega constellations efficient. We want to move on to deployable integrated systems, which is then interesting for Moon, as I said, but potentially also to go beyond, go to Mars. So I think my time is coming to an end. So I just have 3 more slides. And so as a company, what we plan to do is develop what we are right now is a subsystem developer or supplier, but we want to move towards becoming a satellite integrator and eventually a satellite operator. As I said, based on our own proprietary satellites, especially in LEO and also MEO, but also lunar orbit. Here's a few impressions from the company. Top left side, you see my founder, Mayank, and myself. And we've been active now for a few years and have developed quite a few antennas, 2 of which have been launched to orbit actually this year on Transporter 7 and 8. One of our S-band antenna and one of our C-band antennas. So this is more or less a reiteration of what I said before. Our goal is definitely to become one of the the #1 supplier for deep space satellites, starting with the moon, as I outlined previously. So with this, I'm at the end. So thank you for listening. If there's any questions, feel free to let me know or contact me afterwards. We're always happy to talk. Thank you.
Thank you, Johannes. Yes, please. If anyone has questions, this will be a perfect moment. Okay. And thank you very much, Johannes, for your wonderful presentation. And we will just go over right away to Moritz. Are you there? Can you hear us?
Indeed, I am. Hello.
Hi, perfect. Welcome. Please feel free to say something short about yourself and looking forward to your presentation.
Sure. My name is Moritz Förster. I'm currently a master student at the TU Braunschweig. And I'm mainly here because I'm part of the Experimentalraumfahrt Interessensgemeinschaft, or short ERIC, which is a student association of the TU Braunschweig going into aerospace. And I want to show you a little bit about it. Yeah, that's basically already it.
Thank you.
All right, let's see if I can get this image here to work. There we go.
Perfect.
There we go. I hope you can see it all well.
Yes, we can.
All right, so I'm gonna just jump right in. As I said, I'm from the ERIC, and today I want to tell you a little bit about our unofficial motto of taking the lecture hall to space. So let's start in the beginning. There we go. The first question, obviously, is who are we? I already mentioned Experimentalraumfahrt Interessensgemeinschaft, which in English would equate to aerospace interest community. It doesn't quite flow off the tongue that well in English, but oh well, we're German anyway. Currently, we are about 30 students, and we have several projects going to aerospace, high altitude research, satellite research, rovers, etc., which I want to show you through a little bit if I hope I can make it in time. So the question obviously would be, us as a student team, what do we actually do? As a student, some of you might remember, we mostly study, we sit over books, we get a headache, or just sit in lecture and hear dry facts about some topic we are more or less interested in. That is definitely what we in ERIC do not want to do. I mean, obviously we're all students, so we are still doing it by the side, so to speak. But in ERIC, our main focus is on actually doing things ourselves, experiencing things ourselves, designing, crafting, and getting to the goal of a project on our own terms, and obviously collecting a lot of experience and know-how on the way. We are cut up into different subgroups. A group that goes into mostly experimental rockets, which we will talk about, and the other group is mostly high altitude research, so rovers, satellites, weather balloons. And first, I want to also mention that obviously, while you will hear a lot of work-related things, so to speak, we're still just a student group, so we will also sometimes take a hike somewhere in the Harz, or on the bottom picture when we launch rockets somewhere off in deep, deep Sweden. We also have a little party, or we actually also offer student team, or not student team, more like school student teams to come to us and learn a little bit about rockets. We call it mehr Schub-Scotty, so more thrust Scotty, just to get them into the aerospace engineering topic a little bit. The four main projects I want to show you today are Unity, Create, Ortos, and iLoop. And we're basically starting down at the ground level, and we're going upwards. We're launching a rocket, so to speak, for our project Unity. In Unity, we're building experimental rockets. So the first question would be what would be an experimental rocket? For example, this is one of our latest, or not latest launch days, but last October, our last launch day, we had with the Bears a team from Berlin, from the TU Berlin actually, and if you look into that picture, the question would be what of these rockets that are being held is an experimental rocket. On the left, you see a silver-ish one held by Heiko. That would still be a model rocket. It's mostly built out of cardboard, and it flies with rather small rocket engines, just a few 100 meters high. And then on the right hand is from the Bears team a quite large rocket, and that's kind of on the verge. There is not a straight line that says this is a model rocket, this is an experimental rocket. Rule of thumb is if you're using composite fiber and if you have a chance to actually get it close to the edge of space, then it's for sure an experimental rocket. And that's obviously also where we are trying to go with our Project Unity. The idea in Project Unity is so far in the more than 20 years Eric has existed at the TU Braunschweig, most rockets were built as a single system. So you build one rocket, one electronics, one engine, and they fly together, and then you build another one. And now we want to do it modular. So we build a electronics bay module, we build an engine module, we build a recovery segment module, and they are completely interchangeable. So you can fly with different engines, you can trick around with electronics, etc. And we don't have to build one rocket each time. For the engine, we are developing our own hybrid rocket propulsion engine. For the ones who are not too familiar with it, we obviously have liquid propulsion on the one hand, where we have a liquid oxidator and a liquid fuel, which come together and burn. On the other hand, the solid fuels, where you just have all the chemicals mixed in a solid state and it burns like a fireworks rocket. And then the hybrid fuel is just a solid fuel and a liquid oxidator, which come together. So 50-50 of both worlds. Our hybrid rocket engine is called Hydra 5. As you can tell, we have built more than one so far in our long time in the Eric. The current one is running the fuel HTPB, which is similar to the rubber which is used for car wheels. And we're using N2O as our oxidator. We are using a steel or carbon fiber combustion chamber, and we can get about 1,000 newtons of thrust for 7.5 seconds out of it. We test our rocket engines usually in Traun, which is a DLR location not too far from Braunschweig. We are allowed to set up our computers, our fuel tanks, and our test stand there, and then actually run our engine as if it was in a rocket, just horizontally, to check out all the systems, to check if our procedures fit, if all the numbers are right. Then we jump on to the electronics of our rockets. We build them all ourselves. On the left hand, for example, rather old electronics which don't fly anymore. Our current latest electronics for Unity is also a little bit down the modular road. So we have a sandwich out of different PCBs, which do different things. We have a power supply unit, we have a radio unit, we have a computer unit, and we can stack them the way we want. We can add things if we want to add things or leave things out and still be able to fly, which is rather nice, especially as a student team. When new students come in, you can just say, okay, build something and then stack it in if it's fine enough to fly. And since we still don't go into orbit and are not looking to do so rather soon, or probably anytime, all things we launch will come back down. So we need a parachute. We are using mostly mechanical deployment of a parachute because we have bad experience with explosives or any type of explosives to deploy the parachute because it's badly testable. On the right-hand side, our full electronics and parachute system, we can try over and over because it's based on just stringing up a few rubber bands, and we can actually be very confident that it will work when we integrate into our rocket. The fully integrated rocket then is shipped out, so to speak, to a field close to Magdeburg, where we have a lot of space to fly. We set up all our electronics, we set up all the stuff inside the rocket, and then obviously launch it after going down our 70 pages of checklist. And it usually looks quite good. For example, on the bottom left is a little bit older rocket we launched at the exact spot I mentioned. On the right-hand side, we flew in Poland. Top, we actually were in part of the DLR's program called Stern, where you get funded to build these rockets, and we could afford to fly in Kiruna in Sweden. Usually they also come down on a parachute, hopefully. Sometimes they don't. This is Phoebe, which is our first rocket in the Unity program, which we flew last October, and the parachute did not deploy. This also happens. It's actually kind of usual for a student team, so we're not the only ones who are having trouble getting it done reliably. And often then it's a question of digging to get all of the parts off the ground, because that rocket has quite some speed when it comes back down. We call it Spatenbergung, so shovel recovery. We also had the bad luck in that case that our electronics were smashed enough to be still recognizable, but we still lost all our flight data. So finding out what actually happened and what went wrong was a question of putting together all the parts we collected and trying to figure out what happened. And at this point, we are quite certain that it was troubles with electronics, which switched off in conjunction with troubles with our umbilical cord. So the cord that the wire that hangs out of the rocket shortly before launch and gets pulled when the rocket leaves the what's it called? The pad. There we go. And our next launch actually was this Saturday. We could not fly because of troubles with our engine, but we are quite certain that we actually fixed that error. So if our engine would have worked, we would have landed safely. If we were up there, if we were ever in orbit, we would be able to run our next Project iLoop. The idea of Project iLoop is to research additive manufacturing in space. It's rather new. We are working in conjunction with the Institute for Space Systems, which we of the TU Braunschweig, which we're basically in the basement of. And the idea is to build a 3D printer with an infinite z-axis. So you have a usual 3D printer. Basically, you tilt the gantry with the hot end on it to a certain angle, and then replace the print bed with a conveyor belt. And then if you print on an angle on that conveyor belt, you can just scroll away all the stuff you already printed and basically have infinite space in that one direction. The idea being that you can print very long trusses for anything you would like to assemble in space. We did a master's, was it a method? It definitely was some kind of thesis to figure out if that is somehow possible, and they came up with the fact that it could fit into a 1U CubeSat, at least the printing unit, so that's 10 by 10 by 10 centimeters. At this point, we're quite certain that's very optimistic. Also in that thesis, the plan was to fit it into a 3U CubeSat. We are still far off from that. The project, together with the DLR, is running until the end of 2024, so 1.5 more years. And at that point, we want to present a demonstrator that is also vacuum ready and prints peak, PEC, and PI, so thermoplasts that can actually be used in space. And, well, research is underway, so to speak, and we should see quite some cool stuff from that in the future. On the way back down, basically dropping, we would talk about CREATE. It's a REXUS experiment. REXUS stands for Rocket Experiments for University Students, another program from the DLR where you get sponsored to fly your payloads on a rocket. They fly from Kiruna on these rather large rockets that go up to 130 kilometers in altitude. And on the way down, you have about 30 seconds of microgravity. CREATE stands for Carbon Reinforced Additive Manufacturing Technology Experiment. The idea here is to figure out how to best slice carbon fiber into a usual 3D printable PLA filament. The issue is if you do it at well, so to speak, room temperature, or not temperature, but at room gravity, you have lunkers and voids because the PLA is a non-Newtonian fluid. So it will get less viscous, more viscous, less liquid when any force acts upon it. So the idea is if we do it in low or zero gravity, it should be more liquid and better bound with the fibers inside. For that, we have quite a simple experiment. Number one would be where the PLA is stored at 0.7. This is our extruder, just a standard 3D printer extruder, where the number 5, which is the carbon fiber, is being sliced in. It gets cooled on the other side of the hot end and then pulled into another storage space. And then after the launch, when the rocket landed, we take it out and evaluate if it actually worked. The CAD of it to fit into a rocket looks a little bit like this, and it is quite close to what the current state of the project is. The idea was to fly it this summer, but due to politics and Kiruna being rather close to our best friend Russia, it's a little bit iffy when the rockets for students will launch again from there. So currently it's planned for next summer, but we will have to see when it actually happens. Last but not least, if we ever landed, hopefully on Mars, we would have our project Ortos. Ortos is our rover to take part in the European rocketry, the European Rover Challenge. Sorry, mind all over rockets, which is a rover challenge that is held annually in Poland. About nearly 100 teams from all over the world take place. It's called European mostly because it takes place in Europe, but it's not limited to teams from there. The goal is to build some kind of rover that can move around, orientate itself, and do a scientific task. All that on a so-called Mars yard, which is an area they build up in Poland where they dig up mounds and lava falls, so to speak. It's quite cool looking, just to emulate a Mars yard, a piece of Mars where you drive around. Our rover Ortos, it's a little bit difficult to pronounce in English, is a little bit of a classical design, 6 wheels, and a arm in the front and a big mast in the back for the cameras and all things that need a little bit of height to look around. Our science task is looking for life. We are trying to detect adenosine triphosphate, which is quite important to move around. It's a very important part of burning sugars and stuff in our muscles. So where it is, there should be life. And we are using the little bugger on the right bottom, which is luciferase. It's a molecule. When it comes in touch with the ATP, it will emit a single photon. And basically, we just need to find photons if we mix these two. For the science task, you also get a piece of real Mars map sent in beforehand, and you have to find the best way over that map, where to look for life, where you would go land, etc., and send that back to them. And then, similar to the place you looked at on that map, the Mars yard is designed to look like a piece of Mars, also with different topological design parts, like a crater, a volcano, and then you have to redesign basically your path to find where you would look for life. Looking for life then looks like this. We have a vacuum cleaner which sucks up some kind of probe, some surface material, and we filter it out of the air and throw it into a dark chamber where it is mixed with the luciferase. And obviously, if we mix it and we see photons, then we know, hallelujah, we found life on that Mars yard in Poland. In our actual rover, it looks a little bit. It looks like the thing on the left. It's just a tube, and then the black boxes in the back are all the closed-off areas to not let any light in, because that would obviously fail our measurements. Also, front and center is the dual camera we are using to orientate. We make a 3D picture of the entire world, a 3D map, and then we use cost mapping to figure out the best way. So if it's difficult to navigate over some area we found, then it gets a high value, and low value would be a better path, and that's how then we orientate, not orientate, how we move around on said Mars yard. Also part of the science task is operating some buttons and pulling some plugs with some kind of robot arm, which we built ourselves as well. It looks a little bit like this. It has two little rubber fingers, can move up and down. It has 8 axes, I think. No, 6 axes, I'm sorry. And personally, my complete favorite is the fingers of that thing are 3D printed out of a rubbery material, and they have impressive dexterity, just to be honest. One of my favorite projects in Errant. We then went to the ERC 2022, drove around on our Mars yard, did our tasks, and actually ended up winning the science task. So you can win different areas of the competition, and then the whole competition. We only won the science task with our ATP experiment, but it was still quite a good achievement. Then, last but not least, I want to mention we also launched some weather balloons. It's rather seldom and smaller projects compared to the long-term projects I showed you just beforehand, but still fun from time to time. And obviously, you might have noticed our top banner where all the headlines were is also one of our beautiful pictures from weather balloons. It's more a relaxed mission, so to speak, when we launch these. Also, big thank you, obviously, to everybody who helps us financially or with know-how or material. There's a bunch of companies that help us out actually realizing all these projects. And yeah, you're always very glad to have helping hands with us. And yeah, that's it from me so far. And I am very happy to answer any questions you might have or confusions I could clear up from my 20 minutes of motivated rambling. So
Thank you very much. Thank you very much, Moritz. Does anyone have a question?
they're all overrun with interesting things.
Okay, well, in that case, I guess we can just keep on with our final speaker for this kind of slot before we take a little intermission again. So our next speaker is Amrit Suresh. Yes, great. So yeah, you can just go ahead and provide like a brief introduction on yourself, and then also if you need to share your screen for any other materials, then yeah, go ahead.
Hi there, can you hear me?
Yes. Yes, we can hear you.
A thumbs up would be nice. Can you hear me?
Yeah.
Oh, good.
Yes.
Sorry, the interface is in German, so I'm just guessing what is share.
No worries. The button next to the camera. So there's a camera icon, and next to it, you should be able to see. Oh, perfect. Yeah.
So, hi everyone. My name is Amrita Suresh, and I'm currently pursuing my PhD at the University of Bremen, and I'm here to represent the Deutsches Forschungszentrum für Künstliche Intelligenz, the German Research Center for Artificial Intelligence. And the center that we have in Bremen is called the Robotics Innovation Center, or the RIC as we call it. And I come from the team Space Robotics of the RIC. I have an MSc in advanced robotics, and just to tell you a little bit about me, my research interests are currently multi-agent systems, outdoor exploration, collaborative mission planning, decision-making paradigms, and space robotics in particular. Though I also have experience working with autonomous vehicles and other kinds of robots as well. As I said, I'm currently pursuing a PhD, and it is in the topic of heterogeneous robotic teams for outdoor space exploration. And yeah, my other interests are philanthropy, a lot of music, and traveling in languages. And yeah, so here's also my contact details. So if later after the presentation somebody wants to contact me, feel free. Coming to the presentation, well, as I said, I'm from the team Space Robotics, and our team leaders are Marko Jankovic and Dr. Mehmet Yüksel. And here's also a link to the space team. I can put it later on the chat again for your reference. Well, coming to what we do here at Team Space Robotics at the Robotics Innovation Center in Bremen. Well, we have a diverse range of projects in applied AI and robotics, particularly space applications, and which include on-orbit operations, planetary exploration, orbital exploration. We also develop and design our own robotic systems. Implementation of AI-based software algorithms, of course, since it's the TFKI. We also have projects that deal with the integration of physical systems and software and testing facilities here at the RIC. So as you can see in the images, I would like to particularly point out to two of these images here because the other two will come in videos that I will show you shortly. So at the bottom left, you can see that there is a small, there's a system that looks like it's underwater. Well, it is because we have a maritime exploration hall, which is a 1,300 meter square testing facility. And apart from, of course, underwater robotics being tested there, we can also test our space robots since it can simulate low gravity scenarios. And on the top right here, you can see that there is a virtual reality simulation lab, which we call the Cave. And it's a 3D test environment. It's interactive, and one can remotely control and monitor outdoor missions. All right. On the top left and bottom right are two projects which are very interesting, and I will show you videos in the next slide to explain to you what I mean. So apart from that, of course, we have pre-qualification of robotic key elements, system evaluation, and a lot of scientists working on these projects, of course. All right. So, as we know that space exploration has become more and more interesting to a lot of space scientists now, and we can explicitly see the benefits of exploration beyond the Earth, also for scenarios that occur on the Earth, right? Of course, we can use similar systems, algorithms for search and rescue missions, for outdoor resource localization on the Earth as well. And so it is particularly interesting to us to explore the Moon, which is the closest other orbiting body to the Earth. And then, of course, there's Mars. As we know that the European Space Agency, ESA, has now has recently said that we would require multiple launches to deliver samples from Mars under their for robotic exploration, and therefore we are also working on projects in collaboration with the DLR, with ESA. On the left here is a video which I will play for you that comes from the project called Cooperative Robots for Extreme Environments, or COROBEX as we call it. And here we develop and demonstrate technologies for multi-agent robotic teams. Coming to, well, the most interesting part for me. So the primary application of this kind of a system is for exploration of planetary surfaces, focusing particularly on hard to reach areas like skylights, caves, right? So we use here three types of robots, the Sherpa, Asgard, and Coyote 3. That were designed here, and I can play the video for you here. All right. So the overall objective was to design and demonstrate a robotic exploration system with these three robots that are performing a cooperative tasks. As you can see, the one on the far end is the Sherpa. And here, closer to us, we have the Coyote and we have the Asgard robots. And you will shortly see what they do here. So here the idea is to explore this under surface lava tube. So as you can see, this kind of a lava tube is very hard to reach. It's dark, communication could be a problem, and we don't know how far these could actually extend over kilometers. All right. As you can see, the Coyote is tethered and it is slowly suspended and brought down into the lava tube. And after it lands, it can move ahead and explore, continue exploring, and you can visualize, of course, using the simulation tools, and you can visualize this. The perception data and the information that it gets from the exploration of the lava tube. And so this was one analog test mission with these rovers. So now we covered cave exploration. Similarly, we also had a project called Transterra, which was for the application of planetary exploration. And the field trials were conducted at Utah in the United States. And here we can see another video from Transterra. So just to give you an introduction, Transterra was a project with four main modules. One was the Sherpa TT rover module, which is, as you saw, a walking driving rover. Coyote 3, again, we also saw that in COROBEX, used for terrain that is very unstructured. And we also have a base camp, some payload items, and a mission control station. We can take a look at the video of the trials. It was conducted over 4 weeks in Utah. And the systems were basically tested over their locomotion capabilities, over the autonomy and the overall mission scenario, parameters related to the mission scenario. So here we see that there is there's a payload. So we use a kind of cooperative mapping algorithm here with rovers. So they're constantly in communication and sharing information. So what is really happening here is that they are trying to build a sort of logistics chain. So the Sherpa acts as an exploration and sample acquisition rover. The Coyote 3 takes the role of a shuttle system, right? And so what it does is it collects sample containers, as we saw in the video, and it transports them back to the return stage. So here you can see that the Sherpa is continuing to explore and the Coyote acts as the sample collector.
Okay, excuse the last. I'd like to do a question round before I go. So,
The mission command and the control, it lies at the ground station, ground control station. And during these tests, the ground control station was here at Bremen. And we used satellite links for communicating with the systems at Utah. And here, as you can see, the Coyote has the 6 degrees of freedom arm, which collects samples from the exploring robot or rover Sherpa and deposits them at the return stage. So here we can see what is happening at Bremen and what is happening at Utah parallelly. As you can see on the right, there is a person using an exoskeleton, and this is the cave or the interactive 3D test environment, the virtual reality lab that I had mentioned earlier. And from this cave, one can use an exoskeleton, a wearable exoskeleton, to operate on the systems for direct control over the systems that are at Utah.
Es ist immer wichtig, dass man denen zuhört und den lernt selber, wenn keiner eine Frage stellt, dass man selber eine Frage stellt. Ja, dass immer die nicht ohne Frage eine Frage am Ende zu beantworten. Ist halt. Es sei denn, es ist die Zeit, ist dann jetzt schon um oder irgendwas, wir haben halt Zeit. Deswegen ist
All right. So as you can see that there are multiple projects and multi-robot systems, and this is the project that I'm working on right now, which I will just take 1 minute to explain what that is. I hope I'm not running short of time. So the project that I'm working on is human integrated swarm exploration, which basically takes a multi-robot system, a swarm of robots, and to develop an integrative framework where we integrate the robotic system with the human in the loop, and some mixed reality simulation and visualization tools for the human, and also integrating semantic communication between the rovers and between the rovers and the humans into this. Of course, and we're working with two other partners from the University of Bremen, and this project is targeted to design a framework that can be used for further adapted and used for long-term missions with larger teams of humans and robots. And the vision that is kept in mind is extraterrestrial settlements in the future. So here is a small video that I recorded from the simulation environment. So there are 5 Coyote 3 rovers, and their mission here is in this Mars-like environment is to find these cubes of different colors, different patterns, types based on the mission specifications, and to strategize this exploration to reduce redundancies, to reduce the energy consumed, since resources are quite scarce in such an environment. So as you can see, they start by going in different directions. For now, we only have 5 Coyote rovers. The idea is to extend it to larger teams. All right, that's all from me, and thank you very much.
Okay, thank you very much. So thank you very much. So are there some questions?
I have a question. I noticed in your videos there that the rovers all had a diverse array of wheel designs. Is that something that you're actively experimenting with, or was this more of a stylistic choice for costs, or what was your design process there? Hello?
I think Amrita has currently problems with the audio. She just wrote me. But maybe I can shortly jump in here for the questions. So we do have different wheel systems for different purposes. So we saw in the Utah video that, of course, there were some stones of different granularity, and therefore these star wheels are more suitable to also overcome, let's say, medium-sized rocks. Of course, from applications, I mean, we're from Team Space, but also there's, of course, the terrestrial team. So if we do applications in industry, we go with a more like normal shaped wheel there. We also have locomotion systems without wheels. So we are exploring different kind of mobility or, yeah, navigation systems as well wheeled, but also like legged systems there.
Okay, cool. Thanks.
You're welcome.
So are there any questions from this round? So, okay, so I have one question. What was the challenging part? Which one? Which design?
for you?
Okay, seems like this is
Yeah,
actually 21st century, no worries. Do you mean like design of a wheel or a specific system, or the design of the overall mission with like multiple teams and robots?
Oh, both is interesting actually.
Then I try to answer both of them. So the systems usually are always very task specific still. I mean, we all would love to have the system which can or that can do all the tasks, right? Cleaning our house, cooking, making pancakes or whatever. But of course, when we acquire projects, they're usually targeted to a certain yeah, application, and therefore also if we design new systems for these projects, they're application driven. Can range from exoskeleton for rehabilitation to humanoid robots as assistive systems, either be in industry or extraterrestrial for infrastructure installation. So that basically really depends on the purpose where we're going to. For the rovers, we have different kind of also mission scenarios. So there's one project that we have running, which is trying to have a micro rover, which can sort of like, let's call it, survive the extraterrestrial conditions, be it just from heating, being having like solar or photovoltaic panels to be most autonomous. Whereas others are more like proof of concept missions where we say, okay, we don't take into consideration all the real criteria which we would have in the physical world, like all the harsh conditions in space, but where we want to see more on the software or the conceptual area if we can do this collaboration with either human or another team, so robot-robot teaming. So there again, it depends on the mission. As my colleagues Masush already presented, is for this lunar cavern and lava tubes exploration, we wanted to have like a system with different rovers which can handle different parts of the task. Let it be sort of like the exploration of the lava tube, or then the tethering of another robot down the lava tube. So there we have to see like what systems do we have and what do we require, and then sort of like compose the team together.
Okay, yes, that's interesting to hear. Of course, we do also have our challenges in all these things and experiences. Of course, it starts with where the mission to go and how to create an overall general system. So it is, of course, an open platform for robotic application, and now you have so many different versions of it. So that's very interesting to see, and also it's based on mission and the complexity. So yes, great. We were also there at at your facilities, and we already are there today at DFKI. So we're quite familiar with some of your rovers and also know some of your teams. So yes, thank you very much for giving us insight here. And so
You're welcome.
nearly at the end, but at 5 o'clock will be the final last speaker, which will be Robert Miller from NASA Swampworks, and he is the leader of this event at the Moon Village Association. So for the telerobotics, and we are very happy to have him here, and so I hope you will watch it too. After that, we will have a short little break, coffee break, and we'll be back then. So thank you very much for giving us the possibility to share everything with what you have with us. So see you, and
Thanks for having us.
thank you. Thank you. Bye. Bye.
Please change here for BER Airport.
Ausstieg links. Nach Westkreuz. S5. Zurückbleiben bitte.
shed a tear just as long as you stand by me.
Da bist du ja. Wo warst du denn? Hallo. Oh, wie schaust du aus? Oh nein. Ein bisschen Staub abputzen. Ja.
Continue.
casualty. Just as long as you stand by me.
Da bist du ja. Wo warst du denn? Hallo. Oh, du schaust so aus. Oh nein. Ein bisschen Staub abputzen. Ja.
I won't shed a tear just as long as you stand by me.
Da bist du ja. Wo warst du denn? Hallo. Oh, du schaust so aus. Oh nein. Ein bisschen Staub abputzen. Ja.
Hello.
Hello, can you hear me?
Yes, I can hear you. So we are still not online. I will just put you online. Just want to inform you, it's we are streaming live on YouTube. So I will now change and put it online then. Okay, so hello, welcome.
Hi, are you having a good moon day?
Yes, actually yes. So we are really enjoying the day, and the rovers are running constantly. They're still running. We had some student groups which were missing, but we had additional ones. So it's still ongoing. So yes, it's running well from our side.
So how is it working? The students call in and then they're allowed to, how are you letting them drive? You have a special software?
Yes, actually we have, oh, Igor, you can tell
Yeah.
and explain, and I can show you some images.
Okay, so yeah, hello, first of all. The procedure is like that. For every full hour, the student groups are joining, always 2 groups at the same time, and they are first in a video chat with us, the whole group, and there we are explaining them how the whole procedure will work. Then they get the credentials for connecting to the rover, because we had to make sure that not all groups can connect to the rovers at the same time, only the group that we want to connect. And then we have 2 rovers standing there, and 2 groups are connected to each rover. And then they start with the competition. And the competition was looking like we were placing several QR codes on the test bed, and they had to find them, scan them with their phones, and that was guiding them to a quiz. Yeah. And they had to solve the riddles there, and then they could drive further with the rover.
Oh, that's very good. I've been watching online as I can between my other work. So I've been seeing there's 2 channels, and one channel has the stories of the adventures of Hyver, right?
Yes, also. This was now during the break, so we had a break now, and so we had the adventures of Hyver running. And so we can also, but during this we had this live stream where you can see the students and all everything which has been doing there. We have a mission operator. She's constantly in contact with them, giving them tasks that they have to operate. And so far our rovers are running very good. So everything works really fine, and I think it's very exciting for the students. We up to now had actually very good feedbacks. So we had also, well, we had some open loops, so groups did not come. So we had enough viewers here. So we are at the airport. This is the spaceport in Rostock-Lager. So, and there were enough kids also, very young ones, and we allowed them to drive the rover. So, well, yeah, they were just standing there. So yes.
Okay, so it sounds like it's going well.
Yes.
What was the plan for my presentation?
Whatever you like. Yeah, we are just happy to have you here, and want to thank you for being part of it and make this happen. And so you are the last speaker of today.
Okay, and is this live streaming now?
Yes.
Okay. So yeah, I want to thank you first of all for participating in the International Moon Day, and happy International Moon Day to everybody. It's a big day, and if you go to the website for International Moon Day, you'll see that this is truly a global event. There are many things happening across the world today, and it's a celebration of the first day that humanity stepped on the moon on July 20th in 1969. So it's really a great day for everybody, and we're going back to the moon very soon, and with humans, and in the NASA Artemis program, where the next woman, the first woman, and the next man will step on the moon within the next 3 years. So I think that's very exciting, and things are going to get even more exciting when we start teleoperating rovers almost every day on the moon. And this is just the beginning now. And the difference between Apollo and now is what you are doing at Neurospace used to be something that only NASA could do, or a big government agency. Now you have a small team of entrepreneurs doing it themselves. So this is a big difference between Apollo and now. We have the democratization of space, is what we like to call it. Anybody can go into space if they're motivated enough. And so that's what I'm seeing here is a highly motivated team, which is doing a great job. I'm very impressed with your videos, your online presence is just very, very professional.
Thank you very much.
Thank you.
Yeah, so I want to congratulate you on how far you've come in such a short time, but mostly I want to congratulate you for your energy, for your enthusiasm, because this is what it takes, right? It takes a lot of hard work, a lot of energy, and I see that in your team. I see the excitement, I see the energy, I see the youth. I think this is what's going to take us to the moon is the energy and the excitement of everybody involved, and we do it together, everybody in the world. You know, this is why the Moon Village Association is so important. It's the only organization I see that's truly global, international. There are no borders. We're all humans. When you look down from space, you don't see borders, and so that's what's exciting about this is that we're all working together. And I do want to make a plug, a promotion for the Moon Village Association. I'm the chair, co-chair of the Moon Village Association Analogs Working Group. And this activity here was started in the Analogs Working Group as a example of how we can do analogs activity. So analogs means it's a simulation of the moon or Mars here on Earth. But before we can really do this successfully on the moon or Mars, I would say you should not be allowed to go to the moon with your robot or your rover until you have proven it here on Earth first, right?
Yes.
It just makes sense. Why should you risk going to the moon if you can't even operate it on Earth? But operating it on Earth, driving through the streets of Berlin is one thing. But the next step is to take it to a field site. And we call that an analog test site. It's a site with an extreme environment, maybe a desert or something like that. And so then we should test it here on Earth first in an analog test environment. If it passes that test, then you can go to the moon. So the Analogs Working Group is trying to set up a network of analogs across the world, analog test sites in many countries, where we can then test this equipment and also test the team, because it's not just a robot, it's the team operating the robot. So we have to have good teamwork, we have to have good communications, we have to have good skills, and then the robot. So by taking these teams to these extreme sites, you can really get a good teamwork going, and you can test your control from mission control to the field, which is another thing that's often it's communications that breaks down, and when the communications break down, then everything else breaks down too. So these are all things we need to test, and the Analogs Working Group is doing this with the Moon Village Association, but we need more volunteers. The Analogs Working Group has been slow because we haven't been communicating well with the volunteers, so I'm going to use this opportunity to try to make a call for volunteers. If you want to help out with the Moon Village Association Analogs Working Group, you just need to go to the website. I'm not sure if I can share my screen here. Yeah, let me show you what that website looks like so that you can then find it. And then I would encourage you to join our group. I'm sorry, I'm just typing here. Okay. So, okay, I have the website. I'm going to share my screen. Okay, share. Okay, do you see my screen?
Oh, it's just loaded. Yep, there we are.
Yeah.
Okay. So this is the Exploration Analogs Working Group under the Moon Village Association. And Kurusha Ragi and myself are leading it. And so then you can go to this website, and we also have a Slack channel. We have a software called Slack, which is for collaboration. And so we can then go to Slack and well, I won't show it now, but once you join, then you can start collaborating on Slack. And one of our goals is to have a catalog of all the analog sites in the world, and then we can start testing the robots in these analog sites. So that's one of the activities that to start very soon. And we also want to report the results of today's activities, today's International Moon Day, to the International Moon Day Committee. They have a review after this International Moon Day, and then we publicize this, and we also go to conferences and we explain what we did on International Moon Day with telerobotics. So I want to explain to you, it's not just Neurospace today doing this. We also have a group in Hawaii. They're not even awake yet. It's 5 a.m. in Hawaii, and it's 8 a.m. I'm in California today, so it's 8 a.m. in California. So your day is ending, but our day is just starting, which is kind of interesting, being global. And then we have another group in Canada. The group in Canada is working right now, also doing the telerobotics. So we have 3 teams all doing telerobotics today. And when we started this, we said we need to do something with analog sites and robots, but we want to reach everybody in the world. Anybody in the world should have the chance to run a robot. And we've done that. We did that last year, and now we're doing it this year. We're going to do it again next year. So we've shown that anybody in the world can drive a robot from anywhere to Germany. So we know this is possible. My dream is to do this on the moon.
Yes.
So one day we will have an International Moon Day where we will be driving rovers on the moon.
Would be great.
But, and so in the future, we will have a Neurospace rover on the moon, and on International Moon Day, we'll sign you up. But instead of driving in the simulated moon, you'll drive on the real moon. But there's one thing, though, is we cannot let just anybody drive on the moon because there are rules for driving on the moon, so we don't ruin the environment. So I think in the future, we need a lunar driver's license. And then you have to have a lunar driver's license before you can drive on the moon. And so we probably will start as an activity of the Moon Village Association Analogs Working Group, a lunar driver's license test. And so I would like to put that out there for the community. Maybe we can all collaborate together and create this lunar driver's license. And then it will be a qualification you have, and you will not be allowed to drive on the moon without a lunar driver's license. I think this is very important because if you, sorry, okay. Dogs are barking. Sorry about that. So if you drive on the moon today and you drive just anywhere, the tracks you leave behind will be there for millions of years. There's no wind on the moon. There's no rain. It's a vacuum. So your tracks will last for a very, very long time. The only thing that will destroy the tracks of the rover is the micrometeorite impacts, which do happen, but over long time scales. So we probably need to think about roads on the moon. We need to think about roads, and you can only drive on the roads because we don't want tracks everywhere. We'll ruin the lunar environment. So if you have roads and you have rules of the road, then you also need to have a driver's license. So that's what I would like to propose to everybody listening today is how can we make a program, international program for lunar driver's license. And so let's start thinking about that. And if you want to collaborate on that topic, contact us at the Moon Village Association Analogs Working Group, and we'll start this lunar driver's license project. I think that's all I have to say today. I'm happy to answer any questions if you have any.
So how do you think we can start working on it, and how should it be done? Who set up the rules for it, and how will the license, who will hand out this license, who will certify?
So I think the Moon Village Association should hand them out. And I did look into the legal aspects of this, and is it legal to do this? Can you do this? And apparently it is legal. It's not illegal. It's not illegal, so it must be legal. right?
So one of our
And
speakers was a professor for space law, so I can contact him once more.
you can contact him, but I did contact a professor of space law, and she told me it's not illegal. So I said, so if it's not illegal, nothing's stopping us from doing it. She said, nothing's stopping you from doing it. So sometimes in law, the first person to do it sets the law. So if we do the Moon Village Association lunar driver's license, then it gives the Moon Village Association a little bit more authority because they're the first to do it. And then we can start debating about the legalities of it. Sometimes you just have to do it and set a precedent, and then we can debate whether it's legal or not. But I think we should do this just to because it will create a lot of interest from everybody understands what a driver's license is, and now we say this is a lunar driver's license. So everybody understands that. And if we do it through the Moon Village Association, they have an existing authority. They also have a relationship with the United Nations. The International Moon Day was created by the United Nations, but it was the Moon Village Association that lobbied the United Nations to create the International Moon Day. So because they have these connections, they could go to the United Nations and get the official approval or sanction for the lunar driver's license. So I'm just putting the idea out there. I'm just throwing the idea out there for everybody to think about. But I think this is quite exciting, and we can all work together and create this. So I'm happy to discuss this with you.
Great. I think we have
Manuel, if you want to just unmute yourself and chime in there, feel free to.
Okay, cool. Hi, thanks first of all. You mentioned the lunar driver license. I think when we think about, I mean, right now everyone has a picture and idea of, okay, humans either teleoperating the rover or something like this. We also have to consider autonomy, I guess. Because, I mean, right now with Mars, we actually see we have systems there, of course, their mission plan and everything, but they're sort of autonomous around. Delay to Mars is a bit larger. Moon is maybe not as critical. Still, there is delay, but at some point we also want to have autonomous robots driving there. And if we want to think this whole concept of driver license, maybe we also have to see, can we license robots? Can we license software running on robots, assuring exactly the same constraints we just pulled up for human driver license or humans driving?
Yeah, I think that's a great point. And I think that's where the idea of roads come in, or pathways. So you might have some kind of geo markers on the moon saying this, it doesn't have to be a real road. It just has to be a geolocated road. So some kind of software marker with coordinates that says you cannot go outside of these coordinates. And then the programmer has a responsibility to stay in that pathway. So, these are things we have to discuss and debate. But I think you're right. It's also a driver's license for the programmer of the robot.
Thanks.
And I suppose it would also require that the process would be certified, not just in terms of the program, but also in inputting the right commands and that sort of thing. So
I think the main thing is these pathways. If we have pathways, then the rule is you have to stay in the pathway, and then we have to decide: you drive on the right side or the left side.
Okay. So there is another one. Michael Schlüter, please.
Yes, hello. It's very interesting to see all these. The discussions are going really crazy now. I have also an idea. Actually, well, we are now discussing about driving on the moon, but the goal should be also to do something there, not only drive. For example, if somebody is thinking about mining, is this allowed or not to do something like this? I mean, to do some perforations or whatever, take some samples. This should be also regulated somehow, and also some kind of agreement should be also done, because driving is nice, but you have to do something there, I guess.
Yes, I agree. I agree, and this is a topic that's actively discussed. But the lawyers say if you have a mining site, you can put a safety perimeter around your mining site. And then if you have a safety perimeter, nobody can drive into your mining site for their own safety and for your safety. So this idea of a safety perimeter is what's being discussed right now.
Okay, thanks.
So I think with these events, as we have, I think it's the first start. We had a lot of exciting moments. For example, for us, it was also kind of evolution of our rovers itself. When we started the first time, when we went to this lunar yard, and we had it has tons of very fine grain of yeah, regolith actually. This is not any kind of sand. This is real regolith, and it's really fine. And we had a lot of problems with the first version of our rover, and with these, the new ones, they work very perfectly. They are capable of driving, and we can do all these kinds of maneuvers. It's not always easy, but it is. It's because the whole regolith is really loose up till the end actually, and they are still working fine. So there must be also a kind of definition of the surface where you drive the system actually, and how it should look like, and also this how it should be at the end, and what also requires to this analog lab, then analog surface test bed, so to get a kind of driver's license, and we need to set up all these things so to get some kind of license.
Another thing that if you drive on the moon, in the Apollo missions, the astronauts landed, and when they landed, it was 2 to 3 centimeters deep, the surface of the regolith. After 3 days of walking around, it was ankle deep, so maybe 6 to 10 centimeters deep. The more they walk on it, the looser it gets. And this is called dilation. Dilation is when the regolith gets fluffy, it expands. So it actually decompacts. It's compacted and it decompacts and becomes dilated. So if you drive on the surface of the moon on the same pathway over and over again, it's going to get deeper and deeper.
Yeah.
As you drive, it's going to get deeper and deeper, which will cause traction issues with the rover. So we need to find a way to stabilize the surface or to recompact it after a certain number of trips over this same pathway. So everybody needs to think also, how can we build a road, or how can we compact the regolith, or maybe the rover is built in such a way that it doesn't loosen the regolith, but the driving over the same pathway over and over again may be a problem on the moon.
Yes. So, yeah, we have experienced the same, but we are quite happy that the rovers are still running. But as you said, now it got very loose meanwhile, but still working. Yeah, interesting. It's always the difference, the surface you're using them for, and yes, and also the driving mechanism. Yeah.
And also, when you drive closer to the edge of a crater, the regolith is softer at the edge of the crater than it is away from the crater. And young regolith, fresh regolith, is softer than older regolith. So we also have to think about that, is where you drive. If you drive in a dangerous area, which is very soft, your rover could get stuck. So we need to think about where we drive, how we drive, and what the rules are for driving. And mining, of course, and doing science and all the other things that were mentioned. But there's more than just driving, for sure. But I think the driving is the easy way to start.
Okay, there is one more question.
Yeah, well, I mean, in addition to thinking about roads and thinking about driver's licenses, we'd also might need to think about some requirements for vehicle registration. Talking about making sure the vehicles are designed to a certain standard. I mean, our experience was one of our first generation rovers got bogged down relatively easily, but these rovers today have been going for, I think, almost 8 hours straight, and all we've had to really do is change their batteries. So that's one thing that we might also need to consider as a registration and certification, like you get with your car, to make sure everything's up to scratch.
Yeah, and that's a really good comment. And then that makes me think of emergency road services. What if you have to change the wheel? Can somebody help you?
Yeah.
Or can you change the wheel yourself?
We are going the same approach. So what we also meanwhile managed is like our wheels from 6 screws we have now reduced it to one screw, and then afterwards the approach is that they can change it on their own. So yeah, they can maintain themselves.
So I think rovers will need maintenance.
Yes.
They will survive for a while, but they will need maintenance, and possibly you will have to have many rovers and put them in a parking lot when they fail, and bring a new one out. And then when the astronauts come, they can repair them.
Yes. For example, this would be also one approach.
That's one approach. There are other approaches, but that's one approach.
Yes. So, are there any questions? So our last term is still running. The last students are still driving the rovers currently.
The last 15 minutes.
The last 15 minutes are now. And then our event will end, and I think for you it's just starting. So we want to thank you very much for giving us this opportunity to be part of this event. For us, it's a very special day. We also worked hard and organized a lot. We have a great team. There are lots of interns. They are sitting here. They were moderating. And we have so many people working on this and making this happen. And I want to thank my team, thank the Moon Village Association, thank Spaceport Rostock. And we are in for the next year. So for
I want to thank Neurospace and all the volunteers and Rostock and everybody, because what's nice about these events, it's a goal, and you have to pull together to make it happen for that goal. But seems like you've managed to do that, so congratulations, and let's keep going. I hope you have a nice party tonight. I saw you have an after event party, which is important to celebrate your results. So enjoy yourselves, and I hope to see you soon.
Before you go, Rob, can I just get everyone to turn on their cameras so we can have a nice screen grab at the end of our stream here?
Join. You want to join? And
I mean,
one more guest. I have one.
If some people from that room want to come in here and join
Yeah,
behind
so
me,
you
that
can
also works.
go to Rob. So we also have my special guest here is my mom, because it's also her birthday today, and she's joining us here. So happy birthday, Mom!
Happy birthday.
Hey, Georgia and Tilly, can you get your heads down a bit there?
Okay, so
There we go.
let's have one. The other team is downstairs. They are still making they have to suffer at the Lunar Yard.
Shall I do the?
Oh no, I think Rob is doing it, isn't it? Yes. Okay.
Yeah, hold on.
Thank you.
All right. 3, 2, 1.
Cheese.
Just like what the moon's made of.
Okay, so thank you very much. Also, thank you to Giuseppe Raivaldi again. It was so great to have him here. His presentation was really great. We were all listening very carefully. So, and yeah, thank you. And yes, see you next year for the next event then.
Okay.
Thank you very much.
Thank you for the invitation too. For everything.
Thank you.
Thanks. Have a great evening. Bye.
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 Bye. Okay, so yeah, we just let it stream once more.
Okay, the video.
Okay, so we are ready. We are going, and that's the next.
Okay.
Wow.
Now I can pass out. Can I?
Yeah. Okay.
I kept like dozing off with
Yeah, this last meeting, my eyes were closing on their
I was
own.
doing like this, and then I kept hearing like a laugh, and I was like,
It was like this 1 second sleep.
yeah, I was just scared. In the car I'm gonna sleep. Who's driving? Charlotte?
Oh, for the feverish Charlotte.
Oh, is it?
Yeah,
Oh my
she's
God.
having a hard time today.
So
She's
can
under
someone
painkillers.
else drive then? For example, Max or you? Will you?
Yeah, I can.
Okay.
Actually, I wanted to get wasted, but I can also drive and get late.
You can get wasted and drive, but that's what I was.
Yeah, with the lion. I'm trying to find the lion.
Have you heard that there is a lion walking around Berlin? Yes.
Lion?
Yes.
Yeah, in South Berlin.
Did they find any news about it now? Have they had any?
No, they deployed helicopters.
Yeah,
But
there's
did
a
they
police
capture him?
helicopter
Did they
searching
capture
for.
him?
No, they extended the, what you said,
No,
they
that's-
extended the region of.
Die haben es noch nicht gefangen. Es läuft immer noch frei rum.
No, they enlarged the danger zone until Tempelhofer Feld now.
Und alle Leute sind drin? Keiner ist auf der Straße?
No,
I
they,
don't
they, they
know.
just like recommended that you don't go out, but you don't have to stay in.
Where is this lion?
I don't know, no, not where.
Tell me! Why is no one telling me where the lion
How do you lose a lion? Like, how do you find a lion?
Seriously?
Here, the next newspaper article. Raubtiersuche in Kleinmachnow. Haben Sie den Löwen schon angefahren?
Did you hit the lion with the car?
Oh
So
There's sometimes when stuff happens in the world and it's just crazy. It's one of them.
okay, so let's pack our stuff and visit the lion.
Yeah, let's go to Neukölln and search for the lion.
So I
It's screaming out of
have
the
put
window.
this one.
Okay, should we just end the
Yeah.
stream now?
Yes, and
You can switch stop streaming.
Yeah, it's
So we will
really
stop
late.